Okay, so very good afternoon, good morning, good evening, depending wherever you are. It's really my great pleasure and privilege to welcome you all to the first conference on Symposium on Magnetism and Spintronics. Before we start, I like to request Professor Vedang Mohanty, Professor Karunakar Nanda, and Professor Anjan Burman to switch on their camera. Yeah, thank you. So Professor Sudhakar Panda, Director NICER, he had to go through some emergency medical treatment. So that's the reason he is absent today, but he has sent his message, which I will play in a minute. I like to just tell a few things before we invite other guests to share their words about this conference. So, okay. So, first of all, a warm welcome from the organizing committee, core committee of the Symposium on Magnetism and Spintronics. The key is SMS, and we plan to hold SMS-1, 2, 3 in next years to come. Before I give some details about the conference, I first of all give a warm welcome to the guest of this inauguration ceremony, Professor Sudhakar Panda. He is not there physically with us right now, but he has given his message. He is the director of NICER. He belongs to the School of Physics, and he works on string theory. Then we have Professor Karunakar Nanda. He is presently the director of Institute of Physics in Bhubaneswar, and originally he is from Indian Institute of Science. He works in the Material Research Center at IIC, works on various things in condensed matter physics. Then we have Professor Vedang Das Mohanty, who is the Dean of Faculty Affairs at NICER Bhubaneswar. He also belongs to School of Physics and very well known in his for his nice work on experimental nuclear physics. And then we have Professor Anjan Burman. He is presently the Dean of Faculty Affairs from SN Bose Center for National Science at Kolkata. He is actually one of our core committee members for SMS. And I really warmly welcome all of you and thank you so much for giving your time to join this inauguration ceremony. I like to just take the opportunity to also share some happiness that our laboratory at NICER, and that is Laboratory for Nanomagnetism and Magnetic Materials, we call it LNMM. It completed 11 years this year. We actually wanted to celebrate our 10 years last year, but due to the pandemic, it was difficult and we didn't organize. And with this conference, we are also celebrating the 11 years of our laboratory. So I like to thank all my mentors, peers, colleagues, students, collaborators at this occasion for their very generous support all the time they have extended for carrying out our work and in all sorts of our life. I'm really grateful to all of you. Thank you. Then I like to mention that on this occasion that we wanted to actually start the conference on like something on related to magnetism and spintronics. As you may know, we are organizing since last year, June, the webinars, weekly webinar events, webinar series on spintronics that we call as W2S. Every Thursday we actually organize, and I think about 72 talks have been finished and we plan to continue till next year. But that is more focused on spintronics, and we have a strong community in India working on magnetism and magnetic materials. So we thought that we will address both these communities of working purely in magnetism as well as spintronics. Although the spintronics community is not so large in India, but it is growing slowly. And so in that respect, we actually conceptualized this conference concept of Symposium on Magnetism Spintronics, where the core committee members actually come from different cities, Professor Anjan Burman, Professor Perumal from Guwahati, then Professor Pranam Nuduli from IIT Delhi, Professor Anil Kumar from IISc Bangalore, and Professor Chandrasekhar Murapaka from IIT Hyderabad. So we plan that every 2 years we will host this conference at different places. So we exactly don't know the next one will be at which city, but we will let you know very soon about it. So I like to really thank the core committee members and also the local organizing committee members for their general support. Although Professor Anjan Borman will give a formal vote of thanks at the end, I have requested him. But I actually thank all of you, all the speakers, all the participants, and the volunteers. Most importantly, they are actually working. Of course, it is online, but still a lot of organizational aspects were there. And I really thank them, and also our computer center who helped in making the web page. I'm really glad to share that we have about 420 registered participants from about 23 countries, and we have 24 invited lectures and about 15 short invited talks. These short invited talks are mostly the LNMM alumni. So this time we just kept it like that, but I think subsequent years it will be open for everyone. And the speakers are mostly about from 15 countries. We have about 86 posters submitted, and we are uploading the poster files tomorrow and day after tomorrow. There are 2 poster sessions, and very nice work have been submitted. I have really seen the abstracts and really promising work. So I think with this little introduction about SMS, I like to now stop myself, and I again welcome all of you. It would have been really nice if we would be able to host you offline. So basically physically at NICER. We have just recently made a wonderful auditorium, and it would be really nice to welcome you at NICER. But due to the pandemic, I think the online event is something more suitable. But I hope next year or year after, we will have an opportunity to welcome you at NICER. And I think Professor Vedant Mohanty is looking at this. He would be happy also to meet many people and our director and others. Okay, so with this, I will stop now. And I will play, or Sakti or Puspendra, whoever controlling, can you play the video of director, Professor Sudhakar Panda, his video? Okay, maybe we play his video a little later. So I request now Professor Karunakar Nanda to say a few words.
So good afternoon to all of you. So I am indeed very glad to note that a focused symposium in the field of magnetism and spintronics, that is SMS 2021, is being organized by our National Institute of Science, Education and Research, Bhubaneswar, for the first time. And I believe that it is going to provide a platform for senior and young researchers from all over the world to share their results, view, and update their current understanding on the subject. I also believe that you will also all be benefited from this symposium. Just now, just a few minutes before, Professor Vedanta mentioned that there are 400 participants. So basically the overwhelming response received by the organizing committee from 23 countries. And I believe that it is probably the power of magnet that attracted so many participants from all 23 countries. So, and I also understand that organization of such a big symposium is a challenging task. And I applaud that organizing team, and in particular, Professor Vedanta, for their hard work, and wish all the organizing committee a grand success. So thank you all.
Okay, thank you, Professor Nanda, for your speech. I clap on behalf of everyone. I forgot actually in a hurry that in this inauguration ceremony, Professor Wolfgang Kliemann is also a guest. I request him to switch on your camera. I'm really sorry, I apologize for this. So a lot of computer glitches and I forgot completely. So Professor Kliemann, you please switch on your video. And Professor Nanda, you also please keep your video on. I don't see right now. Okay, so now I request Professor Vedant Mohanty to say a few words about his speech. Thank you.
Thank you, Shubhankar. First of all, welcome to all participants. And thanks to all the speakers, invited speakers, and other participating speakers for accepting our invitation to be part of this symposium. The list of invited speakers has several eminent persons, the names of which I get to know because of Suvankar, dragging me into many of his discussions and meetings. And also, thanks to the organizing team to think about such a topic, which is rapidly growing, magnetism and spintronics. Now, also, as Subhankar said, it is 11 years since we started this topic at NICER, with his lab getting set up. Since then, we have added some colleagues in both experiment as well as in theory, and we are building up a strong group in magnetism and spintronics. So that is one of the top areas of research at NICER. I am not from the field of magnetism and spintronics, but when I look at the today's speaker list, there is Dr. Niru Chaudhary, Sagarika Nayak, Swagato Malik, Srijani Malik, all doctors. I think I was the doctoral committee chair of all of them, and I have learned more about magnetism and spintronics during that course of their presentations every year in their annual talks. Then we have a set of young people which got trained in our lab on magnetism and spintronics. They are, I can see it is Gajanan Pradhan, Arup Behra, Swapna Sindhu, Biswajit, and now they are taking whatever they learned to greater heights at all over the world. So I will be very happy to hear them speak later today in the evening. So when Suvankar mentioned to me about this topic and this novelty of having this symposium, I was looking yesterday night about different aspects of it. I did also come across an alternate track, spintronics without magnetism. So this is an interesting topic where the spin orbit effect lies in the heart of efforts to merge spintronics with semiconductor technology. At some point of time, it may be good to have one talk on this alternate track in this regular feature of magnetism and spintronics. So with these words, again, welcome all for this symposium. Thanks, Suvankar and the organizing team for making this happen. And thanks to all the speakers, the participants, and wish you all a very successful discussion and symposium. Thank you.
Okay, thank you so much, Professor Mohanty, for your kind words and very encouraging words. Now I request Professor Wolfgang Kliemann, my PhD supervisor, and I request you to say a few words. So Wolfgang, please unmute and say a few words. Thank you.
I'm online.
Yes, we can hear you.
Okay, and you see me?
Yes.
Okay, fine. It's always a challenge. Well, dear colleagues from NICER and the Institute of Physics at Bhubaneswar, and from the Bose National Center for Basic Sciences in India, and dear all who are listening. As an external participant of the upcoming scientific meeting, I am deeply honored to be invited to give an address to the plenary audience. You know, my only privilege is I was the PhD advisor of the convener of this forthcoming symposium on magnetism and spintronics, SMS-2021, Dr. Subhankar Bidanta. I remind you, he spent the years 2002 up to 2006 at the University of Duisburg-Essen in Germany. It's in northern Germany. It's very cold here now. We have 0 degrees centigrade, but still we survive. And he earned his PhD in September 2006. Yes, I have to confess that my own forthcoming talk, which will come next, will be completely Spintronics free. I'm very sorry, and isn't it a shame? Well, I have my excuse is I'm an experimental physicist, emeritus, lacking any laboratory since a couple of years at the age of 79. So it's a little bit too late to really enter the real Spintronics. But you will hear something about magnetism and related subjects next. And you accepted my talk. Thank you. I'm very happy to get this opportunity. But in particular, I'm totally motivated to give my comments on this meeting and on its organizers, namely to praise their immense efforts invested for its final success. I just learned you have 400 participants on the screens, so congratulations. And everybody knows what this means in Corona time. We are all a little bit isolated, and in particular, traveling becomes very cumbersome. So we are far away, some 3,000 miles from India. I'm sitting here in northern Germany, and you are in the warm environment of India. That's good for you. And well, it is not impossible, and the Zoom transmissions are just a substitute. And I have now the impression everything is fine with the technology. Congratulations also to your collaborators who trained me to come into the screen. I'm deeply impressed of the wealth and this breadth of the subjects being treated in the program which I browsed. I look forward learning new results and meet new, what's happening?
No, you continue, it's fine, please.
Something happened, at least virtually. Maybe next year we can meet again in person. So for today, have a good time at SMS-2021. Enjoy meeting friends and bring good news when you yourself return home. Thank you, Subanka, for inviting me, and good luck. Have fun. Thank you.
Yeah, thank you so much, Professor Kleeman, for these very encouraging words. I really appreciate your training, and I'm trying to continue that. So now I will share my screen, and I will show the recorded video which we took last evening from Professor Ponda. I hope my screen is visible.
Yes.
Okay, so.
Hello everyone. Good morning, good afternoon, and good evening to all of you, depending on wherever you are on the globe. But wherever you are, even if it is virtually, but this conference on International Symposium on Magnetism and Spintronics will be connecting you. I'm really delighted that the School of Physical Sciences of Niger Bhubaneswar is organizing this conference. The aim of this conference or symposium is to provide a platform to share knowledge on the current research trends on magnetism and spintronics. Research on magnetism and spintronics is one of the most sought after areas, as I understand from my colleagues in the School of Physical Science, Niger. The School of Physical Science is well equipped for cutting-edge research in nanofabrication, photonics, multiferroics, dielectrics, solid-state ionics, spectroscopy, and transport studies, superconductivity, ultra-cold atom, and quantum optics. Besides that, we have groups of faculty working on statistical mechanics, nonlinear optics, and semiconductor lasers, atomic physics, high energy physics, and string theory, which is a byproduct of quantum field theory along with quantum gravity. There is also a small group working on quantum information and other frontier areas in physics at Niger. Niger is one of the new research institutes under the aegis of the Department of Atomic Energy, and starting with a transit campus 35 kilometers away from this present campus, the institute grew up rapidly and has been well recognized in India and abroad. After doing their PhD, the School of Physical Science, after doing their PhD, are doing postdocs abroad in good places, and some of them are back to India also with faculty full science. This institute is a teaching cum research institute. Many students who have done their MSc in either physical science, mathematics, biological science, chemical science, they have gone abroad for their abroad and other good places in India for their PhD degree. The present organizer of this symposium, Dr. Shubhankar Vedant, had organized earlier big conferences in past, and it was always a great success. I at least remember the ICMA-GMA 2018 conference held in our campus, which was an excellent conference, and he has been organizing the webinar series on spintronics since more than 1.5 years, and it is also a great success story at Niger. In a similar note, I expect SMS Symposium will not only help to spread the research mandates of Niger, but also help younger graduates and undergraduate students of both India and abroad to decide their future career goals. Niger supports this conference wholeheartedly, and I'm confident that, like in the previous cases, it will be a great success. Enjoy the meeting, have your discussions, exchange your ideas. I'll be happy if new collaborations come up after this symposium. Thank you very much.
Okay, so thank you, Professor Konda from the organizing committee for kindly giving your message. So now I request Professor Anjan Burman to give the vote of thanks, and then I will present some mementos for our guests, and then we can continue the lecture. We are just on time. So Professor Burman, kindly give your vote of thanks. Thank you.
Thank you, Professor Vedanta, for kindly inviting me to give this vote of thanks. So on behalf of the organizers, I extend my gratitude to those who deliberately came forward and shared their ideas and helping hands to successfully organize this conference, Symposium on Magnetism and Spintronics, SMS 2021. The first and foremost, I would like to express my sincere gratitude to Professor Sudhakar Panda, Director, Niger, for conveying his motivational words and his kind support for organizing this conference. I'd also like to extend my gratitude to Professor Karunakar Nanda, Director of Institute of Physics, Bhubaneswar, for taking time out of his busy schedule and grace this occasion with his presence. My sincere thanks to Professor Vedangodas Mohanty, Dean of Faculty Affairs of NISER, for his indispensable assistance to well organize this event. Further, our heartfelt thanks to our beloved Professor Ulkan Kliman for his kind and inspirational words. I'd also like to thank Professor Ashok Mahapatra, Chairman of School of Physical Sciences, NISER, for his kind cooperation at any time. Our deepest gratitude to all esteemed delegates for accepting their invitation and share their experience to work with all of us via this conference, which will be extremely beneficial to all the participants. A heartfelt thanks to all the core committee members. I'm also a part of that, the SMS-2021, and we are now looking forward to having future SMS conferences at different cities in different institutes. I'd also like to extend my gratitude to the local organizing committee members for their constant support and suggestions to organize this conference. It is needless to mention the great effort of the Computer Center of NISER for providing immense help for building the website and the technical help. We thank the NISER administration for their support staffs and the support staff for the kind help and support. Last but not the least, of course, I express my sincere gratitude to Professor Shubhankar Vedanta, the convener of SMS-2021, who conceived this idea of this symposium and communicated with all the other people involved, including me. And he has done a wonderful job in well organizing the first ever symposium on magnetism and spintronics, SMS-2021. With this, I wish SMS-2021 a great success, and we hope to, and we look forward to organize this conference in a periodical manner in the near future. Thank you. Thank you all.
Thank you, Professor Burman, for your vote of thanks. Now I will share my screen and I will show the memento. I request you to read it basically and present it digitally to our guests. So this is the digital flag or the memento for the director NISER. I request you to kindly read it.
Yeah, so Symposium on Magnetism and Spintronics, SMS-2021, National NISER Bhubaneswar, India, takes immense pleasure in presenting this plaque to Professor Sudhakar Panda, Director NISER Bhubaneswar, for being a guest in the inaugural ceremony. Thank you, sir.
Yeah, thank you very much. Thank you. Then I request you to present this memento to Professor Karunakar Nanda.
So again, Symposium on Magnetism and Spintronics, SMS-2021, NISER Bhubaneswar, takes immense pleasure in presenting this plaque to Professor Karunakar Nanda, Director, IOP Bhubaneswar, for being a guest in the inaugural ceremony. Thank you, sir.
Thank you.
Okay, so Symposium on Magnetism and Spintronics, SMS-2021, NISER Bhubaneswar, takes immense pleasure in presenting the plaque to Professor Vedangodas Mohanty, NISER Bhubaneswar, for being a guest in the inaugural ceremony. Thank you, sir.
Thank you.
Symposium on Magnetism and Spintronics, SMS-2021, NISER Bhubaneswar, takes immense pleasure to present this plaque to Professor Ulkan Kliman, Emeritus Professor, University of Duisburg, Essen, Germany, for being a guest in the inaugural ceremony. Thank you, sir.
Thank you.
Okay, now I will read this for you. So it's really my pleasure to present this plaque to Professor Anjan Burman, the core committee member and one of our leading expert in magnetism and spintronics in India. So Symposium on Magnetism and Spintronics, SMS-2021, takes immense pleasure in presenting this plaque to Professor Anjan Burman, SN Bose National Center for Basic Sciences, India, for being a guest in the inaugural ceremony. So I think we are just in time. So I like to really again thank all the guests. Thank you so much, Professor Vedangodas Mohanty, Professor Karunakar Nanda, Professor Ulkan Kliman, and Professor Sudhakar Panda, who is not here right now. Okay, sorry. Again, I sincerely thank all of you, and let's hope that we will have a very vibrant conference for next 3 days. And now I think we can stop, and we finish the inaugural ceremony. So I request Professor Saurabh Giri, who is the chairperson, the session chair for the next session, and Professor Kleeman is the next speaker. So I think we can start the scientific session. Thank you so much. So thank you all. Thank you very much. Professor Giri, you can now take over.
Yes. Thank you, Professor Vedanto. I am honored to chair this special scientific session. In this session, we have 4 eminent scientists as speakers. The first speaker is...
Sorry, I just actually in a hurry now. This is a new training we have to do. I forgot to introduce Professor Saurabh Giri. Professor Saurabh Giri is a senior professor at the Indian Association for Cultivation for Basic Science in Kolkata. He is an expert in like magnetism, in exchange bias, multiferroics, and various frustrated magnetism systems. He has done very nice work, and I'm really big fan of his work. I'm really privileged that he has kindly agreed to session this chair. So it's all to you. I'm really sorry for breaking the briefing. Please continue.
Thank you, Professor Vedanto. So as I have expressed that we have 4 eminent scientists as speakers in this session, and first speaker is Professor Kleeman, and it is my privilege to say some few words about him. Professor Kleeman is a professor of experimental and applied physics at University of Duisburg-Essen. He received his PhD in 1968 from University of Göttingen and became professor at University of Paderborn in 1975 and Duisburg since 1982. His perpetual research interest in both magnetism and ferroelectricity brought him to the different international famous universities in the globe, such as University of Paris Sud, UC Santa Barbara, Riken Tokyo, SNU Seoul, and UFMG Bell Horizonte as a visiting professor. He has published more than 450 papers in the reputed international journals, which has the citations over 12,000 with H-index 47. He has been serving in editorial boards of reputed journals and organizations, committees of various conference series. His activity have recently become focused on magnetoelectric and multiferroic materials. So it's my pleasure to invite Professor Kleeman to start his talk. Professor Kleeman, please.
You don't have my video?
Yeah, it's fine.
We can see your video, but not at your slides. You can, yes, you can share your screen. Yeah, something is coming.
Right.
Yeah, we see it.
No, yes.
Yes, please start.
Okay, it's running. So, okay, you see here my title, Universal Domain Wall Dynamics in Disordered Ferroic Materials. This belongs to the topic E of your map, roadmap, magnetic domains and domain wall dynamics. And you will see surely magnetic domains and their dynamics and also some related ferroelectric materials, which are interesting enough. In the background, you see our campus. Physics is somewhere here. Can you see my arrow here?
Yes.
Yes, okay. I was not sure. And here is my my residence, academic residence. Okay, let's start with my talk, interacting ferromagnetic nanoparticles from superparamagnetism to superferromagnetism. That is a field which we started in 2001. Supermagnetism starts with superparamagnetism at increasing nanoparticle concentration to super spin glass and super ferroelectrics, super ferromagnets, sorry. So first of all, we start at low density. The gaseous non-interacting material might be sketched like that. And then if you switch on the dipolar interaction between the spins, you get a frustrated interaction because something is happening here. That is the question mark, which goes into the glassy disorder. That means you will find triangular arrangements of super spins. So the nanoparticle spins, total spins, which are not collinear and not anti-collinear either. And at high concentration, after switching on dipolar and exchange interaction, will go to superferromagnetism. We started this work with so-called discontinuous multilayers together with colleagues from Lisbon. It is multilayers of soft magnetic cobalt iron alloys embedded between alumina nanoparticles, nano layers. And here I show you how it's made. On float glass, you evaporate or you sputter alumina, then cobalt iron, and they do not wet. They are not wetting. This so-called Vollmer-Weber growth mode makes them nanoparticles totally embedded in this multilayer. This idea has been followed in 26 publications together with the originators of the materials. This is Susana Cardoso and Paulo Freitas from the University of Lisbon. Susana is expected to join the meeting. I'm not sure if she really has already shown up her contribution. I hope very much. Hola, Susana. Okay, let's go into what we did those days. Shortly after this agreement between Lisbon and Duisburg, we investigated a single monolayer of alumina, cobalt iron alumina, 3 nanometers, 0.9 nanometer and 3 nanometer thick on a X-ray transparent KBR substrate. And here you see the distribution of the nanoparticles. You see the hexagonal environments here and here, some of these triangular arrangements. And here is the statistics of the width. The average diameter is 3 nanometers, and the distribution sigma is about 20%. So pretty close, but not really regular. In this first, from these first layers or multi-layers, we measured the magnetic susceptibility. Here you see the real part to the left hand, the scale, and the imaginary part, which is here, for frequencies between 1 Hertz down to 10 millihertz. And you see the most probable relaxation time is situated at the peak of these curves, and it's slowly shifting towards lower temperatures. Here we are in the vicinity of 50, 60 Kelvin. And the first idea was to try a blocking ansatz, tau, that's the inverse frequency, more or less, to be proportional to an exponential according to Arrhenius, Neal, Brown, and a plot versus 1/t of the logarithm of tau gives a reasonable straight line, but we have to pay attention to the parameters before. What is the anisotropy energy, which is fighting with the thermal energy, kV, something like 10 to the minus 20 watt seconds. That's pretty small, but we don't know exactly what happens with such a nanoparticle. Let's look for the prefactor. And here we are really alarmed. This tau naught is in the range, the region of high energy physics, so nuclear physics, and that's certainly unreasonable for nanoparticles. And now we come to the final idea. Can I switch off? Wait a minute. I have a button, big button on my, okay. Maybe you can you see the background?
Yes.
Yeah, I cannot because there's something loaded upon it. Okay, that's the presentation of these data. Now, following this, which I cannot see here, it's a power law. Tau as a function of the inverse reduced temperature with respect to glass temperature. And the best fit gives reasonable parameters of the prefactor, 1/10 of a microsecond, and Z nu, the dynamic exponent, is around 10, which is known from spin glasses. And the glass temperature finally is Tg 46 Kelvin, and that is reasonable, and we believe on that. So I've said something about this super spin glass. I have not enough time to tell more about that. Let's go to larger thicknesses of the cobalt iron, which then coagulates to nanoparticles starting from 1.1 to 1.6 nanometers. And here we want to see if this is really the superferromagnetic state by magneto-optic Kerr effect. So here is the program what to see. Superferromagnetic domains of this multi-layer cobalt iron with alumina of this these parameters. And what we expect is somewhere some domain boundary between in plane up and in plane down magnetized magnetization. And here we see the result. longitudinal magneto-optic Kerr effect measured here in a time series from 1.5 seconds to 7 seconds, switches the up magnetization step by step to the down magnetization. And we can see this also in a movie where the happening is real time. We see how this fuzzy domain boundary is marching on the screen. So this sideways motion shows you the process of remagnetization from up to down. And for this, we have a theory which had been discussed by Thomas Natterman, Prokofsky, and Vinokur in this Physics letter. They predicted that at finite temperature, a rough domain wall in a random medium will encounter dynamic phase transitions at different field amplitudes. And there are different critical fields, H omega, HT1, and HT2, which are mapped here on a magnetization versus field hysteresis. This is incomplete, which stops before it can switch. And here we have so-called local relaxation. So relaxation of the magnetization of reduced space without bulk movement. But then there is a crossover at this point to the so-called creep, dynamic creep. And there's a discontinuity of the M versus time or M versus field characteristics. And then the creep goes into an accelerated slide motion. And from the slide, we come here to the so-called switching region. So I hope you can see that. I cannot. That's a pity from this arrangement of the screens, which are intermixed here. Here we see a periodically dynamic phase transition of a cobalt 1.4 nanometer, alumina 3 nanometer, 10-fold stack of single layers. Let us first start this here. It is a so-called Cole plot. The ordinate is chi double prime, the imaginary part, and the ordinate is the real part. And here we have the low field amplitude, which is applied, and frequencies between 1 kilohertz and 1 millihertz. And we see here the flat relaxation characteristic and then the linear creep characteristic. Then we switch over to the lower bound here. I hope you can see it. It is covered here by whatever meaning, 1 kilohertz, 1 millihertz, from creep to accelerated slide, and then to switching at 3 different temperatures. Here the temperatures are the same, but at low field, it is the inverse order. You see the blue on top, and here a blue on the bottom, and here on top. Okay, and from here we have the idea that these materials follow a certain scheme. The icon of our talk is this coal sketch, which shows all the different do I bother you by switching here? I don't know how to remove that.
We see your screen.
Yeah, but I cannot see what I show. That is my problem.
Oh, I'm
So
sorry.
here. Do I destroy something? Yes.
Yes.
Yeah, the video is stopped.
You kindly share again.
Yeah, video should.
You share your screen.
Yeah.
Yes.
My goodness. But
It's
I'm.
We see it.
Yeah, but it's now the beginning. But the screen is half covered. I'm very sorry.
Oh, we don't know.
That's
But we can see the full screen.
Yeah. Okay, I don't know what I have written here, but I have to go to full screen, sorry. And then I move on. And here I have another material which we have borrowed from University Paris Sud in Orsay. Jacques Ferret and colleagues have worked on platinum, cobalt, platinum, triple layer on semiconducting substrates. And here they show the creep from down magnetization to up magnetization. And this is shown here, the velocity as a function of the external field. And here we have the creep regime. This is the theoretical exponential power law, velocity versus inverse field. And the slide regime is a real power law, nearly a linear curve. And this is what we see also in our results. Here I show you the real part and the imaginary part of the susceptibility. And here the Cole plot, chi prime versus chi double prime versus chi prime. And we see at high frequencies in this range, the relaxation characteristic, then the bend over, the kink point to the creep regime, and the next station is the slide, and the next at a higher temperature, better seen, is the switching movement. So that is what we find here from this platinum, cobalt, platinum, and this was quite satisfactory to have that close to this sketch, which is schematic icon. And here I show you by Jan Renzius, who was in my group at that time. He's now in ETH Zurich as a lecturer, I think. Now, then as a young student, he found out a trick to produce domains in a subcoercively biased AC field. And I can activate, I hope. Oh yeah, now we have a movement, sorry, a movement of the boundaries from up to down magnetization. And that looks quite funny. And you can play around with that. And I show you another document of that magnetic creep in the same material. Here you see the alternative field applied, 0.5 millitesla, and phase shifted the magnetization, which goes up and down. And every peak shows a large area black, and here we are in the minimum large area white. And we were very attracted by this figure, which reminds us of a famous French painting. It is the painting Liberty Guides the People in the 1830 revolution, which has been painted by Delacroix. I can shift my Delacroix in the Louvre Museum. Okay, but that's only entertainment. Now I come to a non-magnetic material. We wanted to see more the dynamics of periodic stripe domains, and we found a wonderful, I have to move this nasty line. So Pamela Thomas gave us the potassium titanyl phosphate, KTiO4, which is a ferroelectric above 920 Kelvin. This specimen is part of a 6 by 6 by 0.6 millimeter cube with a low periodic poling of period of 9 micrometers. Here you see lambda half down polarized, and this up and down and down, down and up. And if you apply an alternative field, in this case, the electric field, perpendicular up and down, you make a movement of the domain wall, and these domain walls are performing different movements, and we are at, in our case, in the relaxation regime and the creep regime. So we are from 10 to the 5 to 10 to the -4 hertz frequency, and these the relaxation peak is of the imaginary part, this bell-shaped curve, and the sigmoidal or S-shaped curve is the real part. If you put them together in a Cole plot, you have chi double prime versus chi prime, and that this gives something like a depressed circle. And below this frequency, where we have a dynamic phase transition, relaxation to creep, these two curves are completely parallel, and this means in the Cole plot, this is a straight line. And that's a wonderful demonstration of this kind of, I can also move that out. I found a trick. The Cole plot shows you this part and this part, and yeah, well, sorry. Now I go from the phase transition at 233 degrees down to lower temperature and to higher temperature, where we see some deformations. This is in crossover region, which I'll touch immediately. First of all, we have to know how to describe this depressed semicircle. this is described by a Debye function with in a kind of sub-Debye presentation, 1 minus alpha, and the correction factor is 0.28. So this is a fitting parameter. And okay, now I can move this bar, which you don't see, obviously. At creep frequencies, we have another function from the theory, where it's also a correction parameter beta 0.35, which allows fitting of this curve. And the intermediate curves between totally stretched into the creep and totally curved into the relaxation regime is a continuous crossover phenomenon of relaxing wall segments down to the so-called lock-in length scale at the critical temperature. Okay, the last point which I want to show is another interesting ferroelectric, so-called relaxer type ferroelectric, strontium barium niobate SBN, which has become very famous in this community. Here you see the C-plane of this tetragonal symmetry. Strontium and barium are mixed, but they have all the same polarity. But there are two changes. Yeah, okay, some text: charge disorder, tetragonal tungsten bronze structure with stoichiometric negative cation, that is here, which are effectively negative vacancies, and random positive dopants, rare earth, cerium plus, for instance here. And these two disordering charges produce local random electric fields with fluctuations. And we have shown 30 years ago the solution of the so-called relaxer problem in ferroelectrics. They give rise to the so-called polar nanoregions in the non-ordered range and nanodomains in the ordered range of the material. Let me show you some, yeah, this was published in 2006, some PFM, so piezo force microscope presentations of PNR. PNRs are polar nanoregions, which are shown up or down polarized, red and blue, and you see they exist above TC. Here's 340 Kelvin. TC has an intermixture of the two kinds of domains or nano regions, and here at lower temperature, this is 300 Kelvin. You see here a growth of these regions, but they are still existing. Now we know that the system will not be regularly ordered at lower temperatures, and this is visible in these plots. We find the persistence of relaxation to creep transitions in this material around the global phase transition, which is 337 Kelvin. That's in this plot of chi double prime versus frequency at the high frequency range. Yeah, 10 to the 4 hertz. I can't see it. Yeah. And you see they are on top, and here are the temperatures below 337 K. So the system remains self-similar above and below the Curie temperature. And this is better shown, or more clearly shown, in this cool plot, chi double prime versus chi prime. And here we see this curve, which contains the wall dynamics continuously from the relaxation on creep regime here. Here are the symbols. Here we have the relaxation peak, and here the creep, and this remains at higher temperature here and here, here and here, and here up to 350 or more Kelvin. So this is the response of the free PNRs, which are formed by local random fields, which transform into fixed nanodomains on cooling. And you see that they remain resident in these spectra here below 335, 333, and they fade out for a while. Another effect was unexpected. That is, wait a minute, here, these slopey curves, which are here and here and here. These are polaronic effects. This is purely electric. Free electrons interacting with the ionic charges make polaronic effects, which have nothing to do with polar nanoregions. Okay, that's a little bit cumbersome and disturbing to you, but I just wanted to explain. And also the last slide, I only want to go briefly. My time is over. This SBN 61, either undoped or doped with chromium 3+, which we published in 2006, enjoys also a real phase transition. This real phase transition is characterized by critical phenomena. We have measured the specific heat, which is here. We have measured the susceptibility versus temperature, which is here, and the optical second harmonic, which reflects the order parameter. That means the bulk polarization instead of magnetization in a magnet. That is this curve. All these phenomena need long waiting times to get approximately equilibrium values. Here we have fitted the specific heat with an alpha close to 0, minus 0.023. And here we have measured, after very long waiting times, the asymptotic criticality with the gamma exponent 1.85. And here the order parameter with 0.13. And well, wait a minute. Yeah, we tested the so-called scaling law of critical exponents. And in static scaling theory, it is the rule, which you might know from lectures on critical phenomena, the sum of alpha plus 2 beta and plus gamma should give 2. We are close to that, 2.09. And what is really expected are the values 0 in the specific heat, 1/8, 0.125 in the beta value, and 1.75. And what is behind these rules is that theory of random field systems, three-dimensional random field Ising magnets or ferroelectrics, which is thermodynamically the same, should be like a 2D Ising material, 2D Ising. Here I have written the to be expected exponents, and the results are pretty close. That's one of the few examples of this rule, which was predicted by Dave Bellinger and Peter Young some 30 years ago, and we were happy to see these results. Okay, this was my talk. What did I tell you? Domain walls in ferromagnetic multilayers, cobalt, iron, alumina, platinum, cobalt, platinum, related ferroelectric crystal, periodically poled potassium titanyl phosphate, and then the persistent random field pinned nanoregions in relaxo ferroelectrics, a specific case in the high disorder field. Here are two reviews which you might also visit, and in particular you should visit, last not least, our topical review of Subhankar and me, which is now more than 10 years ago, when we got this photo when we visited Berkeley labs in 2005, and one data 500 downloads within 4 weeks, 1,000 times or more cited within 12 years. That's really a record. Congratulations to Subhankar Vedanta, our host at this meeting, and thank you for your kind attention. Enjoy the meeting. I'm enjoying also. I got to say what I wanted to say. Thank you. Yeah, the collaborators in the last 20 years on this material. So where are we? Can you hear me?
Yes, we can hear you.
Okay. I stop this presentation.
Professor, maybe we can take just one quick question with delay. So thank you so much, Professor Kliman. Professor Giri, maybe you can ask for one or two questions.
We can have, I invite the one quick questions. So is there any question from the audience?
Seems not.
Okay.
Okay.
I was over time, sorry.
If there is.
Orfman, can you please stop sharing your screen?
Yeah.
Can you hear me?
Yes, we can hear you. Orfman, can you please stop sharing your screen?
So let us move. So if there is no question, let us move to the next speaker. Next speaker is Professor Anjan Burman.
Professor Giri, let Professor Kliman stop sharing his screen.
Can you hear?
Yes, we can hear you.
Yeah.
Professor Kliman, can you please stop sharing your screen?
Professor Kliman, can you?
I don't know. Puspendra, can we from our side stop sharing his screen? Olguang, you are mute.
Now you will hear me.
Yes, yes.
Yeah, but I cannot stop.
On top, now you have stopped it. Okay.
Oh yeah, thank you.
Thank you. So
Sorry.
I will quickly share my screen, Professor Giri, and we just need to, quickly present our.
Professor Clement, can you please stop sharing your?
Yes, he has stopped. Okay, he has stopped. Professor Giri, can you see my screen?
Yeah, your screen is visible.
But I think Saurabh's voice is. I cannot
His
hear.
Connection maybe is not.
Yeah. Okay.
Network
So
connection.
I think without losing time, I like to express my sincere thanks to Professor Clement for his lecture. Professor, the session chair should present this memento, but I take this opportunity. So, Symposium on Magnetism Spintronics takes immense pleasure in presenting this plaque to Professor Clement from University of Duisburg-Essen as an invited speaker for his lecture on universal domain wall dynamics in disordered ferroic material. So, thank you so much on behalf of everyone. And Professor Borman, you can share your screen. I think Saurabh Giri, we lost him, didn't we, right now?
Yeah, can you enable me, allow me to share my screen?
Yeah, so Puspendra, can you make Professor Borman as a co-host?
Okay, thank you. Hope it is visible.
Okay, so he has some internet issue. It's unfortunate.
So yeah, can I go ahead then?
Just a second, I have to introduce you. That's the problem with.
Just say one or two sentences. Don't delay. No issue.
Isita, can you send me that email? Okay, we all know Professor Borman works on this magnetism and spintronics, and mostly on magnonics. So he is very famous working on time resolved MOC and BLS. So I think everybody knows him. So I am sorry, I don't have the CD right now. So I think we can start without losing time. I request you to start your lecture, Professor Borman. Thank you.
Thank you. Okay, so thanks to Professor Vedanta and all the organizers for inviting me. Today I'm going to talk about emergent phenomena in nanoscale magnonics. So just to give a quick overview of the research activities of my group in the SMS Center, we have been working in different topics these days, starting from ultrafast demagnetization, damping, and so on, and then magnonics, magnonic crystals. More recently, we have moved into interface engineering in magnetic heterostructures, spin orbit effects, pure spin current, DMI, spin wave non-reciprocity, topological objects and spin textures, artificial spin ice, new materials like oyster alloy, 2D material spintronics, hybrid magnonics, terahertz dynamics, topological materials, and so on. And we have indigenously developed some of the techniques: time resolved MOC microscope, optical pump-probe spectroscopy, broadband FMR, spin torque FMR, conventional microfocus BLS, and so on. Today I'm going to focus more on the hybrid magnonics thing that I have not talked much in recent talks. So as you know, the world of spintronics have been moving, and the conventional spintronics that we are aware of is now being aided by new phenomena and sort of technology like all optical writing, spin torque and spin orbit torque devices like SOTM RAM, magnonics, magnon transistor and various magnonic devices, atomic spin based logic, and new topic like Skyrmion Hall effects, and so on. And in the middle, The conventional spintronics is also making progress. And what is magnonics? Magnonics deal with spin waves, and spin waves are collective excitations of spins in a magnetic medium. And magnonics deals with the propagation of spin waves or magnon through periodically modulated magnetic media, and that opens up magnonic band structure and band gap, just like semiconductors or photonic band structure and so on. And the important thing is that the magnonic band structure and band gaps, they fall in the gigahertz and sub-terahertz frequency, which is very useful for on-chip data transfer, logic, and various other devices. And here you can see the magnonic band structure for a typical magnonic crystal. And it all started in 1996 when Vazuer et al. Actually proposed this. And beyond that, many work came up. And most importantly, in 2001, Nikita et al. Actually coined the term magnon crystal or magnonic crystal, and a flurry of research in its fundamental and applications were made. And beyond that is only rise and rise of magnonics. And you can see here some typical development. I already showed you magnon transistor. Here is a device actually, and you have magnon holographic memory, logic devices, directional coupler. There are many more. I'm only showing few of them due to the lack of space and time. And new phenomena like skyrmion dynamics driven by magnon, spin wave non-reciprocity, voltage control, magnetic anisotropy, and so on. And in 2021, we wrote a magnonics roadmap in JPCM where we showed that how magnonics have evolved during these last 2.5 decades. And you can see that the conventional magnonic properties like propagating spin waves, magnon, Bose-Einstein condensation, magnonic crystal, etc., are now being aided by various new phenomena. As I said, the spin orbit effects, antiferromagnetism, topological materials, topological objects, sort of VCMA, DMI, strain, and ultimately leading towards new devices like spin wave filters, waveguides, interferometer, directional coupler, logic, and so on. So a multifunctional magnonic device will look like that, where you have the excitation, active medium, and the detection will all have different phenomena, and they are coupled, and they will actually lead towards a very efficient device in future. And one of those is phenomena is, of course, the hybrid magnonics that I have been talking. And here you can see this review article very nicely sort of documented the hybrid magnonics, where you can see the coupling of magnon with phonon, magnon, photon, and superconducting qubits and various other quasi-particles lead towards hybrid magnonics, given coherent transduction, coherent information processing, all on chip architecture, and so on. And because of that, today I have tried to talk about some of the sort of development we have made in our group in hybrid magnonics. And of course, the spin waves, as I said, is collective excitation of precessional magnetization dynamics, and this precession is governed by this well-known Landau-Lipschitz-Gilbert equation given by this famous Landau and Lipschitz, and given by the two torque term, the precessional torque and the damping torque. And this, of course, is more complicated than it looks, because the effective magnetic field has all these fields which are both space and time dependent, and you can sort of conceptualize this in terms of a spatially varying magnetization multiplied by a plane wave is going to give you the spin wave, and also the uniform eigenmode of the system can be written like that. Of course, the spin wave can have two different regimes: the exchange coupled regime and the dipolar coupled regime. In the exchange regime, the dispersion is like that, and in the long wavelength region or regime, you have a k-square like isotropic dispersion, whereas sort of the dipolar coupled regime has a strong anisotropy. As you can see, the dispersion is very different for different orientation of the wave vector with magnetization, and you have different types of spin waves like magnetostatic surface wave and two types of volume waves given by these dispersion relations. So the first thing that I will talk today is the hybrid magnetodynamical modes in two-phased multiferroic nanomagnets, or the magnetic straintronics. As you know, that strain has been recently given as an efficient way to switch the magnetization in some of these papers, and which shows that the energy consumption is only 1 attojoule for Spintronics switching, which is much better than even the spin orbit torque. And switching time is more than nanosecond, which gives us hope for going towards the non-von Neumann kind of computing. And what strain can do to magnetization dynamics is like that, because it can use this inverse magnetostriction or the Villary effect, where if you grow a magnetostrictive layer, magnetic layer on a piezoelectric layer, so in presence of an electric field, you have this, the strain amplitude can be written like that, where D33 is the piezoelectric coefficient, and the stress will be sigma equals to the Young's modulus times the strain. And then the magnetic anisotropy originating from the Villary effect will be given by 3/2 chi sigma. So that gives you a periodically modulating anisotropy, and it can modulate the precision. So what we did in our case, instead of applying a physical strain by a DC voltage or a pressure, we actually use the electric field of a laser. So we grew nanomagnets on piezoelectric layer, and we applied the laser field, and the electric field of the laser periodically reconfigured the charge distribution of the piezoelectric substrate. And that caused a periodic strain due to this D33 and D31 coupling, and that generates surface acoustic wave. And this surface acoustic wave will propagate through the substrate, and that will periodically expand and contract the magnetostrictive nanomagnet, and that will change its magnetization due to the inverse magnetostriction or the Villary effect, and that will give a periodic anisotropy that will modulate the frequency. And this combined effect is reported for the first time in this paper by Sucheta Mondal et al. What we did is we measured this by using a time-resolved magneto-optical car microscope based on a 2-color optical pump probe technique coupled with a microscope, where the pump and probe collinearly focus on the sample like that. And this is some overview of the experimental setup. So the details are like that. The samples are like that. They are grown by E-beam lithography and E-beam evaporation. They are of the almost semicircular, slightly elliptical, with 190 and 186 nanometer major and minor axis, and they are separated by about a micron. So when the pump and probe are sort of focused on a single dot, they are looking like that. So they are far apart, so only a single nanomagnets are being pumped and probed, and the surface acoustic wave generated are shown from the reflectivity, time resolved reflectivity data, which gives us actually these harmonics of 2 gigahertz, so 2, 8, and 16 gigahertz. And if you calculate the velocity of SAW in the substrate PM&PT is 2000 meter per second, we get from the frequency a pitch of 1 micron. So this is definitely the surface acoustic wave. Now what it does to the hybrid the magnetodynamics is like that. So in absence of this surface acoustic wave, the dynamics should be like that. So it has the edge mode and the center mode. The edge mode is dominant should be in this case. But when we have the strain, the surface acoustic wave, then we in addition we get a lower frequency and higher frequency sideband, and the center mode is almost sort of diminished. And as a function of field, you can see this all these modes change their frequencies, and you can see the sort of the trajectory of this magnetization is slightly different from for different field. This is because the phase between the magnetic and the surface acoustic wave is different. And now what we can do is we can write the anisotropy in terms of the two harmonics F1 and F2, and see what can be done. We then did the micromagnetic simulation by introducing this harmonic sort of anisotropy with the F1 and F2, where K0 is given by 3/2 chi sigma, as we already shown from the Villary effect. And we are able to actually reproduce this. This is a simulated spectra, which also showed the sidebands, and these dotted line are the simulated spectra, frequencies, and the symbols are the experimental frequencies. Frequency doesn't change with pump fluence, and we have been able to reproduce it. And these are the frequencies, and what we got is the sort of K0 is 22,500 joule per meter cube, and these are the known parameters for PM and PT. And we got a strain of 0.18%, and the electric field of the laser is coming out to be 6.4 times 10 to the 5 volt per meter, which is exactly what we are actually using in the laser. So then what the simulated modes look like, these are the simulated magnetic modes of the spin wave mode without strain. So this is the center mode and edge mode. But when we are applying the surface acoustic wave, these are the power and phase, and this is the phase of the, sort of the magnetic, purely magnetic mode. And these are the hybrid modes at different fields. And you can see they are completely different from the normal spin wave mode. And they are having various kind of quantization and even azimuthal quantization here. And they are changing because the magnetic, sort of the phase between the surface acoustic wave and the, magnetic mode are changing with field. And as a result, the hybrid modes are giving very different, feature. So with that, I will now discuss the resonant amplification of intrinsic magnon mode and generation of new extrinsic mode in a two-dimensional array of interacting multiferroic nanomagnets by surface acoustic wave. So here what we show that it's a bias field free SAW-driven magnonics. Here we have, sort of these semi-elliptical nanomagnets, which are again cobalt and deposited on, sort of lithium niobate substrate. And this is also piezoelectric, and they are now very close together so that they have a collective mode even in absence of any bias magnetic field. So this is why we call it a bias field free magnonics. And even if we do not apply a magnetic field, we get a very nice, precision in this. And this is the time resolved reflectivity, which also shows the surface acoustic wave here. These are the major and minor hysteresis loop of the sample, and these are the geometry. So this is the, so sample, the electrodes are given here. So the SAW can propagate like that. We can also have electrode in the other direction. So we can see the anisotropy in the SAW-driven mode. And before that, I just wanted to say that recently, more recently, we actually developed extreme sub-wavelength magnetoelastic antenna implemented by this, based on this sample only. Okay, so here we can see that, the Fourier transform shows that we have 4 different modes, 3, 4, 7, and 10 gigahertz, and they come both in the reflectivity and, car rotation because they are the hybrid modes. And these are the power and phase. And you can see that, the phase power is rather weak, and the phase is a little bit sort of skewed, not very coherent. But let's see what happens when we drive this by surface acoustic mode. So whatever SAW you see here is only from the laser electric field driven. Now we apply a real surface acoustic wave by, sort of RF generator and through electrode. And now we try to drive them. And now this time SAW is propagating along the major axis of the nanomagnets. And now these are the experimental data. And these are driven by SAW frequencies from 1 gigahertz to 10 gigahertz. And you can see that we can, sort of generate new mode at 1 gigahertz, which were not there. In 3 gigahertz, we are amplifying this mode to very high value, like all other modes are diminished. 4 gigahertz, again, this mode is amplified, other modes are diminished. At 6 gigahertz, a new mode appears here, other modes are there. 7 gigahertz, the mode is amplified, and sort of 8 and 10 gigahertz, these modes are new mode generated and amplified. So the amplification of the existing modes are by a factor of 4 to 7, whereas new modes are generating, and sometimes they are actually, sort of, shrouding or, sort of dominating the existing magnetic modes. And these are sort of the modes after, sort of SAW, sort of boosting. And you can see that the power is now, pretty high, and the modes are very sharp. The phase is very sharp now. So it shows that the modes are now, sort of amplified or, sort of driven by the surface acoustic mode. And remember that only 4.5% or only 4.5 microwatt of the power was actually coupled to the sample. So if we can couple more power, it will be even better. And here, these are done by stress field calculation with in the micromagnetic simulation. And when the SAW is propagating along the minor axis of the nanomagnet, we see a completely different phenomena. Here, these are the time resolved data, and here you can see that now only the driven modes are there. Even in the experiment, the driven modes are dominant apart from this mode. whereas the other modes are completely, sort of extinguished. And this is particularly because of this, from the, magnetic field distribution, we can show that this is because of the magnetic field along this direction is much less. So here, the magnetostatic interaction is much less. And as a result, so SAW is playing a major role here. And these are the power and phase distribution for this particular geometry. So anisotropy in this inter-element dipolar interaction makes this straw-driven magnetoelastic mode very different along two different directions. So now we go to the third problem, like strong magnon-magnon coupling and nonlinear FMR shift in ferromagnetic nanostructure. There we used a ferromagnetic home-built ferromagnetic resonance setup with a home-built probe station like that. And you can get more details from this paper. And here the sample is sitting here, and we are using a coplanar waveguide. And what we are using is ferromagnetic nanocross structures. These are made of permalloy, nickel iron. And these nanocross structures are made by E-beam lithography, and they have different kinds of dimensions from 300 nanometer to, they are all like having same separation, but it's going from 200 nanometer to 600 nanometer. And you can see that the real part of the S11 shows these ferromagnetic resonance peaks. And these are like, this is the surface plots, which are made of by stacking a number of such spectra. And this is for a thin film, which shows a purely Kittel-like behavior, single mode. And these are from the nanocross and with varying dimensions. And you can, the major feature you can see here, there is a dip here, which is because of a mode softening behavior. And here you see some, anti-crossing like behavior that we will describe later. And there are further features, very interesting features that we have already discussed in these two papers. So what we are going to do here is now drive this by microwave power and see what is happening. Now, in a hybrid system, quantum states are coherently transferred from one medium to another using different carriers, like I said, like superconducting qubits, photons, phonons. And magnon-magnon interaction has been achieved in thin films, large magnetic microstructures with a coupling strength, which is given by G0 times square root of n, where G0 is a coupling strength between individual spin and n is the number of spins. So naturally, in order to get a large coupling, you need to have a large number of spin. And that is why obtaining strong coupling in nanoscale magnetic system is non-trivial. But what we did here is, in case of ferromagnetic nanocross structure, dynamic dipolar interaction induced strong coupling or magnon-magnon coupling. So this is the sort of result with variation of microwave power. This is at minus 15 dBm. This is for plus 4 dBm. So two things one should notice is that this mode here is now having a single mode behavior when you have a minus 15 dBm. But when we apply a plus 4 dBm, then you see there is a splitting. And if you zoom on it, you see there is kind of an anti-crossing like behavior here. And this mode, which is at around, sort of 6 or 7 gigahertz, is showing a pure anti-crossing, even without even at a very small microwave power, which is only increasing with the microwave power. And these are the, sort of spectra, which shows that this 2G is the, separation between these, and K1 and K2 are the line width of these peaks. And from here, we can calculate the cooperativity, and let's see what happens. And another thing is that we will show you the nonlinear ferromagnetic resonance shift at the same frequency, but from two different branches of this magnon modes. Okay, so these are like highlighting the magnon-magnon coupling. And here we show the sort of this splitting due to magnon-magnon coupling as a function of power. And you can clearly see that we actually open up the magnon-magnon coupling with increasing power. So the splitting actually opens up and then increases. And these are the simulated data which actually reproduce it. And these are the G value for the experimental and simulated case. The cooperativity is given by G square over K square. But G I have already shown. K is actually K1 and K2, which are the sort of line width of the two modes, half width at half maximum. So the first anti-crossing, it is G is tunable by microwave power. And for the first anti-crossing, the cooperativity is 0.28, which is not a very strong coupling, intermediate coupling. But the second anti-crossing is C is coming up to 0.6, which is actually entering into the strong coupling regime. And this is a nonlinear FMR shift. So these two modes, as I showed you, in one case, actually the mode frequency increases with the microwave power. In the other case, it actually decreases. And when we plot them as a function of power, you can see they enter into nonlinear regime. These have quadratic components, and that is why we call them nonlinear regime. So then we did some simulation in order to underpin the magnon-magnon coupling. For that, we use a RF field, which is given by that. And this power of microwave is converted to this amplitude of the RF field. So it's actually the correct value of the RF field. And what we see is that from this the magnetic field distribution, you can see the magnetic field lines and so on. They are getting stronger, and it's getting deeper. So as the microwave power increases, the dynamic dipolar coupling interactions between these nanopores increases, which boosts the magnon-magnon coupling. And you can see that with increasing power, the modes are becoming nonlinear, and that is why they're becoming more incoherent. So here, minus 15 dBm, we clearly see a mixed backward volume De-Monash-Beck-like behavior with n and m equals to 7 and 3, and there they become very incoherent. So the good thing is that we can show the coherent propagation of this coupled mode. So this is an uncoupled mode, only single mode, and when you excite it, you see it doesn't really propagate through the array. But the coupled modes, both of them, when you excite them locally, you can see they are propagating pretty well through the whole array, which shows that they are coherently propagating. So this is one of is important for the coherent information processing. So the last problem that I wanted to discuss is the voltage control on-demand magnetic nanochannels based on VCMA. We all know that the VCMA appears due to in ferromagnet insulator interface due to relative changes of electron occupation in the 3d orbital of the ferromagnet and the 2p orbital of the oxygen. And as a result, the outer plane orbital of FM is strongly bonded with 2pz orbital of the oxygen. This causes a charge transfer from 3z to 2pz orbital. And if you apply electric field, you can actually change this charge distribution. And as a result, you can change the anisotropy, giving rise to a voltage control anisotropy, which is given like that. Beta is the VCMA coefficient. And recently, we actually developed electric field control spin waves in ultra-thin coffee bead film. And now we extend this idea to develop a magnetic nanochannel. So this is the sample geometry. The anomalous Hall effect measurement shows this sample is in-plane magnetized. And here we have an ITO electrode because we want to do optical measurement. And this top ITO electrode and bottom gold electrode will be used for applying the electric field. And here the cobalt iron boron and MgO-Al2,3 are the sample. And when we do not pattern the the sample, we see that there is only a shift in the resonant frequency of the spin wave mode with the voltage application of voltage because of the VCMA. But when we did further characterization in order to understand the coupling coefficient, beta value, and so on. And then we actually pattern the ITO by using e-beam lithography. And then we see that when we apply the voltage to this patterned ITO electrode and this gold electrode, then only the region below the ITO, the PMA or the VCMA will occur, whereas when there is no ITO, then no VCMA will occur. This will divide this into two regimes, region 1 and 2, and this will act as two different magnetic material. And that immediately, when we measured the BLS spectra, immediately that splits the mode into two. And that actually changes with the voltage and the wave vector. And this is the frequency versus wave vector behavior, which shows that there is two different bands with a band gap, clear band gap here at V equals to -4 volt. And when we do the plane wave method, and here this blue line is the plane wave method based simulation. And then when we do further simulation, we show that the mode which is 1 is flowing through the red region has maximum amplitude. So mode 1 is flowing through region 1 and mode 2 is flowing through mid region 2. Okay. And we show the reconfigurability by changing the voltage to +4 volt, which actually changes the frequency and the band gap. And also it switches the propagation from 1 to 2. So now mode 1 flows through region 1 and mode 2 flows through region 2. And we did further experiment to show the reconfigurability by patterning the patterning the sample but not applying any gate voltage, by not patterning the sample, and so on, which shows that there are only single mode. So basically, you know, the two modes and the band gap was because of the modes propagating through these and their coupling, magnon-magnon coupling during their propagation. So to summarize, I have shown hybrid magnetoelastic modes in sort of a cobalt nanodot deposited on PMNPT substrate. I have shown resonant amplification and sort of generation of new mode by surface acoustic wave and bias field free magnonics here. I've shown strong magnon-magnon coupling in nanocross structure due to dipolar coupling, and I showed on-demand development of on-demand magnonic crystal or nanochannel by using GCMA. So these are some pictures of my lab. So we have developed indigenously time-resolved microscope, VNA FMR as twin rock FMR, optical pump probe spectroscopy is another amplifier-based lab, and BLS, conventional BLS, micro BLS, terahertz spectroscopy, and so on. So this is the group, and these are the people who have been involved in this: Sucheta Mondol, Anulekha De, Shamiran Choudhury, Kartik Odhikari, Avinash Chaurasia, and Amrit Kumar Mandal. And these are my collaborators who contributed to this work: Professor Otani from Japan, Professor Supriya Bandyopadhyay from Virginia Commonwealth University, USA. These two books, actually, book and book chapter, gives you a lot of background. And very recently, we have written a series of perspective, roadmap, you know, sort of review articles, and so on. This one is just accepted, Magnetic Spintronics in Applied Physics Reviews, and you'll get that soon. So this will give you a lot of background work that I have presented here. Thank you very much.
Thank you very much for the nice talk. Since we are running out of time, so maybe we can have one single question. Actually, I found one question. Do you think we can use the magnon-based detection of skyrmion excitons in antiferromagnetically coupled textures where it is difficult to probe them using conventional imaging technique due to vanishing magnetization?
Yeah, yes, definitely. They can be measured by antiferromagnetic resonance or the corresponding inverse pinhole effect. So those are pretty well known. The bulk measurement will not be able to probe this, but this kind of probes will definitely be able to measure the said excitations.
And one more question is, how much field can we apply in such experiment to achieve different regimes, or the measurements can be performed only at the remnants?
It depends. In some of the measurements, I have shown that like this one, just give me a little bit of time. Yeah, this one measurement is performed at remnants because the sort of interacting field, the sort of magnetic field interaction between them is large enough to have a coherent precision. So that is why we can have this in the bias field free regime, whereas we generally need some hundreds of Oersted, sometime even less than that, to have coherent precision. In some material, we may need a little bit more, maybe of the order of 1 kilo Oersted, 2 kilo Oersted, but not more. We do not need any superconducting magnet or anything. Just simple electromagnet will be good enough. Small electromagnet will be good enough to have these experiments and probably the devices.
Okay. Thank you very much, Professor Barman. So let us thank the speaker again.
Professor Barman, you kindly stop sharing, and I will share my screen. And I request you, Professor Giri, to read the memento for Professor Barman.
Yes.
I think you can see my screen.
Yeah, I can see. So Symposium on Magnetism and Spintronics, Niger, Bhubaneswar, takes immense pleasure in presenting the plaque to Professor Anjan Burman of SN Bose Institute, Kolkata, India. Thank you.
Thank you very much. Thank you.
Yeah, thank you. Now, before we move to the next talk, I have a request to make a conference photo, so to say virtual photo. So I request everyone to switch on their camera and we will take a screenshot and then we can continue. So, Haipeng, your voice, your face is not, yes, okay. Wolfgang, you also not visible clear. Yes, now it is better. Thank you. So I will take some group screenshots. Smile. Okay, there are many, so I have to take. Sakti, do you know how to put all the people in one frame? I don't know. So, okay, look at Stanislas. Okay, some more pictures, some more people. I have to take 5 screenshots though. Okay. Just a second. Okay, so I think we are done. So let's move to the next speaker. Thank you so much, Professor Burman.
Thank you.
So we can switch off our cameras and let's move with the talks. Thank you.
Thank you, Professor Burman.
Thank you so much.
So let us move to the next talk. Next speaker is Professor Atkinson. So it's my pleasure to say a few words about him.
Okay, so I think we are done. So let's move to the next speaker. Thank you so much, Professor Burman.
Thank you.
So we can switch off our cameras and let's move with the talks.
Thank you, Professor Burman. Is there? Okay, so Professor Dale Atkinson is the Sir Gareth Roberts Professor of Applied Physics. At Darwin, he has more than 20 years of research experience in academia and industry, and is working on spintronics, magnetic materials, and thin film semiconductors for flexible electronics and nanocomposite pressure-sensitive inks for sensing applications. Professor Atkinson held a prestigious UK EPSRC Advanced Research Fellowship in Nanoscale Magnetism and Spintronics from 2004 to 2009, and RC UK Fellowship in Nanoscience from 2006 to 2011. He has published over 100 research papers, including work in a very famous journal like Nature Science, Nature Materials, Physical Review Letters, Applied Physics Letters, and had 4 granted patents. In 2000, Professor Dale Atkinson was awarded a prestigious BAE Systems Chairs Gold Award for Innovation. So with this, may I request Professor Atkinson for the beginning of your presentation. Professor Atkinson.
Thank you. Can you see my screen?
Yes, we can see.
Okay, can you see that?
Yes.
Okay, thank you for the kind introduction, Professor Giri. And it's nice to see so many of my friends and colleagues in India. Just referring to Professor Kleeman, it's about 4 degrees here 3 or 4 degrees here in Durham in the northeast of England. So we're not quite so cold as in Germany. Of course, I'm honored to be invited to speak here today at this symposium. And I'd like to talk about this topic of interfacial effects, which of course is critical in spintronic multi-layer systems. And this will be, it's important for many aspects of research within spintronics and also magnetics as well. And it's a very broad subject, so I don't propose to speak on everything today. But what I would like to talk about is the focus on damping, and it's as it relates to spin transport in ferromagnetic thin films and heavy metals. Now, you may well know this topic is actually at least 40 years old, starting with the work of Silsby in the early 1980s. But it was about 20 years ago that significant research began, where the key experiments from a Japanese group of Mizukami, Ando, and Miyazaki, excuse me, and very famous theoretical, those were experimental works, and very famous theoretical developments by Sikovniak, Bratas, and Gerrit Bauer to help explain this increase in the damping when we put a heavy metal on top of a ferromagnetic material. That's now called spin pumping. Everybody will have heard of spin pumping. It's a common term, but 20 years ago, it was only being really introduced and developed for the first time. What I would say is actually in the last 20 years, there's been continued exploration to improve our understanding of damping in these thin film heavy metal systems. And the theory has been generally very good. And people have found other factors that are really critical. And one of those factors that's really critical is the interface. Another factor is actually something which is very fundamental to spintronics. It's the spin diffusion length. We still have huge variations in the value for the spin diffusion length. So today I would like to talk about both what's the correct value of spin diffusion length? Can we extract that from spin pumping? If so, how do we do it? And also, if I put a heavy metal on top of a ferromagnetic material, that heavy metal may become magnetized, it may become proximity polarized. And there's a lot of debate about whether proximity polarization plays any role in spintronic processes, particularly in spin transport. So I'd like to address both of those today, this spin diffusion length and the role of proximity-induced magnetism in spin transport. But of course, first, I just say I'm sorry we're not in person. I've had some wonderful times when I visited India in Delhi, in Calcutta, and in Bhubaneswar and in Jatni. This is my last memory from my visit to India several years ago, and I see some of my friends, including some visitors like Professor Kleeman and Professor Takanashi there. Okay, so back to the science. In this talk, I'd like to thank particularly my PhD student from Durham University, Charles Swindells, and also another student of mine, Richard Rowan Robinson, for the work I'll be discussing. But most of this collaboration is based on the work of Charles Swindell, working with Yong Choi and Dan Haskell at the Argonne National Lab, Tom Hayes, a very close friend and colleague of mine at Warwick, and some really good guys at the Institute for Molecular Physics in Poznan in Poland, Hubert Goinski, Piotr Kuszwik, and Felix Stobiecki. And also Pavel, who is currently on away with, he has a new baby. Okay. So let's get moving. We have the structure for my talk. First of all, I'd like to talk about the interfaces structure in general, how you define, how you think about interface structure, and give you some examples of the results that you'll see throughout this talk. So I use X-ray reflectivity a lot, and we do a lot of fitting and interpretation of X-ray reflectivity. So I'll show you an example of that. Then I'd like to introduce proximity-induced magnetism in heavy metals. What is it? And I'll give you the well-known examples with ferromagnets, but actually there is also some work we've done on rare earth transitional metal ferrimagnets. What happens when you put a heavy metal in contact? Does it follow the ferrite? Does it follow the transition metal or the ferrimagnet or the rare earth? Or does it follow the net magnetization? So we looked at the proximity-induced polarization in those systems. Then I'll get onto the main topic, which is damping and spin transport in these heavy metal systems. So I'll give you a brief introduction. Then I'll ask this, I have these two questions I introduced earlier. Is the spin diffusion length a fixed value for a material? Does it depend on thickness? What is that value? I don't claim I have an answer. The answer, I have an answer. Whether it's the correct answer is for the field to decide over time. And then secondly, does the damping enhancement we see when we put heavy metals on top of or in contact with ferromagnetic materials, does that enhancement, is it affected by any proximity-induced magnetization in the platinum layer? And we have some very new results, which I hope I'll be able to show you and demonstrate that that is actually the case. Okay, so those are the questions. So let's start with this importance of the interface. Of course, if you're looking at the interface, it's really critical because the interfaces in spintronics define and determine the electronic interactions and the hybridizations that give rise to much spintronic phenomena. So those interactions, as we know, give rise to anisotropy. Those interactions give rise to the Dalajinsky-Mariah interaction at those interfaces, and it defines the conduction channels at the interface. So if you've got a spin polarized current or a spin current traveling from a ferromagnet to a heavy metal, or from a heavy metal to a ferromagnet, the conduction channels are determined by that local electronic structure. So understanding the nature of the interface is really critical. Now, many people do this with transmission electron microscopy. It's a very powerful technique, particularly in a very high resolution mode. It provides real space images. So when you look at it, you can usually see directly what you're trying to interpret, and it has excellent spatial resolution. But of course, there are some problems with it. It's difficult to make a quantitative interpretation. It's very time consuming in the sample preparation. The images are really representing an ultra small region. So is that region representative? And that's where it can be challenging. So there's a complementary technique, which is what we use, which is X-ray reflectivity. Many laboratories do X-ray diffraction. If you've got X-ray diffraction kit, you can probably do X-ray reflectivity for structural things. It's a reciprocal space method, and it requires you to extract quantitative information by doing best fitting models. So you simulate the solution to the electron density of your sample. But if you get a good simulation, the electron density, you may not have exactly the right layers, but the electron density distribution will be representative of the result that you get. So here is an example. In this graph here, this data is, the blue data is measured, and this orange line that you see is actually the best fitting simulation. And from that best fitting simulation, what we will extract is something we call the scattering length density. And you can see for this sample here, so here's our silicon dioxide substrate, here's our cobalt iron boron layer, here's a platinum layer. In this case, we were looking at spin current tunneling through silicon dioxide, but the important point to look at here is you can see clearly the uniform density of the cobalt iron layer. You can see the density here of the platinum layer is much higher, but you have these regions in between. These are the interfaces. So these interfaces have a finite width. So when you're thinking about thin film structures, you should not be thinking, okay, these are nice, simple parallel plates sat one on top of the other. There will be some topographical roughness. There will be some intermixing between these layers as well. So it's really critical to understand what you're dealing with and not to think of it in simple parallel plate terms, okay? So that's all I wanted to say about that. You'll see that coming back later on when I show many examples of scattering length density. I'll also be showing some magnetic examples as well. So in introduction to proximity induced magnetism. So if we think about a system like this, here's cobalt, and here's our ferromagnet. Actually, for metals like palladium and very famously platinum, if you put these metals in intimate proximity to a ferromagnetic metal, then actually, because they're close to the Stoner criteria for ferromagnetism, they actually become magnetized. So you can induce a magnetic moment in them. And this is associated with hybridization. So in the case of platinum and cobalt, it's 3D, 5D hybridization, and it's intimately connected with the electronic structure around the interface. So if you have that electronic structure suitable, then you will see a proximity magnetization. And this is interesting in itself, just from a physics point of view, but it has potential implications for spin transport as well. There is a variety of evidence for and against its role in spin transport. Okay. Now we can actually measure the proximity induced magnetism in these heavy metals using energy specific X-ray methods. So specifically, we can use X-ray circular dichroism. And this example I'm showing you here is actually X-ray circuit dichroism for cobalt. But actually, if you tune to the platinum edge, you can see the magnetic moment in the platinum itself. So there will be a moment in the cobalt, but you're not interrogating that. If you are using magnetometry, like a squid, you would be looking at the total moment. If you use resonant X-rays for XMCD, you can look at this specific element. The physics is relatively well known. You have left circularly polarized light and right circularly polarized light, and you get different amounts of, you get different populations at the Fermi surface. And from this, it means you get different levels of absorption depending on the magnetization state or the helicity of the particular light. I don't want to talk any more in detail about that. I just want to show you an example. So this is our iconic platinum cobalt platinum system. This is X-ray reflectivity. You saw this before, but actually this time we're running it at the platinum edge. So what that means is that we're actually tuned to the platinum energy, and then we can flip the helicity. When we flip the helicity, this reflectivity changes a very small amount. But if we look at the difference, this asymmetry factor here, this is a magnetic signal that you're seeing here. And actually there's two curves on here, there's blue one and black sets of data. If you just look at the black one, for example, this is the magnetic signal that we get from this platinum in this case. And if we make a simulation of this, which takes into account the magnetic moment, we can actually use this to look at where the magnetization is taking place within the platinum. And that's as an example here. So what you can see in this simple schematic is here is a bottom platinum, here is the top platinum, and here is the cobalt. The black line you see here, this is the scattering length density. This is the profile of the structural profile of the material. So here is the interface between the cobalt and the platinum. It looks very broad, but it's not really. We're on an angstrom scale here. The red line that you see is the magnetic scattering length density. So this is actually the magnetic signal coming from the platinum, and here's the magnetic signal coming from the platinum. And you may immediately say, okay, but I see it's overlapping with the cobalt. Yes, it is, because actually there's some intermixing at that interface. And wherever you have some intermixing, there's a possibility of cobalt in contact with platinum, and that can give you this proximity polarization. So that's proximity polarization. I'll be referring back to that later. But I just want to give you one example of proximity polarization. Most people have studied this in the ferromagnetic transition metals, cobalt, iron, boron, alloys, etc. You can also look at it in, people have looked at it also in the oxide ferromagnets. We decided to look at it in the metallic rare earth transition metal ferromagnets, because in those systems you have this magnetic compensation. And also you have a bulk perpendicular magnetic anisotropy. So these rare earth transition metal alloys are really very interesting from a spintronics point of view. By changing the composition or by changing the temperature, you can sweep through the magnetization compensation, and that's where you get some interesting physics happening, which may have some beneficial applications in spintronics. So the question that we had was actually, if you have a system like this, so your rare earth, it's a ferrimagnet, so the rare earth and the transition metal are effectively pointing in opposite directions, and you get hysteresis loops that look something like this. In some cases, the magnetization will increase, and in other cases, the magnetization will decrease as you change the temperature. This is a compensation point you see here in this particular one. This is a cobalt gadolinium sample. You can see the compensation here. But the question I wanted to ask is, with regards to proximity-induced magnetism, is the magnetization pointing this way in the platinum, or is the magnetization pointing this way? So which way is the platinum? Is it following the transition metal? Is it following the rare earth? Or is it following the net magnetization? So will it change when we go through compensation? So this is what the results look like. Here is we tuned to the platinum edge. Actually, we also tuned to the gadolinium edge and looked at the moment in the gadolinium. So we have a moment in platinum and in the alloy. And what you see here is, this is the asymmetry ratio. This is the magnetic signal that we see for our two alloys. We have a cobalt gadolinium alloy and a cobalt iron gadolinium alloy. And what we see when we look at this, when we do the analysis, we see that for the cobalt iron alloy, in this case, the transition metal is dominating. The gadolinium is a smaller moment. The platinum magnetization is following the cobalt iron. It's pointing in the direction of the net magnetization as well. Now, in the other situation, in this case, it's a cobalt gadolinium alloy at low temperature here. The gadolinium is dominant. So the magnetization is pointing in the direction of the gadolinium. But if you look at this moment in the platinum, the moment in the platinum is still following the direction of the cobalt. So what we can say here is that the proximity-induced moment in rare earth transition metal alloys is typically aligned with the transition metal, not with the gadolinium. The physics of the exchange associated with this is quite complicated, but it probably can be explained going all the way back to some theory from the early 1970s. Okay, so moving on, I just wanted to say also we can control the proximity polarization, and we can do that by adding a spacer layer. So in this case, we added gold or iridium. Gold and iridium may have a small proximity polarization, but that moment would be much smaller than in platinum. And also gold and iridium are heavy metals as well, so they're a good choice because of that. Here is some of the results that you're getting experience with now. You can see the reflectivity data, and you can see the reflectivity data here, and the black lines of their best fitting simulation. So we can fit this very well. And again, you can see the magnetic signatures coming from that. If we look at this scattering length density, so there's no spacer layer here. If we look here, you have a big spacer layer. And what you see is, if there's no spacer layer, we have a big moment. When we introduce a spacer layer here, a very small one, this moment goes down, then the moment comes down a lot. And then when we have a very large spacer layer, we get no moment at all. So if you separate the platinum completely from the cobalt, then you will lose the such, you will lose any proximity-induced magnetization. And you see, in fact, the magnetization drops very quickly as a function of the spacer layer. So within 1 nanometer, typically, there's no magnetization associated with that interface. Okay, right. So that's proximity polarization explained. Let's move on and talk about damping and spin pumping in heavy metal systems. This is well established, so I'll just briefly introduce it before going on to answer some of the questions I said at the beginning. This is a famous result. We replotted it. This is from Mizukami, Ando, and Miyazaki. And what they saw is, for a given reciprocal thickness of a ferromagnet, in this case nickel iron, when you have platinum or palladium, you get a huge increase in the damping. You get a large linear increase in the damping if you have an increasingly thin ferromagnetic layer. And basically, the simple interpretation of that is your total damping is the intrinsic damping of the ferromagnet plus some additional term associated with the interface. And this is where all of the interest and excitement came from, because this allows you to control the damping. If you can control the thickness of your ferromagnet and the non-magnetic layer, you can control the damping, and you can create interesting systems because of that. So it's a bulk and an interface term. This can be understood in quantum electronic terms, in terms of basically you need a spin orbit coupling, etc. So it could be simply coupling at the interface, and if you have coupling at the interface, so this is a very nice paper by a group in Poland and the UK, and this is the damping parameter. This is they have some cobalt, and they're putting different magnetic non-magnetic layers on the top, and you can see in this case this is platinum. If you put platinum on top, even a few nanometers of platinum will lead to a very large increase in the damping in this system. And it's largely because of hybridization, electronic hybridization and exchange, and spin orbit coupling. You've got a much larger spin orbit coupling from the heavy metal, and that's what gives you the damping. That's one explanation. Of course, and it's probably part of the real explanation. Of course, there is spin pumping. Spin pumping theory was developed to explain those early results I showed you. If you have a precessing ferromagnet, you create a potential at this interface, and that potential drives the spin current. And if you have no platinum at the interface, then you get some damping that looks like this. And if you have platinum at the interface, you see much heavier damping. So this is acting as an additional channel of loss. This was developed by Sokovniak and his colleagues in terms of the spin current flowing. The spin current that flows from here, that spin current flows and is absorbed. And if you look, you see this is a spin current. The term in the spin current looks like a term in the Landau-Lifshitz-Gilbert equation. So we can understand that it's effectively an additional contribution to the damping. And it's defined by the thickness, 1 over the thickness of the ferromagnetic layer, and by this spin mixing conductance here, G effective. The spin mixing conductance is a kind of catch-all term, and that's one of the things that has really been discovered and understood better over the last 20 years since it was first reported. And the interface itself is really critical. But in this case, what you're also looking at is the absorbance of that spin current. So the spin diffusion length of the non-magnetic metal is really critical. So this alpha is determining here on 1 over F. So I showed you that, that's the relationship I just showed you. If we look in more detail at the spin mixing conductance, it depends on the thickness of the non-magnetic layer as well. And it depends on a couple of things. It depends on this spin flip probability, epsilon here, but it depends on the spin diffusion length. And that's where we have a lot of interesting questions and queries from the spin diffusion length, interface, short spin flip probability as well, as I mentioned. So the question is the spin diffusion length a single value? Well, actually, if you look in the literature, there are really big names who have measured the spin diffusion length, for example, in platinum, and they come up with value of 11 plus or minus 3, so something up to 12, 13, 14 nanometers for the spin diffusion length of platinum. Other groups have looked by other methods, by the spin pumping in particular, and they get values of 1.2 nanometers. These are recent papers, and we still have a massive discrepancy in the value. We have more than an order of magnitude, or of about an order of magnitude difference. So what is the true value? And is spin pumping, is it giving us the correct value? That's the question I want to ask. And actually, is the spin pumping uniform? Maybe not. There's a suggestion from Bob Berman's group that actually it's the spin diffusion length times by the resistivity, which is constant. So we looked at this and we said, okay, let's make the spin diffusion length thickness dependent. And we use the thickness dependence of this form here. And what we actually showed was that we come up with the same form for the spin mixing conductance, but now you can see the spin diffusion length becomes thickness dependent here. So we have a thickness dependent spin diffusion length. When you get to the infinite regime, you get to the real value. But in the ultra thin film regime, the spin diffusion length is thickness dependent. So this is what the resistivity. This is how we might measure a system like this. This is measuring the magnetization damping. We're using FMR. We can fit the real and imaginary components, and we can look at the line width as a function of frequency. Now, this line width is actually here, delta H, has an extrinsic component which is associated with defects and other systems that create additional forms of damping. The intrinsic damping of the material alpha is encapsulated with this term here. Now, if we just look at this expression we had before for alpha total, actually what you can see is that delta alpha is proportional. We don't need to know what gamma is, and we don't need to know what M effective is. If we're doing fitting, gamma and M effective are two correlated fitting parameters. So if we can avoid having to work out what gamma is, so actually in our work, what we do is we say that we use this parameter 4 pi delta alpha over gamma as that's what we measure. We can extract that easily from a measurement. We don't need to make an approximation for delta alpha because it depends on M effective, which we may not know. And if you measure it with the squid, is it right, or does it take into account something from the platinum proximity? So we used that analysis and we made some fitting, and all of the data is fitted at the same time. There's an example here. This is platinum cobalt or cobalt platinum, two different systems. We changed the thickness of the platinum, but we also changed the thickness of the ferromagnetic layer. You need to do both. You can't just put a single thickness for the non-magnetic layer. You have to do, for a detailed fitting, you need to change the thickness of the ferromagnet and you need to change the thickness of the non-magnetic layer. If you do it and you fit simultaneously, you can see our fits, the quality is generally very good. And we've assumed some thickness dependence for the spin diffusion length based following a model for the thickness dependence of the resistivity. So the thickness dependence of our spin diffusion length is similar to the thickness dependence of the resistivity. And we do it for different materials, different interfaces, but the results largely come out to be the same. So let me just go through this. If we use a constant spin diffusion length model from Sokovniak for platinum cobalt interface, we get a value of about 1.6. So this agrees with the work of Hoffman, etc. But we think this may not be correct because it's not taking into account the thickness dependence of the spin diffusion length. If we take that into account, what we find is that the infinite thickness dependence of the spin diffusion length gives us a value in this case of about 9.5 nanometers. In the case of, in this particular case, we obtained a value of about 6.6. So we don't have great consistency, but we have a much higher value for the spin diffusion length of platinum here. In ruthenium, we get a sensible value for the spin diffusion length of ruthenium of about 22. So this method seems to be appropriate and seems to work. So I would say we have reasonable grounds to say the spin diffusion length is thickness dependent. Now, the final thing I wanted to say is we've not taken into account anything special about the interface, and it's known that there is additional spin memory loss at the interface, and the spin overcoupling at the interface is certainly having some interesting impact. So there's some spin current diffusion from which we can get the spin diffusion length, but there's also things happening at the interface, and that's not taken into account here. But that's what I want to try and look at now, one aspect of it in particular. There's a lot of interest in whether the polarization of platinum has any impact on magnetotransport. Many papers say no, some papers say yes, some papers say no, some papers say no. So there's yes and no, depending on the system that people measure. There's a disagreement about whether you really get any impact on the damping and the spin diffusion length, the damping and the spin pumping, depending upon the proximity polarization of the platinum. So we made some samples. We had two different magnetic systems with a gold spacer layer. So and we made proximity-induced magnetization measurements, and we made FMR measurements on the same samples. And you have 7 nanometers of magnetic material. We have a gold wedge here, so it goes from nothing to a thick gold spacer layer, and then 4 nanometers. So here we have good proximity. Here we should have no proximity polarization. This is the scattering length density. This is the SIMS information showing you the structure. So we know the structure very well. And if you look with the FMR, we measured in several places like this. Here's an example of the result I showed you earlier. And this is what we get. For the nickel ion system, we see the magnetization drop, the damping drops down with gold thickness. In the cobalt ion system, we get a similar behavior. It's dropping down. The nickel ion system is more complicated because actually some nickel is diffusing into the platinum, which gives us an offset. But basically what you see is it drops down, then goes to a plateau. In this case, it drops down and goes to a plateau. And it goes down towards the natural cobalt ion thin film value. So from this, we can extract the damping as a function of the gold spacer layer thickness. We also did proximity polarization using circular dichroism along the same samples. And this is what we see. This line here is an example of a platinum proximity polarization. It's dropping as a function of gold spacer layer. We also measured gold, interestingly, and the gold goes up, and I don't really have time to talk about the gold. The gold goes, so there is a moment in the gold, but the gold does not seem to contribute significantly to the spin pumping or the spin absorption. We also plotted some hysteresis loops. This is a platinum hysteresis loop, which is following the magnetization of the cobalt ion in this case. But from this, we can extract the XMCD as a function of thickness. So we can end up with plotting this graph, which is the damping, alpha, and this is the PIM, the proximity signal. And what you see is as the proximity magnetization is falling, the damping is falling, and it looks like if you extrapolate, it's going to be falling to approximately the value with no with no proximity polarization in the case of nickel ion. And similarly, we see the proximity polarization is falling, and the damping is also falling back towards the value for the intrinsic cobalt ion alloy. So there's a strong indication here that the spin pumping is correlated with the magnitude of the proximity induced magnetization. is a direct comparison. We put a straight line through there as a guide to the eye. It's a strong dependence. It's probably not linear, but it is a strong dependence. So it looks from our work like there's an intimate connectivity between the spin pumping and the enhancement of the damping and the presence of PIM. If you have a large proximity-induced polarization on platinum, you have high damping. If you have no proximity-induced polarization on the platinum, you have very small amount of damping. That's a key result. So the interface is really critical. It's not just the bulk of the heavy metal, it's the interface and its proximity polarization seems to be intimately linked to that. So that's all I wanted to say. So I'd like to go to my conclusions. To say the spin diffusion length is sensitive to the film thickness, I would say. We see a damping in nickel iron platinum and cobalt iron platinum that shows a relationship with the proximity-induced magnetization in the platinum. What that means is the theoreticians need to go back and actively consider the role of proximity-induced moment in spin transport. And if you would like more information, these works are published recently. Thank you very much for your attention.
Thank you very much for excellent talk. So this is the time for the questions. So I invite you for a few brief questions.
Yep, thank you.
From the audience.
I think there is a question written by Satya Prakash Patti. I will read it. He has issues with microphone. How maximum movement in a mu bore unit can be obtained in platinum layer by proximity-induced movement?
Sorry, can you repeat the question? I caught the last part, but not the beginning.
So how much magnetic movement in mu bores can be obtained in platinum by proximity-induced effect?
It's a good question. I don't know that number off the top of my head. People have measured that with XMCD. When we're doing X-ray reflectivity, we don't measure it directly. We have we can only look at relative changes, but it's relatively small. But I don't remember the number. It is published in some works by the So I don't know the number. Sorry.
Professor Giri, maybe we can take one more question by Saugata Mallik.
Yeah, please.
Hello, Dale. Very nice talk. I enjoyed it. I have a question. You said that the spin diffusion length is sensitive to the film thickness. Here, film thickness, you are basically corresponds to the heavy metal thickness, right?
Yes, yes. And we're looking at spin diffusion length in the heavy metal. Yes.
This is quite crucial information because you see there is a difference of factor of 10, and like we quite often use aluminum or copper to like have a transparency from the DMI perspective. So can you comment like what can be like the real one, like in between 1 and 10 there is a huge difference, and
well, so our result, our work has shown, and actually there is a work by a very good guy in India called Kuntal Roy, who has done some work on this as well. And independently, we both shown that the thickness dependence is important. And when you put the thickness dependence in, the value that you get is closer to the high end. So it's more like 10, for platinum, it's more like 10 nanometers.
Okay.
But what's interesting, you mentioned also, so it's confusing as well because there is some interface role as well. So you mentioned copper, and copper, yes, copper has a big spin diffusion length. When we put copper into, we did the same work with copper. Copper is much less satisfactory. We get almost no damping enhancement when we put a copper spacer, even a very small copper spacer layer. So there's something more than the spin diffusion length going on. Even copper, which people think of as a nice, simple, well-behaved material, is really complicated. Maybe there's some structural or some interface issues, but it's copper does not behave in the way we were hoping for it to behave. It was more complicated than we expected.
Okay. Thank you very much.
One more question from Ragini Chaturvedi.
Yeah, I'm
Sorry, you've gone quiet.
Sir, I'm audible.
Yes, please.
Yes, my question is that, sir, where you shown your FM ferromagnetic alloys MS loop, what was your T-shape transition at near 300K in a very small lesion? You are getting a hysteresis loop. What is the reason to getting a hysteresis loop at 300K? And what is the TC about your sample, sir?
So let
Exactly
me go.
according to the theory, this is not possible because at 300K, if T is greater than TC, material shows a paramagnetic behavior, then this small resistance is not possible. What would the reason for it, sir?
So I think I have the right graph on the screen now. Do you recognize this one? This is the correct graph you're referring to? Can you see the screen? I'm still sharing.
Yes,
Yeah. So the platinum becomes proximity polarized and it becomes exchange coupled to the ferromagnetic material. So it begins to follow the ferromagnetic material. So if I plotted the hysteresis loop from Moke or from squid, the loop I would see would be really the hysteresis loop mainly from the cobalt iron alloy. What you're seeing here is the same loop shape, but this time it's magnetization in the platinum. We know it's in the platinum because we're tuned to the platinum energy. So the only signal we're sensitive to is the platinum energy. So this hysteresis loop really is coming from the platinum, and the orange loop is really coming from the gold. So we see proximity-induced magnetization in platinum and in gold.
well, sir, this is not the loop. Your first loop where you properly described your MS loop. This was the picture. This I'm not talking about.
I have to interrupt. I'm sorry. Actually, we are running a little bit behind time. So I would suggest there are also a few more questions by Arun Kumar and others. I request, as you have written in the email, the invited speakers are requested to visit the FRAME virtual platform after their lecture. And maybe you can do that after this one more lecture of Professor Haiping Ding. And then you can virtually interact there, and that's like a virtual conference hall. I'm sure the speakers will be there and the participants can enter there. We will have the poster sessions there. So you can go and interact with them, or you can write an email, but I'm sorry, we have to move on. I will just quickly share my screen to present the memento. So, yeah, so I request Professor Giri to read it.
Yeah, so it's my duty to read this digital memento. Symposium on Magnetism and Spintronics, Nizar Bhubaneswar takes immense pleasure in presenting the plaque to Professor Dale Atkinson, Durham University, UK. Thank you.
Thank you very much. Very kind of you. Thank you.
Thank you. So we move to the next topic.
Yeah, let us thanks to the speaker. Yeah. And let us move to the next presentation. So before that, I would like to introduce Professor Ding. Professor Ding has completed his PhD in physics in 2001 from Martin Luther University and Max Planck Institute of Microstructure Physics, Germany. He has been visited for postdoctoral research in different places like Max Planck Institute of Microstructure Physics, Germany in 2001-2002, Argonne National Laboratory in 2002 to 2005, Max Planck Institute again of Microstructure Physics from 2005 to 2006, and from 2006 till now he is professor in physics in Nanjing University, China. His major interests are in molecular beam epitaxy, magneto-optical Carr effect, spin polarized scanning tunneling microscopy, magnetic ultra-thin films and nanostructures, magnetic related quantum phenomena. So with this, I would like to invite Professor D for presenting your lecture.
Okay, thanks the Chairman for the nice introduction. So my name is Haifeng Ding from Department of Physics from Nanjing University in China. It's my great pleasure to present my talk here. The title of my talk is The Evidence of the Inverse Rashba-Eisenstein Effect at Heavy Metal Copper Interfaces. Let me see. Excuse me, I couldn't Okay, here's the outline of my talk. First, I will give you a short introduction when we carry out this work. And second, I would like to explain this symmetry analysis, which is very critical to distinguish this IRE from the other effects. And third one, I would explain to you that our experimental results, hopefully I can convince you what we observed is indeed IRE. And finally, I would like to summarize and acknowledge my co-workers. It is well known that the electron has both charge and spin degree of freedom. In the past, we mainly used this charge current. Part of the reason is it's very easy to generate and detect. Utilize of charge current bring us many new functionalities and improve our daily life significantly. However, the charge current, because of it has jaw heating, it may have leakage current. So it has high power consumption. Unfortunately, as the device size scales down, this problem becomes more and more severe. It's a good time to search for alternatives. Pure spin current, which refers this spin up electron and spin down electrons are moving towards opposite directions, is clearly one of these alternatives. The reason is it has no net charge current, so there's no jaw heating, also there's no radiation amount, so it has very low power consumption. However, it's not so easy to generate and detect. One of the possibility to use this charge current to create a pure spin current and use the pure spin current in a device, and for a readout, one converted the pure spin current into a charge current and to read it out. In these processes, we convert the charge current into pure spin current for writing and converted pure spin current into charge current for a readout. Thus, that we say spin charge conversion is one of the essential ingredients of spintronics. When we talk about spin charge conversion, usually we refer this figure when we injected pure charge current into our sample, which has the spin orbital coupling. Spin up electron and spin down electrons are scattered differently, and the result, especially that in its transverse direction, it's scattered in the opposite direction, resulted in net pure spin current, and this so-called spin Hall effect. And due to exactly the same mechanism, that if we injected pure spin current into our sample, the electrons with opposite spin are moving and in the opposite direction. However, they are scattered in the same transverse direction, resulting a net charge current. This so-called inverse spin Hall effect. Spin Hall effect and inverse spin Hall effect both are the bulk effect. Besides the bulk effect, there's also an interface effect which can contribute to the spin charge conversion, which we call it Rashba-Eisenstein effect, and it's a reciprocal effect, inverse Rashba-Eisenstein effect. In the following, I will go a little more details on this inverse spin Rashba-Eisenstein effect. Its Hamiltonian can be written like this. It is original from that spin orbital coupling, so it is proportional to the cross product of the wave vector k and the spin axis. And it's also originated from that interface inversion symmetry breaking at the interface. So it's proportional to the potential difference across the z direction, across the interface. Alpha r is the Rashba constant. And with this additional Hamiltonian term, the originally degenerated bands were split as two. For the spin up bands, this red one, and also the spin down bands. This is the side view. From the top view, one can look at this, has two circles. Depending on the sign of this alpha r, these inner circles can have this clockwise rotation or counterclockwise rotation, where typically the outer rings has the opposite rotation sense. And this is originally from this Hamiltonian, in this case that spin like to perpendicular to the momentum. And when we're impinging pure spin current, this will create spin accumulation, for instance, for the spin up channel, and this will increase the population of these spin up channels and resulting shift of these two circles and resulting like this. And this shifting will cause the imbalance in the momentum axis and resulting a spin charge conversion. This is so-called inverse Rashba-Eisenstein effect. And because it is an interface effect, it bears great tunability, so it is of particularly interest. And this has been several reports on this Rashba-Eisenstein effect. One of the famous example is silver bismuth bilayer. Roger Sanchez, Professor Villa, and Professor Foote, they compare this spin pumping results of this silver bismuth bilayer as compared to bismuth or silver single layer alone. And they found a strong enhancement on the converted charge voltage, and they attributed this to the IRE at silver bismuth interface. However, this is still in hot debate. For instance, a couple of years later, Professor Charlene Chen from Johns Hopkins group, they revisit this with this spin Seebeck effect. And they found it, no, there's no spin charge, almost no spin charge conversion. It is vanishing spin charge conversion. And very recently, Professor Xiaofeng Jing from Fudan University in China, they used two spin pumping sources to pump pure spin current from the opposite direction into these silver bismuth bilayers. What they found it is, this is inverse spin Hall effect dominant pure spin transport. You see that one says it is IRE effect, one says there's no spin charge conversion, as one says it's inverse spin Hall effect. So there's still in hot debate because there's no direct evidence of IRE particularly in metallic system. So this is still missing. This is why we carry out this work. We would like to search for a system which has direct evidence shows this IRE effect. Before going to our experiment detail, I will explain a little bit to you this symmetry analysis. As I mentioned to you, Rashba effect, it is an effect caused by the immersion symmetry breaking at the interface. The Hamiltonian says that it's proportional to this potential difference across this interface. And this potential difference is originally from this material difference from this bilayer systems. And if we reverse this staking order, this potential difference will reversing its sign. So this Hamiltonian will become negative. That is will result is the reversed band splitting as compared to the left. You will find it at the left, the inner ring has clockwise rotation, while on the right wing, it has a counterclockwise rotation. And it has a consequence on the spin charge conversion when we're impinging pure spin current into it, well, resulting the opposite spin charge conversion for the reversed staking order. So this is would be the fingerprint of the IRE. This reversed staking order should result opposite sign of spin charge conversion. Additionally, because it is an interface effect, so the IRE should only dominate at rising thickness. So if I point it out once more in one sentence, the opposite sign of the spin charge conversion for the reverse staking order at very thin thickness. This would be the fingerprint of the IRE. Okay, now let's look at the real experiments. This is the experimental technique we used, this is the spin pumping. Thanks, Professor Atkinson, he explained this in previous talk. And so here's we had a CPW. We put our sample on top of the CPW. We excited RF field and applied measuring the converted charge voltage as function of this external field. And before going to our real example, I will show you first the set up the benchmark for the sign detection. Here's we first made a measurement for platinum, 5 nanometer platinum. Platinum is a well-known material which has a positive spin Hall angle. So you will see that in a positive field, it shows pronounced signal at positive branch. When we reverse the field, it goes to the negative, it shows the negative with this opposite signal for the reversing the field, as well as this Lorentzian line shape. So it is originated from this spin pumping related spin charge conversion. And this is for the platinum. And let's look at for tantalum, which is another material well known. It has a negative spin charge conversion because it has a negative spin Hall angle. When we apply the positive field, you will see this sign goes to the negative. And when we reverse the sign, it's also reversed. So in the following, we will mainly focus on this positive magnetic field. If I summarize that, if the spin charge conversion is positive, you will only see this positive signal. If it's a negative, you will see negative sign. And that's we will perform the measurements. As I mentioned to you, we will perform the measurements for the reversed staking order of 2 materials. For the material choices, we pick up copper tantalum and the copper platinum. The reason is copper 111 has a well-defined surface state close to the Fermi energy. When it contacted with strong spin orbital material like tantalum or platinum, it may cause that Rashba band splitting. Okay, let's look at the sample. We look at the copper tantalum first. We fix this copper thickness as 6 nanometer, and tantalum we have 2.5 nanometer. You will see that it's independent on this reverse the staking order, both shows the negative sign. Seems there's no IRE effect. However, because this thickness is thick, as also as it is both shows the negative spin charge conversion, which is consistent with the negative spin Hall angle of tantalum. When we reduce the thickness, go down to 0.9 nanometer, you will find that for tantalum placed on top of copper, it shows the positive sign. And for copper on top of tantalum, it shows the negative sign. So this is a very good indication for the IRE effect. And we can go further down to the thickness, goes to 0.6 nanometer of tantalum. It says that, again, found it in the opposite spin charge conversion for the reverse staking order. In fact, we look at a wide thickness regime, and we found it below 1.5 nanometer. It has opposite spin charge conversion for the reverse staking order. Above that, the both goes to the negative, which is consistent with the negative sign of the spin Hall angle of the tantalum. It's because inverse spin Hall effect is dominant. So what we observed is the sign changes with the reverse staking order only at thin thickness regime. If you remember the fingerprint I mentioned before, this is exactly the fingerprint of the IRE. So this is what we observed. And if this is the true signal should be independent on the measurement technique, we also take the spin-specific measurement, which is Professor Charling Chen has used. And it's also very simple measurement. We have a thermal reservoir here. and we have a heater, and we put our sample in between this heater and the reservoir, and this create a temperature gradient. And we're measuring the bodied signal as function of the external field. Typically, it shows up hysteresis look like signals. And I also would like to point out on the sign for the spin charge conversion. For platinum, you see it shows a positive for the positive field. For tantalum, it also shows negative for the positive field. So this again set up the benchmark for the sign detection. And let's look at our real sample. Again, tantalum 2.5 nanometer on copper and 6 nanometer, independent on the staking order, also the negative. However, when we reduce the thickness, go down to 0.6 nanometer, tantalum, it has negative sign, has the opposite sign for the reverse staking order. And when we look at the whole thickness regime, you see again, below 1.5 nanometer, it has the opposite sign for the spin charge conversion, for the reverse staking order. And above that, it is always negative, which is consistent with the inverse spin Hall effect of tantalum. And if we compare both techniques, you will see they are rather consistent, but both change the sign at around 1.5 nanometer. So we confirm this IRE with two independent methods. In the following, I will show you additional confirmation with the control experiment. As I mentioned to you, tantalum on top of copper, it has shows positive sign of spin charge conversion. Copper on top of tantalum is also negative sign of spin charge conversion. Now, if we have copper or tantalum on top of copper, let's add another copper on top of it. So it has two interfaces, one with the positive sign, one with the other one has the negative sign. Both might cancel each out, and resulting only the inverse spin Hall effect. And let's look at the experiments. So we pick up the thickness around 0.9 nanometer, and it shows for this bilayer system, tantalum on top of copper, it shows this positive spin charge conversion. However, when we add another copper layer on top of it, 6 nanometer, this is trilayer systems, you will see sign reverses. So because this is inverse spin Hall effect is dominant. And you may complain this signal to noise ratio is not so good. Let's look at it on the spin pumping signals. And this is 2 layers, bilayer, exactly the same sample. We found it shown spin pumping positive sign. However, when we look at trilayer system, it becomes negative. So we have once again confirms the fingerprint of the IRE at this copper tantalum interface. And actually, we also performed the measurements for copper platinum. Similar finding was obtained. And you may find it here is below 0.3 nanometer. This is opposite spin charge conversion is obtained for the reverse staking order. Both are confirmed with spin pumping and the spin seeback measurements. In comparison with this copper tantalum system, we will find it platinum on top of copper, which shows a negative sign, while tantalum on top of copper, which shows the positive sign. Also, they have difference in the crossing 0 point for copper on tantalum, which has 1.5 nanometer, and for platinum on copper, which only at 0.3 nanometers. And in the following, I will show you this quantitative estimation of this IRE effect. And we pick up a model developed by Kai Chen and Sufeng Zhang from Arizona University, who published this paper in 2015 in Fixed Letter. The main idea is we pump the pure spin current injected into the non-magnetic material, and this need to across this interface. And when it across this interface, it has a interface spin loss. And meanwhile, it also contributed spin charge conversion through this IRE effect. After entering into this bulk material, non-magnetic, it also contributed spin charge conversion through this inverse spin Hall effect. So it has two terms. One is from that inverse spin Hall effect, the other one from this IRE effect. And the reason why we choose this because we trust this model. We test this model with experiment, and we're measuring this spin Hall angle and the spin diffusion length of platinum with different pheromatic material like permalloy, cobalt, and the cobalt iron. We always obtain this, we utilize this model. We always obtain this same spin Hall angle and the similar spin diffusion length. We do not use this thickness dependence. We obtain exactly more or less the same spin diffusion length. And this is for platinum, and we also measured it for palladium. So similar results, similar spin Hall angle, similar spin diffusion length. So we trust this model. And then we pick up this model to estimate the IRE constants. And from our thickness measurements, we know there's critical points where there's around for copper tantalum, which is around 1.5 nanometer. Below 1.5 nanometer, it has positive sign because IRE is dominant. Above that, it is negative sign because inverse spin Hall effect is dominant. So at this critical thickness, there's two effects actually they balance out, resulting in a zero spin charge conversion or zero spin pumping voltage here. So we can put this goes to zero and easily obtain this formula for lambda IEE. It is proportional to the spin Hall angle of this tantalum, and there's only one parameter here is the critical thickness, which is measuring from here. And there's also additional term is this how much the spin current loss at the interface. This delta can be measured from the fitting of this effective spin mixing conductance measurements. With this one, we can calculate it for tantalum on top of a copper, which is positive 0.02 nanometer. For platinum on top of copper, it is negative 0.02 nanometer. And we would like to compare our results with theoretical understanding. Before that, I will show you our structure characterization. This is done with the X-ray diffraction and also with cross-section TEM. And here you may find it cross-section TEM measurements. Here, this part is ink. You can find it's well crystallized. And here's a tantalum, here's the copper. You'll find it's a well separated interface. And if we reverse the stacking order, here's the copper and here's the tantalum. And again, well separated interface. And here's the zoom in of the high resolution signal. We'll find it is well crystalline. Copper is also well crystalline. However, tantalum is more like amorphous. And when we look at this through this X-ray diffraction, we found that it has 111 oriented. And copper is also 111 oriented. Copper 111, as I mentioned to you, it has a well-defined surface state close to the Fermi energy, which is around the 0.4 electron volts below the Fermi energy. And then as we go to our theoretical collaborator, Professor Zhe Yang from Beijing Normal University. Actually, he calculated, he put it 10 layer of copper with 111 oriented and he calculated, added 1, 2, 3 monolayer of tantalum. They always found rush bar band splitting, and like from here you can see for the inner ring is counterclockwise rotation, outer ring is clockwise rotation. Very interesting. He also computed the spin charge conversion for this copper tantalum interface. As compared with the tantalum, it has opposite sign, which is in good agreement with our experiment. And he also made a calculation for plotting on top of copper. Similarly, he found that the big rush bar band also close to the Fermi energy, and he found it in a spin charge conversion for copper platinum always also has an opposite sign with the platinum, which is also again in good agreements with our experiments. And finally, I would like to summarize, and I hope I convinced you that we demonstrate on the first time the IRE at the metallic system is in particular is heavy metal on 111 oriented copper interface, because we observed this sign reversal with the reversed stacking order at the ultra thin thickness. Now, we confirm this with two independent methods, spin pumping and the spin feedback effect. We also developed a method to quantitatively estimate the sign and amplitude of the IRE effect. If you are interested, this paper was published last year in Physics Group B. And finally, I would like to thank my coworkers. This is my PhD student, Dr. Wei Yi, who did most of the experiments. Bingfeng Miao is my assistant. We did data analysis together. And Professor Zhe Yan, who made the first principle calculation. I also would like to acknowledge Professor Minzhong Wu from Colorado State University, who gave us the guidance for the ink field growth, and Professor Yizheng Wu from Fudan University for a lot of helpful discussions. And finally, I would like to thank you for your attention.
Thank you very much for the nice talk. So next session will start from 5 p.m. So we have already crossed 2 minutes. So there is one question we can from Indranil Sarkar. Can you tell your question directly?
Yeah, thanks. Thanks for the nice presentation. I just wanted to know how you ensure a good surface coverage when you start making sub-nanometer thin films, because that might otherwise create pinhole effects for current flow, etc.
Can you repeat the question again?
How you ensure good surface coverage of films at sub-nanometer thickness?
Oh, this one actually we do not know because we're not measuring that. However, from this TEM images I showed you before, you will see that the film has well separated. The interface is good, and from our measurement compared with our thickness calibration, it shows that it's very close to our thickness calibration. So in this case, we can say this is for the thickness control, we have a very good control.
Thanks.
I mean, I can just probably make a comment that probably you are rotating your substrate during deposition.
Oh, actually not. We use the actually perpendicular sputtering.
Okay.
However, we have a bit large target.
Okay, then probably, yeah. Otherwise, people make rotation and that makes kind of the continuous thin film. Okay, thank you. Thank you so much.
So thank you. So
I will now I will share my screen.
Digital memento, yeah. So it's my duty to speak about this digital memento. Symposium on Magnetism and Spintronics, Niger Bhubaneswar, takes immense pleasure in presenting the plaque to Professor Ding, Nanjing University. Thank you, Professor Ding.
Thank you.
Yeah, thank you so much, Hapeng, a very nice lecture.
Yeah.
So I like to also present a small memento to our chairman, Professor Saurabh Giri. So Symposium on Magnetism and Spintronics, SMS, takes this pleasure in presenting this digital plaque to Professor Saurabh Giri for chairing this session 1. So we like to thank you, Professor Giri, for leading this session very nicely. And I like to announce that we will break now for the poster session. So there is 1 hour of poster session. And at 6 o'clock, again, the talks will resume on the same Zoom platform. So it is up to you to log out or log in. It's up to you, but we will meet after 1 hour. Thank you so much. So see you. We can go to the friend platform now to see the posters. Yeah. Okay, I'm sorry, my mind is full. So we are immediately starting the session, but maybe we take a 15 minutes break. So I'm really sorry, the poster session is tomorrow. So we will start immediately after, let's say, Indranil, you are there. So we can start after, let's say, maybe 10 minutes. I am extremely sorry, I apologize. We start in 10 minutes. Let's take a break at least. Okay. So Indranil, please take over.
Firstly, I will congratulate the organizers for coming up with this very exciting conference series, which, if I may call, covers a very unique and timely topic of fundamentals to application of spin. So I really feel privileged to be part of this conference series. With this, I welcome you all to the second session of the SMS 2021 conference series. We'll have 9 contributory presentations, each of 12 minutes. And in order to keep time, I will give a little call out or shout out, what I would like to, whatever you can call it, at 9 minutes, okay, to all the speakers, so that you can wrap up at 12 minutes and we can have few very urgent short questions at the end of each talk. So with this, I would like to invite our speaker, Dr. Niru Chaudhary from IIT Delhi, to start her presentation on formation of 360-degree domain walls in magnetic thin films with uniaxial and random anisotropy. So Dr. Chaudhary, please go ahead.
Yes, sir.
Yeah, by the time Niru shares her screen, so I like to actually introduce Professor Indranil Sarkar. Can you hear me, Indranil?
Yeah, thanks. I can hear you.
Sure. Yes. I'm sorry, I'm a little bit tired today with all this.
You can just say one word. That's it, Indranil Sarkar. Thanks for that enough.
Yeah, Indranil is an associate professor at the Institute for Nanoscience Technology at Mohali in Chandigarh, and very good friend of mine. He also works on various topics in magnetism, nanomagnetism and spintronics. And really thank you, Indranil, for taking care of all this. So please start. Niru is very special. She is my first PhD student. Niru, please go ahead.
Yes, sir. So is my screen visible?
Yeah, it's visible.
Okay. So, okay. Hello, everyone. I am Niru Chaudhary, as introduced, and I did my PhD from 2010 to 16 in NISA Bhubaneswar with Vedanta sir. And presently, I am a research associate at IIT Delhi. And as he said, of course, I am very privileged to be the first student, and we shared quite some memories. So I would like to first share some memories which we had, because this is a decade, it's a success of a decade long time of our lab. So this was very first our experimental trip. We I would like to take the pointer. Yeah. So this was our first trip to IIT Bombay and TFR, and before that I never knew that fun and work can coexist. It was quite hectic schedule in the morning, but evening were always refreshing with sir. And during the course of PhD, we learned very quite a lot of things, from holding the substrate to publishing the papers, managing the data, results, explanations, many things. But what we learned, what at least stays with me till now, is the hard work. Just do your best, give your best, and just give it the best, and whatever happens, take it gracefully. So this was the photo that we had during the conference, Indo-Japan conference, and it was quite of work. So this message still stays with me. And I'm very grateful to all the members, all my lab mates, that we are still in touch, we are still in interaction. This is one photo we had with, we had dinner with sir, with my husband, and it was 2-3 years back. I hope the interaction still continues. And going back to the part, so it is quite obvious as a PhD we had to publish papers, lot of stress, lot of research travel. Then we need to attend the conferences. As I said, we organized two conferences where we volunteered under the guidance of Professor Vedanta. But when we look back, what I remember still is not the stress, but the great time, the group dinners, the lunches that we have. I would really thank everyone for such wonderful moments. And yeah, so this is one. So the work that I'm going to discuss today was also awarded a Best Poster Award in ETA FM 2016. So coming to the talk, I would like to start from the very basic thing from the domains. If I have a single domain state, so the exchange energy will be minimum, but the stray field energy will be more. So the domains are formed to reduce the stray field energy, and we see here if it is a closed state, there is no stray field energy. And if you zoom into this boundary, we see spins gradually rotating from one direction to other. Parallel spins to the domain wall plane is block wall, and this is Neal wall. I'm going a bit fast for the time management, and these are quite trivial. So these are the equations for the domain wall width for the block wall and the Neal wall. Now, if we look into the types of domain walls, so the simplest one is 180-degree domain walls, where we have two domains which is antiparallelly aligned, and the wall separating this black line will be called a domain wall. This figure is the curve microscopy image, where we can see that the two contrasts representing the two domains are separated by 180-degree domain walls. There can be 90-degree domain walls, where the adjacent magnetic regions are aligned 90-degree to each other, and this is the one of the cubic system. Then there can be other systems where there can arise a case where we have domains which is parallel and there is still a wall. So these are called 360-degree domain walls. Now, if we look into the literature, this 180-degree domain walls are quite common for uniaxial systems and 90-degree for cubic systems. But the 360-degree domain walls are very rarely observed. There are cases where they have been observed for the defects, where the system has defects or the pinning center. So what we are doing in this work is we are trying to give a reason, a possible reason, or trying to explain the 360-degree domain walls that we have observed in our system. So our system, we had this aluminum oxide and cobalt iron boron multi-layer system. As you can see, it was 9 layers, and there was a small field applied during the magnetization. So we had field-induced anisotropy, which can also be seen from this plot. But looking closely, we can see there is this small peaks along the hard axis. So this indicates there is a small randomness, a small misalignment between the grades. We will come back to this later. And these are the experimental domain images performed using XPM. So we can look here. If we say the black one is along the field, the white one will be in the opposite field. And what we see is when two domains merge, two 180-degree domain merge, we form a 360-degree domain wall. This thread-like structure along which my cursor pointer is going, this is a 360-degree domain wall. This side is white and this side is again the same contrast. So both the magnetizations are in the same direction. We say both are up. So, and these domain walls are quite stable. As we can see here, it requires quite high field to be annihilated. This is something around 23 millitesla. So here, this is still, a part is still there and some are annihilated. So this was along easy axis. Now, if we go for the hard axis direction, we see that there is this loop-like structures. If we look here, these are again, if we see the zoom part, my arrows here, both the contrasts are of the same gray scale, and there is this thread-like structure, which indicates there is a 360-degree domain wall. So to understand these things, we tried to do oomph simulation, where this oomph simulation is basically based on the time evolution of the magnetization and this kind of LSD equation. The effective field here is given by this equation, and the energy is the summation of all the contributing energies, these anisotropy exchange, Dmax and Tmax. So as I have already discussed, we have some randomness in our system. So what we did was, in addition to the uniaxial anisotropy, we added a small random anisotropy in our system. So it was very difficult to simulate the 9-layer sample. We started it simple. We made it 2 layers, and then we put the most generalized case where generally we have high uniaxial anisotropy in our system, a very small randomness. So we see that for these two cobalt layers, this is kind of two layers of the cobalt separated by Al2O3. So what we see is the reversal in both the layers are by 180-degree domain walls. And just for the completion, the red pixel is along the direction of the field and blue is the other direction of the field. So now what we did was we started slowly to increase the random anisotropy. So we made it equal, random anisotropy equal to uniaxial anisotropy. And we see that there are this, again, which we have seen in experiment, this thread-like structure, this 360-degree domain walls in one layer. And we also tried to see a case, perform the keeping every parameter same, just by changing the values of the anisotropy. We made it such that it is comparable. The uniaxial and random is comparable. So we again see that there is a formation of 360-degree domain wall. And if we look into this hysteresis loop, this zoomed part, which is this D and E, we can see this requires a higher field. This E is higher than D, which is the point of annihilation of this domain wall. Similar to what we have seen in our other XPM measurements here, that it required high field to annihilate. So from this, we can conclude that we need the formation of 360-degree domain walls can occur.
9 minutes.
Yeah. Formation of 360-degree domain walls can occur when either the random anisotropy is comparable to uniaxial or it is greater. And along hard axis, it is when the two domain walls merge, they give us 360-degree domain walls. Now, we did the same thing to understand the reversal along hard axis, kept everything safe, took these parameters, and what we saw was along hard axis, the spins of the neighboring region, they do not rotate coherently. So it should be a coherent rotation rather than they have opposite sense of rotation. So we can see these arrows, these are rotating in an opposite sense. If one is clockwise, this first region, this which I have marked, if this goes clockwise, the other will go anti-clockwise, and there is a formation of 360-degree domain walls. This was for one layer, and if, the same thing was happening for the bottom layer. So what happens here is actually this randomness outweighs the exchange energy and breaks the coherent rotation, and we see this 360-degree domain walls. So to conclude this work, we can say that random anisotropy is which is an essential ingredient to the formation of 360-degree domain walls in our system. Now, I would like to briefly give an overview of the work that I have been doing in IIT Delhi. So this is one part where we have been looking into the spin pumping in this particular system, permular gadolinium. And what happens is this gadolinium, when it comes adjacent to the permullite, a part of it gets magnetized and this antiferromagnetically coupled. Now this acts as a spin sink and it enhances the spin pumping. Now we are also working on 2D systems here. So what we have seen is when we have something around 3 to 4 layers of MOS2 and then there are defects, some kind of triumphs, we see that alpha is enhanced. So this is kind of defect-induced enhanced spin pumping. On the same system, on the same system of 3 to 4 layers of MOS2 and permullite, we determined the DMI, and we can see for comparison, we have given here with the 2 layers, we can see that the slope is more. From this graph, we get the slope of this graph will give us the value of DMI interaction. So we can see that for 3 to 4 layers, it's more. We are also, okay, I have not put it here. We are also working on spin orbit rocks in various systems, something like ferromagnet and ferromagnetic insulators. So that I have not put it here. And finally, I would like to thank all my collaborators during the PhD, and all the collaborators which were associated with this paper and all my papers. Thank you.
Thanks, Dr. Chaudhary, for this very nice presentation. So now we'll take up question. We already see one question in the chat window. Shivangi Rotigi, can you switch on your mic and ask your question?
Hello, ma'am. Ma'am, I have a question regarding Ohm simulation. As far as
Yes.
I know, you are using uniaxial anisotropy. So my question is, in that we generally specify an anisotropy coefficient, and here you have said there are two anisotropy coefficients that you have used in your program. So can you please tell a little about that?
Okay. So
Hello.
yes. There is an option you can add the second anisotropy, and okay, I cannot remember it exactly, but you can say that it can vary. So magnitude can be we kept the magnitude same. We did not vary the magnitude of the random anisotropy of the spins, but what we varied was the direction of the spins. That we did, but I don't remember the exact commands and exact syntaxes. This is what we did.
Yeah, because as far as I know, means with anisotropy coefficient, we just specify a block, specify O-axis, uniaxial anisotropy, and then for uniaxial we get just one parameter, that is K1, to just give the coefficient that we're using.
Okay, I think
there
this
is
becomes
a
a longer
option.
discussion.
There is an option to add the random anisotropy. You can write some random. There is a particular command, a particular syntax. You can directly use it. I think.
So you can you tell me that right now?
Maybe for more detailed discussion, I would request, because we have a really short presentation, maybe you can go to this friend zone as described by Dr. Vedanta and discuss over there.
Okay.
So
thank you.
Yeah, not only today, I think tomorrow, day after, all 3 days, anybody can go to the frame. You can also drop an email and go there and discuss. Okay.
Great. I don't see any further questions being raised or hands being raised.
Sir, can I ask one question?
Sure. Please go ahead.
This is regarding domain wall width in the case of Neil wall. I think the anisotropy K is missing in that. Intentionally you put that, or
no. I'm really sorry. I made the presentation in quite hurry.
Fine. Actually,
it can be a mistake.
I can find only the dipole interaction term there.
Where
the first slide where you have given the thickness of the domain wall. Here, Neil wall case, there is no K. In the denominator, there has to be K plus the same square term will be.
I might have missed
okay,
it.
maybe
I've made this in
this
really
could be
hurry.
more a one-on-one discussion. So
fine.
I think that makes us move this next talk. But before that, let's thank Neeru for this excellent presentation. I will clap for her.
Thank you, sir.
Okay.
And Indranil, our organizing team will share their screen to present the memento.
Fantastic.
For invited talk, so you kindly present to the speakers. Okay.
Okay.
Yeah.
So is this one coming up? First one for Neeru or?
Yeah, for Neeru and all other speakers.
Yeah.
Neeru,
can you share it?
Sharing, then they will share the screen.
Sure.
Yes.
Okay, so I will read it out for you. Symposium on Magnetism and Spintronics, SMS 2021, takes immense pleasure in presenting the plaque to Dr. Neeru Chaudhary, IIT Delhi, in appreciation for being a valuable speaker to give a lecture on her presentation, Formation of 360 Domain Walls in Magnetic Thin Films with Uniaxial and Random Anisotropy. Thanks, Neeru.
Thank you, sir.
Thank you, Neeru.
Thank you, sir.
Very nice.
So let's move to the next presentation, which is by Dr. Sagarika Naik. She's from NISER Bhubaneswar, and today she will be presenting her work on role of spin glass-like frustration on exchange bias effect in iron, iridium, manganese electrostructure and nickel manganese cobalt Dr. Naik, can you start? Shubhankar?
I don't know. Sagarika, are you there? We see something on the screen. Sagarika, you need to unmute. I don't.
Hello, sir.
Yeah, we can hear you. Please start your presentation.
Sir, just give me 20 seconds. I'm starting.
Sure, sure.
So, am I audible?
Yeah, you are audible.
Hello, sir and all. Before going to my presentation, I want to tell something related to LLM. So I joined as a PhD student from 2014 to 2020 at Niger under this provision of Dr. Chubankar sir. And from after defending my thesis now I am working as a postdoc at Niger in the same LLM lab from 2020 July onwards. So my research topics are exchange bias and exchange ping systems. These are few publications from LLM I got, and so now, so my current topics in my postdocs are like organic spintronics, molecular spintronics, inverse pinhole effect, and exchange bias, etc. So I would like to express that my feelings towards LMM is that. So of course, LMM is the best place for healthy research, but also it is a constructing environment and rising steps towards research. So, so my the topic is for my presentation is role of spin plus light interface on exchange bias property in ferromagnet antiferromagnet thin film systems. So first I will describe how the exchange bias phenomena occurs. So if I consider a ferromagnet and antiferromagnetic system, so ferromagnet has its ordering temperature called Curie temperature, and antiferromagnet has its ordering temperature Néel temperature. So when you also we need to go to a temperature below both Curie temperature and Néel temperature. So and after that we need to field cool the sample, and because of that field cooling procedure we get an unidirectional exchange anisotropy at the interface, and that is called unidirectional anisotropy. Because of that you can see at the interface fields are ferromagnetically coupled, and in many systems, this ferromagnetically coupling order in positive field cooling procedure, and because of that, there is an excess interaction at the interface. And when you sweep the magnetic field, the ferromagnet requires an extra magnetic field to reverse to negative saturation direction because of the exchange interaction at the interface. Therefore, we get a shifted hysteresis loop, and the shift in the hysteresis loop is called the exchange bias field. So next, I will describe the application, spintronic application with this antiferromagnetic based exchange bias system. So in a memory device, in the storage devices, we need a read and write heads, and that is basically like spin valve. That read and write heads basically spin valves or MRM devices, and also in the leaving that point also, now because of to lower the power consumption and thermal stability and other things, so thermally adjusted MRM device also uses antiferromagnetic metals. Next to move, I will go to the interface configuration in a ferromagnetic and antiferromagnetic configuration. So in a ferromagnetic antiferromagnetic system, if there are epitaxial also, the if they are epitaxial also, but the interface structure is completely different from the bulk of ferro and antiferromagnetic structure.
And the situation is also different if ferron and ferron polycrystal or an amorphous system, but their interface, many theoretical models have been proposed to explain the exchange bias result considering the spin configuration. In many theoretical models, they have used collinear interface configuration and also not collinear interface configuration. In first AB figure, we can see these are ferromagnetic couple and this B, it is antiferromagnetic couple. And in this figure, right side two figures, we can see this configuration and non-collinear configurations. This is because of lattice mismatch, strain and defects and other things. But in this slide, I have not discussed about spin class like interface. So interface can be also spin class like. So spin class model first described by this thesis by Chlorine Radu. They have introduced in this thesis the spin class model. In that model, they have assumed the interface is like spin glass. So in the spin glass means there is a competitive ferro and antiferromagnetic interaction. So there is like called a frozen spins, which is frozen by the field cooling procedure, and another is rotatable spins, means this can be rotated during the magnetization reversal. So the interface contains both the frozen spins and rotatable spins. So because of that, the rotatable spins, because of that, there is a non-collinear collinearity with the cooling field direction. And this they have these energy equations. They have used these energy equations with the additional term like effective spin glass anisotropy, reduce effective spin glass anisotropy, and reduce effective exchange coupling energy at the interface. And they found that when the interface is spin glass like, then there is a significant amount of exchange bias is present. However, when there is a completely random interface is present, it is found that this MS loop is completely symmetric. So we can say that a spin glass like interface can also give exchange bias like effect. So this is my results. So I will first describe the iron iridium manganese exchange bias system, in which iron is the ferromagnetic layer and iridium manganese is the antiferromagnetic layer. The systems are grown on silicon substrate with the seed layers like tantalum and copper to improve the growth of iron and iridium manganese systems. And so first I will describe how we investigated the spin glass like interface, how it tuned the exchange bias properties. So we first take the temperature dependent study, and we found that by field cooling and field cooling procedure, we took different MS loops at different temperatures and extracted the value of exchange bias field and corrosive field and plotted against temperature. And we found that there is an exponential decay of both exchange bias field and corrosive field with temperature. So in general, if there is a frozen space at the interface is present, then there is a much range in exchange bias field, but there should be a low value of corrosive field because the spins are frozen and that does not contribute to the corrosive field. But however, if the interface is spin glass like, then both the interface contains both the frozen spins and the rotatable spins. Because of that, we found there is a sudden rise in both exchange bias field and corrosive field at low temperature below 50 K. This indicates the presence of spin glass like interface and its role to exchange bias property. Further, we have performed cooling field dependency. So first we field cool the sample set from 400 K to 5 K in presence of different cooling magnetic field. However, we found that the exchange bias field is decreasing with cooling field. In general, in a ferro and antiferromagnetic system, the exchange bias field should increase with cooling field because the number of frozen moments increases with the increase in cooling field. However, there is because of the spin glass like interface, there is a competition of interface spins with the cooling field and because of that interaction with cooling field, that interface spins becomes more random, and that corresponds to the decrease in exchange bias field with cooling field. Further, I performed the training field measurements to see if the interface is also playing a role to the this spin glass like interface is playing a role to the training relaxation or not. To find training effect, we first field cool the sample and taken the first hysteresis loop, and after that I took 10 consecutive hysteresis loop and then plotted the action bias field with loop number and found that there is a very large decrease in action bias field from n equal to 1 to n equal to 2 loop. However, there is a continuous, there is not much large decrease, but it is continuously decreasing with loop number. And therefore, first try to fit with this thermal relaxation. This equation number 1 is the thermal relaxation model. This is based on for a ferro antiferromagnetic system. But we could not fit the data using thermal relaxation model, considering the ferro antiferromagnetic system. However, considering the frozen and rotatable spin relaxation model, where this exponential term AF and PF, the exponential term, and this exponential term, this PF is basically the relaxation of frozen spins, and PI is the relaxation of rotatable spins. Considering this model, we found that there is a best fit with this model, and we found that this parameter we have evaluated and found that the interface rotatable spins is relaxing 8 times faster than frozen spins. So we found that is the interface is spin-glass-like, and it is almost constant with varying the thickness of the iridium manganese layers. So indicating that iridium bulk iridium manganese is not contributing to cobalt iron boron systems. However, because we also found the similar behavior of the exponential decay and also exponential decay with temperature and also decrease action bias with cooling field. So I am showing the results of only the training effect of nickel manganese cobalt iron boron action bias system. In that system, we varied the nickel manganese system like 5 nanometer, 10 nanometer, and 15 nanometer, and similarly we fitted the similarly we have fitted the data with this thermal relaxation model, but we found this instead you can see that n equal to 1 data we could not fit, and this indicates that that might be a possibility of the presence of spin glass-like interface. And we consider these two models which can be considered for spin glass-like interface, and we found that somehow in this system we found that the ratio is increasing with the increase in thickness of the nickel manganese layer. This indicates that is the nickel manganese bulk of the nickel manganese is contributing to the training relaxation. So in this system, nickel manganese cobalt iron systems, we perform AC susceptibility measurements to find if to find further evidence that is this interface is spin glass like in nickel manganese cobalt iron system. First, we perform the AC susceptibility of nickel manganese single layer thin film, but we found noisy data. However, when the bilayer system is we performed the AC susceptibility, we found that that the peak shift is happening with the increase in the frequency, AC frequency. And we fitted the data, and we found that best results indicating that is from Hubel-Fulcher fit. We found that is the interface is spin glass like, so spin glass frustration is present in this system. However, we could not fit the data considering critical slowing down model. This indicates that is the interface spin glass frustration is not that much strong, so that critical slowing down model is not satisfying. So this is the summary. So we found the presence of spin glass like interface and its effect on action bias property. We found the antiferromagnetic bulk contributes to the training relaxation and also to action bias. So my sincere gratitude to my supervisor and Subhankar Vedanta sir, and that thanks to all my lab members. Thank you.
Thanks, Dr. Naik. It was really excellent talk. So now we can have some questions. I don't see any hands yet. Okay. So Sagarika, just a brief question. It was a really excellent one. What would you call as one unique experimental proof to know that really a spin glass interface is formed. Apart from, is there anything that people normally do apart from doing this indirect measurement to understand spin glass interfaces? Are there any experiments available?
This memory effect we can do, but for that also spin glass may be strong, and also edging effect, and like this magnetization time means different times this edging effect we can do.
Okay.
And
Okay, that sounds good. Yeah, let's once clap for Sagarika. I will clap for her. It was really nice presentation. So Shubhankar, you can share the memento maybe. I can read out.
Could you please stop sharing your screen?
yes, yes.
Okay, so Symposium on Magnetism and Spintronics, SMS 2021, takes immense pleasure in presenting the play to Dr. Sagarika Naik from NISER Bhubaneswar in appreciation for being a valuable speaker to give a lecture on role of spin glass-like frustration on exchange bias effect in iron, iridium, manganese, and nickel manganese coffee B bilayers.
Sagarika, please stop sharing your screen.
Thanks, Sagarika. Right. So maybe we can go to the next presentation with this one. I would like to invite Mrs. Mona M.M. Bhukta from Johannes Gutenberg University, Germany, and she will be presenting a work on degenerate fermionic states in synthetic antiferromagnets. So Mrs. Bhukta, please go ahead with your presentation.
Can you see my screen?
Yeah, we can see you, but not your
okay, I guess now.
Yeah, it's coming up.
Thanks.
Yeah, we can see it.
Okay, hello everyone. I am Mona Bhukta, and I am currently a PhD student at Johannes Gutenberg University at Mainz with Professor Dr. Matthias Klaue. And I have done my master's, integrated master's from NISER from 2015 to 2020. And during these times, for my sixth semester project, I worked with Dr. Shubhankar Vedanta with LSMO, and it was a really nice work for 6 months. And until I moved on to my love on the fermions for my master thesis, and where I worked with the energetically degenerate fermion states in synthetics, antiferromagnets, and temperature-dependent fermion dynamics. During these 3 years at my NISERs, it was really working with all the colleagues from the LNMM, so it was a really great pleasure for me. I attended 2 conferences in my times in LNMMs. One is ICMAGMA in 2018, and one is BTNT in 2019. And I really want to thank all of the LAM members for their help and support. So with this, I want to move on to my talk, and today I will be presenting about the part of my master's thesis was which says the degenerating fermionic structures in synthetic antiferromagnet. First, I would like to thank my all my co-authors, Dr. Rajbhushan Singh, Dr. Saugata Mallik, Dr. Stanislas Rohat, and my professor, Dr. Shubhankar Vedanta. So before going to it, let's have a small overview about the fermions. What is a fermions? A vector field is called as fermions, or called to be a fermionic if it is a spherical topology. So the fermions has initially discovered in the field of nuclear physics before it comes to the field of the condensed matter physics, and we know that the fermions have been topologically protected. So the fermion spin textures are arranged in such a way that you can really map into a unit spheres, and it can wrap up the unit spheres exactly one time. So these topological protected make the fermion specials from rest of the domains in the domain sols. Because of this integer topological number 1, it cannot degenerate to another topological states of monodomain state, let's say 0, because of these energy barriers. And currently there are a lot of mechanisms that stabilizes the fermions. Amongst them, so one of the mechanisms that we focus here is the DM interactions, interfacial Dymolsky-Moria interactions. But we know that the fermions have some demerits as well. The demerits means
Mona, sorry to bother you. Can you share your screen in a way that it's in the presentation mode, because
it's not in the presentation mode?
No.
Not now.
Mona, I think you go on top, the display settings, you make it, just go to the display settings on top.
Now?
Yes, now it is better.
Okay. Yes. So because of these topological properties, also skyrmions has a negative points because this topological property provides the skyrmions as skyrmions Hall effects. When you apply current in a nanotracks or a racetracks, the skyrmions will deviate from the directions of the current flow, and this phenomenon is known as this phenomenon is known as skyrmion Hall effect. But this now there is various way to overcome and minimize this skyrmion Hall effects. One of the ways the putting a skyrmioniums. A skyrmionium is a one skyrmion inside another skyrmion, where the topological charge becomes zero and the skyrmion Hall effect becomes zero. And there are other ways like synthetic skyrmions and synthetic antiferromagnets, skyrmion in antiferromagnet, manipulations of skyrmion Hall effect using in-plane magnetic field. So one of the approach that we have been taking here is the skyrmions in synthetic antiferromagnets. There have been several works of using skyrmions in synthetic antiferromagnets. It shows that if you have two layers which is antiferromagnetically coupled by RKKY interactions, in the top layer the skyrmion will have the topological charge of 1, and then the bottom layer the skyrmion will have topological charge of -1 because of the negative RKKY interactions. And if you apply this current, now the top layer skyrmions have the skyrmion Hall effect opposite to the bottom layer skyrmions, and this will cancel the overall skyrmion Hall effect, and this will make the skyrmion moves in the straight line. Okay, so moving from the skyrmions, there are also a lot of varieties of exotic structures that have been currently investigated using different kind of mechanisms. So one of this mechanism is the frustrated exchange interactions that we just Sagarika talked about just before my talk. So in the frustrated, if you have a systems which has both IDMI and frustrated exchange interactions, we can not only stabilize skyrmions, but we can stabilize various exotic spin tensors like q equal to 0, q equal to 2, q equal to -1, 1, 2, 3. And there has been some report about this kind of structures in the theory. So, but the point to be remembered here is that when the skyrmions is stabilized using this frustrated exchange interactions, we can only stabilize these exotic kind of structures. We can't stabilize this exotic kind of structures only with IDMI interactions, because the IDMI fix a particular chirality of the spin tensors. So what we did in these structures, we did in this work is we want to mimic the frustrations in the systems, but without considering the frustrated exchange interactions, so that in one systems we can have a skyrmion, anti-skyrmions, Q0 or all exotic kind of structures, but we are not considering frustrated exchange interactions in these systems. So for this, we modeled the synthetic antiferromagnets, and in the synthetic antiferromagnets, we have two layers. One is a top layer and then one is the bottom layers. What we did, we modeled the systems using OMP, and we subjected the top layer with anisotropic DMI. So if the anisotropic DMI is a special kind of DMI which forms a anti-skyrmions, and the isotropic DMI is subjected in the bottom layers which forms a skyrmions. Now these two layers are RKKY coupled by RKKY interactions. But what will happen? The skyrmions will try to make another structures which is opposite to a skyrmions in the top layer, and the anti-skyrmions will make another structures which is opposite to anti-skyrmions in the bottom layer. But now these two things will contradict with each other because of the properties of the DMIs. So now here we can mimic a frustrated systems, just like having a normal frustration systems. So for these simulations, we consider some kinds of parameters of MS, D, and K. And what we consider this RKKY interactions as a perturbations. So we consider it's on the three limits: strong coupling limit, intermediate coupling limit, and low coupling limit. And we see how by varying the RKKY interactions as a perturbation, can you stabilize really skyrmion and anti-skyrmions in the same layer? To be noted that now we can have only skyrmion in the bottom layer and anti-skyrmions in the top layers. So now what we did, we saw that at low coupling limit, we did not find any mixings of the skyrmions and the anti-skyrmions in any of the layers. Now then we move on to the intermediate coupling limit. Then what we see that we see some specials and novel kind of spin tensors, and that is called a Q0 structure. In these pictures, you can see this structure has topological charge of Q. And this is the top layers of a synthetic antiferromagnet, where in one layer you can stabilize both his skyrmions, A anti-skyrmion and 0, Q equal to 0 structures in the same layer using the properties of the RKQA interactions and the IDMI. Now we have three different kind of structure: W equal to 1, W equal to 0, and W equal to -1. So this W is the winning number. Now we have 9 possible of paired structures in the 2 layers. And with these 9 possibles of the paired structures, we try to stabilize all of them, but we see that only 6 kind of structures are stabilized in the systems, and the rest of the 3 structures are not stabilized. But to be noted that we see some kind of elliptical, we did not see a circular, conventional circular structures aspect, we see some elliptical structures which has been elongated. So here we see that this is the top layer and this is the bottom layer, and we considered some initial conditions and we relaxed it with the time with a Euler evolver using Ohm, and we see in one layer we have some Scormion-like structures which has a topological number of 0, and the other layer also we have a Scormion-like structures with a topological number of 0. Like this, we get 6 different kind of structures with this. So what is more interesting is we want to know why these structures are stabilized and what are the mechanisms that stabilizes them. So when we see the energy analysis of these 6 kind of structures, we see that there is a 3-fold degeneracy in between these 6 structures. So this basically the structures from the A, B, C, 0, 0, 1, 1 and -1, -1s share the same energy levels and is the most stable structures. And these structures 1, -1 and 1, 0 is also share the same energy levels, and we found a 3-fold degeneracy of 3 degeneracies levels. And then we detailed look at the anisotropic energy, total DMI energy and RKQA energy, and we also found a similar kind of energy degeneracy of these 6 degenerate structures in the synthetic antiferromagnet, which is really novel. And then we move on to the strong RKQA coupling limit, and in the strong RKQA coupling limit, surprisingly we found that we could not even stabilize last 3 structures. We can only stabilize these top 3 structures in the strong limit. So that means all these 3 structures which is higher in energy got eliminated, and we get 3 structures with degenerate energy states. So this makes these 3 kind of structures really noble because of its elliptical shapes and because of stabilizing it in the same field without considering the frustrations. Further, to verify our theory, we considered a wide range of DMI and perpendicular magnetic anisotropy to see if the same structures exist in a wide range, and actually it does. We also calculated the dynamics of the Scormionic structures, because the main purpose of this kind of structures is we can have more freedoms in the data storage technology devices. So here we have simulated one dynamics of the Q equal to 0, 0 Scormions in a synthetic antiferromagnets, and we see that the Scormion doesn't have a Scormion Hall effect, and it has a very high velocity, as high as 1700 meters per second squares. So with this, I like to conclude my talks, and I want to say that yes, we successfully modeled the systems which mimics the spin frustrations by considering the RKQA interactions as a perturbations, and we can see 6 noble different chiral spin textures in the synthetic antiferromagnets. And I would like to thank you all for listening to the talk, and thank you very much. And thank you, Dr. Shubhankar Vedanta sir, for all of his support for my master thesis and for this talk.
Thanks, Mona. It was really a very nice presentation. So now the floor is open for questions. Well, I don't see anything.
Just a short comment, Mona. You forgot to put the archive link.
Yeah, but yeah, I have some mentioned it here.
Where? Okay.
So
right.
the paper is under review in print.
Okay.
Okay. So if anyone want a detailed studies of these papers, please email me and I will send you the archive link, or I will put it in the chat.
Great. So that's great. So I can see the guide at work. Great. So is any further, are there any further questions or comments one would like to make? If not, let's thank Mona for her brilliant presentation. Let me clap for her. Okay, so we should present a plaque for her nice presentation. Mona, can you switch off your?
I have already. Yes.
Okay. So here goes the plaque. Symposium on Magnetism and Spintronics, SMS 2021. Nizer Bhubaneswar takes immense pleasure in presenting the plaque to Mona M.M. Gupta from Johannes Gutenberg University, Germany, in appreciation for being a valuable speaker to give a lecture on degenerate Scormionic states in synthetic antiferromagnets. Thanks, Mona.
Yeah, thank you, Mona. I have a small request, Indranil. Let's take Dr. Robbie Kumar, because he has another meeting at 6:30. and then we can go to Gajanan. Okay.
Okay. So let me invite Dr. Banapelli Ravi Kumar from ISC Bangalore to make his presentation on effect of thermal annealing on the interfacial Zalonsky-Moria interaction in perpendicularly magnetized tantalum, platinum, coffee B, platinum ultra thin films. So Dr. Kumar, please go ahead with your presentation.
Sir, can you hear me?
Yes, we can hear you.
Okay, and could you see me?
Yeah, we can see you. You have to start sharing your slides now.
Yes. So can you see my screen?
Yeah,
No?
you can go to presentation mode now. Yeah, perfect. It's
Yes,
on there.
yes, sir. So first of all, I would like to thank the organizing committee, especially Professor Subankar Vedanta sir and the lab members. I was with them in 2018. After defending my PhD thesis, I joined them as a research associate, and Professor allowed me to work with him. But unfortunately, I had to spend only 3 months time with him as I got Kotari Fellowship and I had to join. So I missed the chance to work with him. Anyway, I always be thankful for his nice company. So can I proceed with my presentation?
Yes, please.
Yes, sir. Just a second. So good evening to everyone. I'm going to present a work on this effect of thermal annealing on the interfacial Zaloshinsky-Moria in perpendicularly magnetized TAPT, CFD, PT ultra thin films. So currently I'm a postdoctoral fellow at Department of Physics, ISC Bangalore. I'm working with Professor Anil Kumar. So outline of my talk is as follows. I'll give a brief introduction about my work, then I'll discuss some results, then I'll conclude the talk. So the spin-orbit interaction at the heavy metal ferromagnetic metal interface leads to perpendicularly magnetic anisotropy and the structural inversion asymmetry. Most of us know about these things. And the perpendicular magnetic anisotropy leads to sub 10 nanometer domain wall widths. By contrast, inversion asymmetry manifests in interfacial Zaloshinsky-Moria interaction, having the form of asymmetric exchange interaction given by the Hamiltonian H is equal to the dot product between the dm constant and the resultant vector coming from the curl of these two neighboring spins. So, and the magnitude of the Zaloshinsky-Moria interaction D is given by the product of the field that corresponds to dm interaction and the saturation magnetization, square root of the ratio between the exchange stiffness and the effective magnetic anisotropy. So interfacial DMI acts as an effective chiral in-plane field that stabilizes Neal walls with a specific chirality, and this chirality is decided by the sign of the DM interaction, as well as the skyrmions can also be stabilized because of this interaction. Actually, this interaction prefers the perpendicular alignment of the neighboring spins because of the interplay between various magnetic interactions such as exchange interaction, which is symmetric one, and the anti-symmetric exchange interaction, which is DM interaction, dipole-dipole interactions, etc. We can observe a slight tilting of the neighboring spins, but we don't see perpendicular alignment of the neighboring spins. And the community is working to get the optimized D to stabilize chiral domain walls and the skyrmions currently. So it is technologically relevant to improve D, but it should not be greater than the critical domain wall, the critical DM interaction. Because above this interaction, the domain wall energy becomes negative and it leads to a spontaneous proliferation of the domain walls. So there have been a few experimental attempts to control the IDMA, such as introducing the tantalum as a buffer layer and giving asymmetry to the top and bottom layers to the ferromagnetic layer. So many trials happen to control the IDMA. So the most of the people try to control the DMI with thermal annealing. So I also choose thermal annealing to tune the IDMI strength in the TAPT CFBPT stacks. So in this work, I have chosen tantalum, platinum as heavy metals and COFB as a ferromagnetic layer. And as everyone knows that COFB is suitable for the current-induced magnetization reversal and domain wall motions in the racetrack architecture and SOTA MRAM architectures. And I have employed a method of field-induced domain wall motion to obtain the DM constant. I have used sputtering system to grow these stacks upon the thermally oxidized silicon wafer. And yeah, in the deposited samples, one be the control sample and the two samples I used for thermal annealing. So here the bottom TAPT were 3 nanometers and the capping was 2 nanometers. I had created an asymmetry above and below the COFB by depositing 3 nanometer on the bottom and 2 nanometer on the top. COFB layer thickness is 0.72 in one stack and 0.93 in another stack. X-ray reflectivity measurements were carried out to know the sublayer thicknesses of these layers, and the magnetization as a function of field and the temperature were carried out on MPMS squid to get the required parameters to obtain the DM constant. And I have employed field-induced domain wall motion using Kerr microscopy. So yeah, the first requirement to get the chiral domain walls, the stack should exhibit PMA. So when I have done magnetization as a function of field in the outer plane geometry, I could see the square loops, and which indicates there is perpendicular anisotropy in all the stacks in the COFB 0.72 and COFB 0.93 stacks. In the control sample as well as the anneal sample, only the 300-degree anneal sample in this 0.72 stack doesn't show PMA. But it shows a reduction in the PMA. So I wanted to know what is the reason behind this, for which I have done zero field cool magnetization as a function of temperature. Here you can see that the phase transition from ferromagnetic to paramagnetic state is occurring around room temperature, and this magnetization as a function of field in the outer plane geometry also is done at room temperature. So that's why at such a critical point, the anisotropy is either weak or absent. That is why there is a reduction in the perpendicular magnetic anisotropy. And the area between the easy axis magnetization and the hard axis magnetization can be used to calculate the K effective. So if I get K effective from this area and the saturation magnetization from this outer plane geometry measurements, I can calculate D only when I get HDMI. That is why I have followed a method reported in this paper, that is field induced domain wall motion. So according to that method, I have created one up domain by giving a pulsed magnetic field in the outer plane geometry, and you can see a circular domain. So when I have given bias in plane field in the positive X direction, the right wall has more velocity than the left wall. When I reverse the in plane field direction, the left wall has got more velocity than the right one. Similarly, when I nucleated down domain using pulsed field in the downward direction, I could see one nucleation of the bubble domain. When I have applied in-plane field in the positive x direction, the left wall has got more velocity. When I reverse the field direction, the right wall has got more velocity. So here you can see the velocity of the circular domain as a function of in-plane field. So here the left wall and the right wall velocity profiles are given for 0.72 and 0.93 CYFB thickness stacks. So, and for annealed samples also it is given. So here the arrow indicates the minimum of this velocity. Actually, if there was no DM interaction in the stacks, this would have been at 0. The minimum would have been at 0. Since there is a DM interaction, we could see some offset in this velocity profile. So this is due to the DM interaction in the system. So, and as the thermal annealing temperature is increased, the DM, the HDMI, let's say HDMI or field that corresponds to DM interaction gets shifted to low temperatures. Sorry, low in-plane field side. So you can see that the DM constant is decreasing as a function of annealing temperature, and as a function of thickness, it is decreasing. So in the inset, you can see the domain wall width that is found in the order of 10 nanometers. So this negative sign indicates that there is a right-handed chirality in the system. So, so assume that the here this is up domain, from up to down, it is going in the right-hand chirality mode. So in conclusion, the D decreased with increase in the CYFB thickness and the annealing temperature. So I am attributing it could be due to boron diffusion out of the CYFB layer, and the interlayer mixing is also happening. Yeah, I would like to thank the organizing committee for giving me this opportunity to present my work. I would like to thank my mentor, Professor P.S. Anil Kumar and Shrikar, who helped me for getting velocity profile using Python code. I would like to thank IASC for giving me, for facilitating me with the clean room facility. I would like to thank UGC India for DSK PDF fellowship. Thank you. Thanks for your attention.
Yeah. Thanks, Dr. Kumar, for the nice presentation. I think we have got some questions here.
Yes.
So take them up. Okay, so I think this is from Shahid. Shahid, can you please switch on your microphone and go ahead with your question? Shahid? It seems he can't. So let me ask the question for you.
Yes.
From can coffee bee composition change the PMS strength?
The strength, yes, it changes.
Yeah, would you like to detail on it a little bit, like
yes.
how it changes if it becomes cobalt rich or iron rich?
Yes, even I have gone through the Chikazumi book for getting the answer why boron is mixed up with COFE and not others. So there I have seen the anisotropy is varying when you change the cobalt concentration, iron concentration, and when you mix up with boron, aluminum, any other elements. So by reading that only I got the answer. Yes, the properties would change when you change the concentrations.
Okay. So maybe just would like to add one comment that it's of course the hybridization of the various states, the surface states, which brings out kind of spin polarization at the interface, which can be in plane or out of plane. Well, okay. So there is another question. What is the composition of coffee bee? So
this is 60-20-20. Cobalt rich.
Hello.
Hello.
Yeah.
I have another question.
Okay.
Okay. In case of platinum CFD system, it is well reported that by BLS people can observe up to something like 0.61 millijoule per meter square. But if in your case it is symmetric stack, but you also seen some kind of similar kind of value. So may I know means how this annealing changes this much value, gives this much value? Because
Yeah. So here, first of all, this is not symmetric stack. Of course, quasi-asymmetric. It is the bottom layer thickness is 3, the top one is 2. But in the control sample itself, you can see the value is around 0.6, right?
yes,
Not
yes,
in,
that
yeah, it is around 0.58. Yes.
Yeah, I am agree that this is the thickness is asymmetric, but if you see in case of IDMI, interfacial DMI, around up to 2 nanometer only, it will the IDMI plays in the thickness of 2 nanometer of heavy metal, the plays in interfacial DMI. So in the if you see that way, then the top and bottom layer thickness is only 1 nanometer is difference. So
Yes.
this asymmetry gives that much value, are you saying?
Not only because of the platinums, the bottom tantalum also contributing to improve PMA as well as D. So there are reports if you deposit the buffer layer tantalum and if you don't deposit buffer tantalum. So that is also contributing to the DMI.
Okay.
Okay.
That sounds good. I think for further question, maybe we can again get into that friend zone as described by Dr. Vedanta, Professor Vedanta, sorry. So let's thank Dr. Kumar for his very nice presentation. Well, let me clap for him. So I will read out the plaque presented to him. It reads like this: Symposium on Magnetism and Spintronics, SMS 2021, NISER, Bhubaneswar, India, takes immense pleasure in presenting the plaque to Dr. Bandapalli Ravi Kumar from IC Bangalore in appreciation for being a valuable speaker to give a lecture on effect of thermal annealing on the interfacial Zalonsky-Moore interaction in perpendicular magnetized tantalum platinum coffee B platinum ultra thin film. Thanks, Dr. Kumar, once again. So,
thank you, sir.
Yeah. So I think let's
Thank
go
you,
ahead.
Ravi.
Thank you, sir.
So can we move on to the next presentation? Shubhankar, is it Gajanan?
Yes.
Okay, so it's my pleasure to invite our next speaker, Mr. Gajanan Pradhan from INRIM, Italy. And he is going to present the talk titled Effect of Random Anisotropy in Stabilization of Skyrmions and Anti-Skyrmions. So Gajanan, can you please share your screen and start presenting?
I guess it's okay now.
Yeah, your slides is shared. Yeah.
Okay. So hello everyone. I'm Gajanan Pradhan, and now I'm working in RIM in Italy. So today I'll be going to present my topic, which was my master's thesis topic, the effect of random anisotropy in stabilization of skyrmions and anti-skyrmions. So briefly about my background, at NISER, Bhubaneswar in India. I did my bachelor's and master's integrated degree in NISER, and my major was in physics and minor in chemistry. So my master thesis was under Professor Shubhankar Vedanta at LNMM lab in NISER, and I worked on this magnetic random anisotropy effect in the stabilization of skyrmions. And we had this publication this year about this work in the Journal of Magnetism and Magnetic Materials. So here is my group. These were the people who were when I was doing my master's, and it's a really very good group, and we're still in contact with each other. And the field we are working on is also kind of nearly similar to each other. And currently, I'm working as a PhD at INRIM, in the National Institute of Meteorological Research at Torino in Italy. And I work now on a very different field. In fact, on the electric field control of magnetization reversal in topological nanostructures in multiferroic stacks, and for low power magnetoelectronics and data devices. So brief introduction on DMI, which, even though it has been covered by other people recently. So Zalewski-Murray interaction is asymmetric exchange interaction, which is found in bulk materials and also in thin films, where we have this inverse and symmetry breaking in case of inverse and symmetry breaking, and also large spin orbit coupling layers, which are the prerequisites to have a DMI in the system. So in thin films, we have this interfacial DMI, where we have this large heavy metal or the large spin orbit coupling and large spin orbit coupling material, where we generate this D1 tensor, the DMI tensor at the interface. And talking about the skyrmion formation and anti-skyrmion formation, when we have isotropic DMI, the DMI, the chirality of DMI along X and Y are the same, then we generate skyrmions in the system. And when we have an anisotropic DMI, when we have this, and the chirality is opposite along X and Y, we generate anti-skyrmion devices. So these skyrmions are this vector plot, which can be reduced to a topological number, which is described by this equation. And for a topological value of 1 or plus or minus 1 for a skyrmion and anti-skyrmion are the most stable states in thin films. So we used micromagnetic simulations to perform to understand the stabilization of these structures in magnetic thin films, which these software that we use is object-oriented micromagnetic framework. So it basically uses the Landau-Lifshitz-Gilbert equation, as you can see in this one, which governs the magnetization dynamics of the individual spins at local sites. So M cross H effective, as we know, is the precisional motion along the H effective field, and the M cross dm by dt is the damping term, which aligns the spin along a particular H effective orientation. So this H effective orientation, the value can be deduced from the total energy of the system which we experience. So this total can be the energy associated with the anisotropy, the exchange interaction, the demagnetization energy, and also the DMI energy, as we represented from here. So in our simulations, we added random anisotropy energy along with the uniaxial anisotropic energy. So what we try to do is we try to imitate the heavy metal ferromagnetic interface, and we had PMA, perpendicular magnetic anisotropy, in the system. So we added this extra Ku, Kr, the randomness in anisotropy for each local sites. So we had a fixed value of Ku along 0, 0, 1 direction, and for each local sites, we changed the we added another anisotropy constant, which is changed for each local sites, as you can see from the different random set values as shown here. So the net anisotropy for each local sites is the vector addition of this Ku and Kr. So overall, we generate a system where we have different magnitude and different direction of total the net anisotropy for each local sites. So the motivation of this work was we wanted to understand the actual scenario which we have in thin films, where we, due to the inhomogeneity in thin films, we do not have the exact anisotropy constant for each grains in our system. And also due to temperature fluctuations, due to some other effects also, we can definitely change the anisotropy constant for each local sites. So further going into results, we first tried to take a nano element of 200 cross 200 nanometer size, and we tried to generate it to nucleate a skyrmion and then stabilize it according to the LLG equation. So in the first case, when we Kr is 0, when there is no random anisotropy anything, only the unit PMA systems, we generate an ideal skyrmion size, if in the first case one we can say. And when the next case, when we added a little bit of random anisotropy, the 0.1, which is very, very less than the Ku value, we slightly changed we deformed the shape of the skyrmion and also the size of the skyrmion. So further, when we increase the Kr to a very large value, we see that the skyrmion size has been very reduced, and also the size, the reduction of the size of the skyrmion is due to the high anisotropy because of the addition of two different anisotropies. For each local sites, we change then for the net anisotropy, we increase of the system. So performing some energy analysis on those structures, we see that when we increase the Kr value from 0 to K3 to 0.8, we increase the random anisotropy energy to a very high level. So if we are from 0 here, probably for P into 10 power minus 18 here, and we have the 22 into 10 power minus 18. So we understand from here that the inclusion of random anisotropy in the system changes a lot, affects a lot in the presence of this anisotropy is associated with this Kr value, which further changes the structures which are studying in our system. And then we also calculated the net magnetization. Of course, with low skyrmion size, the net magnetization of the total nano element we have is higher for case 3. And for all the three systems, when the skyrmion is evolving, we have this, and when it reaches a final state, we have the topological number calculated to be 0.9. So this was done using a Python code. And we observe it's not exactly to 1, because when we have the simulations, we discuss the cell size as like 1 nanometer or 2 nanometer. So when we consider the rotation of spins from from outside to the inside of the skyrmion from 1 to -1, there are some fragments. So that's why we cannot exactly come up to +1 value. Similarly, we perform this one also on anti-skyrmions. We observe similar behavior with this Kr equal to 0. We have this perfect anti-skyrmion state. So this state is a bit squared. This is because due to the block-like rotations and with the higher ms value, which is there in the system. So if you increase the size of the nano element, maybe we expand the size of the anti-skyrmion a bit. So for this case also, we observe that for higher value of Kr, we have this very small size of anti-skyrmion and very distorted size, which is similar to the results we observed in skyrmion. Energy values also represent the similar cases where random anisotropy is very high. For the third case, we have where Kr is equal to the Ku value. And also for this one, for anti-skyrmion, we have the topological number to be negative, depending on just because the spin structures we have in a anti-skyrmion phase, and it's similar to -0.9 as we have in skyrmion. So then we try to change the value of Ku, the uniaxial anisotropy constant and the random anisotropy constant, and try to see the effective size of the skyrmions. So this size was calculated for different randomness in the anisotropy we observed. So we took 5 different cases and tried to average it out and try to find the typical sizes we are performing of for each of the plots on the phase diagram if you see. So what we see is like with increasing in anisotropy, the Ku value, there is the significant increase in anisotropy energy of the system. So that's why we decrease the size of the skyrmion. So if we go from 0.8 to 1, it's at 0 Kr value, we decrease the size of the skyrmion. So next with anti-skyrmions, it is the same case where we decrease to, let's say, from 72 nanometer to 12 nanometer when Kr is very less. Just a second. So, but the thing is, when we see for Kr value of 0.8 megajoule per meter cube, we see that the size variation is quite less. So this can be told as when we have the random anisotropy in the system, it disturbs the whole anisotropic, the easy axis, the local easy axis for each sites. So which acts as maybe a pinning wall, or for the formation of skirmion or anti-skirmion, the size doesn't reduce much. So further, we tried to increase to change the DMI of the system. So we took from 2.8 to 3.8 millijoule per meter square, and with the KR value. So here the KU value is kept constant to be 0.8, and we observed that with lowering of the DMI, we lower the cell size of the skirmions very less, and we observed that it is the same trend for all the KR values. So similar for anti-skirmion also, we observed the similar trend of the shape and size changes for all the phase plots are made for KR and the D value. So overall, we try to observe the shape and size effects, how they are bringing up when we have these different kind of anisotropies and DMIs and random anisotropy energies in the system, and this will give us a very good impression if we for a good study for any kind of experimental observations we have in our future on the present systems. So thank you very much for your attention.
Thanks, Gajanan. It was really a nice presentation. So, are there any questions? I cannot see any in the chat room. If anybody would like to ask a question, it doesn't seem to be the case. So it was really nice. Let's clap for Gajanan once. So I will clap for him.
Thank you very much.
Yeah, I will read out the play. So it goes like this. Symposium on Magnetism and Spintronics, SMS 2021, National Institute of Science Education Research, NISER, Bhubaneswar, India, takes immense pleasure in presenting the play to Gajanan Pradhan from INRIM, Italy, in appreciation for being a valuable speaker to give a lecture on effect of random anisotropy in stabilization of skirmions and anti-skirmions. Thanks, Gajanan.
Thank you very much.
Clap for him once again, and yeah.
Thank you, Gajanan. Very nice talk.
Thank you, sir. Thank you very much.
So can we move to the next speakers? And it's my pleasure to invite Dr. V. Thiruvenkadam from NISER, Bhubaneswar. And he's going to make his presentation on the topic titled Effect of MOS2 on Magnetization Reversal, Magnetic Domain Structures, and Anisotropy of MOS2 on coffee B heterostructure. So, yeah, can you please go ahead?
Am I audible?
Yeah, you are audible, but you have to share your screen now.
Yeah. Is it visible now?
Not yet.
Hello. Just a minute.
Yeah, it's coming now. Yeah, it's visible.
Is it in the presentation mode? Is it visible?
In presentation mode, it's visible and you're audible. So please go ahead.
Yeah. Thank you so much. My topic of presentation is the effect of MOS2 on magnetization reversal, magnetic domain structure, and anisotropy, magnetic anisotropy of MOS2 cobalt iron boron heterostructure. Before getting into the topic, as I am the alumni of the lab, I would like to share some of my feeling towards LNMM. I entered LNMM around July 2017. I worked up to April 2020. My research topic during my tenure is a ferromagnetic semiconductor heterostructure for magnetic field sensor applications. And my research interest is, at present, my research interest is TMD ferromagnetic heterostructure for SOT MRAM applications. And there are too many things are there, very important and significant output from the lab, I would say, because while entering the lab, I was a researcher in magnetic nanocomposites. While entering the lab, I saw the other facet of the magnetism, like magnetic thin film, the complete magnetic thin film deposition techniques, as well as the characterization techniques. These all I learned from 2017 to 2020 from LNMM. I will be happy to share this one. And currently, I am looking for the research position. This is my topic once again. My scheme of presentation is introduction, where I'm giving introduction to transition metal dichalcogenic and its ferromagnetic heterostructure. Hello?
Yeah, please go ahead. We can hear you. Yeah, we can hear you. Please go ahead.
And then followed by the objectives and results and discussion, then conclusions. Introduction to transition metal dichalcogenides. They are shortly called TMD group compounds. It have a general formula of Mx2, where M is the transition metal from the group 4 to 10 in the periodic table, and X is the chalcogen group element, which is sulfur, selenium, and tellurium. These TMD group compounds is just like a graphite kind of layered structure. However, here the transition metals are covalently sandwiched between the between the chalcogen group elements, and each sandwich were with van der Waals force of attractions. If we see their electrical and the optical properties, it is diverse because of large variation in the band gap from 0 to finite. Because of this, its electrical properties vary from semiconductor to semi-metal, insulator to metal. Also, some of the compounds show superconductivity at low temperature. If we see the optical property, because of this wide band gap, it covers complete visible range to infrared range, as shown here. So with these unique properties, when these TMD group compounds were integrated with the ferromagnetic material, it widens their application in the field of spintronic and magnetic storage devices. Here some of the examples I'm showing with the literature evidence. The Shang et al. Shows the interesting anomalous Hall effect in the temperature range of 10 Kelvin to 400 Kelvin in zirconium telluride YIG heterostructure, and this will be in the application of magnetic field sensors. The another one, Jan et al. Written a short review on TMD ferromagnetic heterostructure for spin orbit torque applications, and which will be used in the non-volatile magnetic memory devices. And another one, the Grandel et al. Investigated the cobalt MOS2 heterostructure through DFT calculation, and they found that the cobalt at the interface, MOS2 at the interface near to the cobalt converted into metal. Usually the MOS2 is a semiconductor. At the interface it converted into metal, and also they calculated the spin polarization of 16% in this interface, and this will be have applications in the device with spintronic device with the cobalt electrode for the spin transport application. If you see here, the Wang Zhang et al. Reported the induction of perpendicular magnetic anisotropy in the case of cobalt iron boron molybdenum diselenide heterostructure, and this will be having application in the magnetic storage devices. In all the cases, the interface play a very important role, and these applications are mainly due to charge transfer between or at the interface between the TMD and ferromagnetic material. So our focus is on to study the effect of MOS2 on magnetic property of MOS2 cobalt iron boron heterostructure. In this context, I would like to present my presentation as a two-part. One is fabrication of molybdenum diselenide using sputtering technique and sulfurization technique, and followed by fabrication of MOS2 cobalt iron boron heterostructure and their magnetic studies. Fabrication of ultra-thin MOS2 film by sputtering and sulfurization technique. Here, in order to here the ultra-thin MOS2 films are deposited from sputtering of commercially available MOS2 target. Usually, fabrication of the TMD group compounds from the sputtering is very difficult because the high vapor pressure chalcogen group element usually escapes from the deposition, and we will not get a stoichiometric form of TMD group compounds. The same thing is happened in our case. This shows the sputtered SEM image of the sputtered sample. In order to get means 2 or 3 layer, we limited the deposition with short interval of time, and hence we got island-like structure. Not stoichiometric. It's molybdenum rich because of the high vapor pressure of the sulfur. Sulfur usually get escaped from the deposition, and it is concentrated with the molybdenum. So we move on for the sulfurization reaction in order to stabilize the MOS2 phase, and we did the sulfurization for 5 different temperatures from 700 to 800 degrees Celsius. At 800 degrees Celsius, we able to see some star-shaped structure as shown here in the SEM image, the star-shaped structure, which is and we try to characterize with the Raman spectroscopy. Usually, the Raman spectroscopy show a characteristic peaks for the MOS2. One is E12G and another one is A1G. These peaks are due to the in-plane and out-of-plane vibration of the MOS2 layers. So, by using this Raman spectroscopy, we can also estimate the layer thickness of MOS2 based on the difference between the frequency difference between these two peaks. This is what I am showing here. From 1 to 5 layer, the frequency difference between these two peaks varies like that. Above 25 centimeter inwards, it fall under the bulk category of MOS2. The same thing we can see the different place of the sulfurized sample, which is did at 800 degrees Celsius. We can see many number of star-shaped structure, and their thickness varies from 2 to 3 monolayers, which is estimated from the Raman characterizations. However, for study the heterostructure, magnetic properties of the heterostructure, we need a continuous. However, here we got one island kind of structure. So, deposition time to make a continuous film. However, we lose to create a bilayer or trilayer. We start MOS2. Surprisingly, while increasing the deposition time, while increasing the MOS2, be able to see MOS2 peak even without sulfurization. That was really surprising. But with increasing the deposition time, the peak width, it means that full width half maximum, it decreases. It really indicates the formation of the MOS2 phase. Also, the crystallinity improve with increasing the deposition time. It means increasing the thickness of MOS2. So we plan to deposit a magnetic material on top of it and to study the effect of MOS2 on the magnetic material, which we choose in cobalt iron boron in our case. So here we prepare 2 different samples with different MOS2 thickness of 6 and 28 nanometer. This is the sample structure here, and 6 nanometer of cobalt iron boron on top of it. To understand the effect of MOS2, we prepare another controlled sample where the MOS2 is absent here, and both the samples were capped with MgO. So this shows the TEM image of one of the samples, which is 28 nanometer thickness of MOS2. It clearly distinguishes the interface between the MOS2 cobalt iron boron and the capping layer MgO. And this is corresponding Raman spectroscopy, which shows the peak for MOS2. And without MOS2, if we measure the magnetic property using the Moog-based microscope, where we can record a magnetization curve as well as the domain images with hello.
Yeah, 9 minutes. It's just a call for 9 minutes.
Yeah. So we have here, this shows the angle dependent magnetization curve as well as the domain images for the bare cobalt iron boron thin film, where the MOS2 is absent. It's considered as the reference sample M0. So with changing angle, the magnetization curve did not show much of changes. Also, the domain images also shows did not show any change. This clearly indicates the cobalt iron boron is magnetically isotropic. Here, one more thing I would like to tell that it is deposited on amorphous SiO2, and the deposition, during the deposition, we rotated the sample for 20 RPM in order to suppress any of the growth dependent anisotropy. So this from this result, we can conclude that the cobalt iron boron here is magnetically isotropic. When we comes to the 2 different sample where the MOS2 is present, it's clearly it's different from the previous controlled sample where the hysteresis depends on the angle of measurement. All these measurements are performed by Moog-based microscope and longitudinal mode with a different angle of measurement, and it clearly the coercivity shows the variation with the measuring angle. If we plot the MR by MS ratio with the insert shows the MR by MS ratio with angle, and it's clearly show a formation of a magnetic anisotropy with the presence of MOS2 beneath the cobalt iron boron. Domain images also shows the variation with the angle, and this are the domain videos where we can see easily changes in the domain structure with the field. During the reversal, we can see how the domains are getting changed here. So comparing to the previous sample, these are completely different. It means the cobalt iron boron on top of the SiO2 is completely different from the cobalt iron boron, which is grown on top of the MOS2. And also we can see the sharpness of the MR by MS, the angle dependence of MR by MS. This clearly indicates an anisotropy is getting induced, and it also increases with increasing the thickness of MOS2. It implies that the sharpness in the MR by MS ratio. In order to confirm that, we have performed a FMR measurement, the frequency dependent FMR measurement. Here, this shows the frequency dependence of resonance field and line width broadening for both the sample M1 and M2. By fitting this plot with the Kittel resonance condition, we got anisotropy field, demagnetization field, and Landau G factor, damping constant, and inhomogeneous line width broadening. The inhomogeneous line width broadening decreases with increasing MOS2 thickness. It implies that the crystalline quality or the quality of the cobalt iron boron improves with the increasing thickness of MOS2. And also it shows the increase in anisotropy field. This clearly indicates the induced anisotropy because of the MOS2 beneath cobalt iron boron increases with increasing thickness of MOS2. So followed by this, we have also performed the angle-dependent FMR studies on MOS2 cobalt iron boron heterostructure. This clearly shows the formation of uniaxial anisotropy with minimum of HRES at resonance field at 0 degree and maximum at 90 degree. Again, it's replicated with 180 and 360 degree in both the cases. And by fitting this angular dispersion with this data, we are able to estimate the anisotropy energy density, which is also found to be larger in the case of M2, which is 28 nanometer of MOS2 comparing to the 6 nanometer of MOS2. So these all results clearly conclude that the crystallinity of MOS2 improve with increasing thickness of MOS2. The cobalt iron boron on SiO2 is magnetically different from that of the MOS2. The cobalt iron boron on the MOS2, also the MOS2 induces uniaxial anisotropy on the cobalt iron boron. The strength of the induced anisotropy increases with increasing thickness of MOS2. And I thank my sincere thank to Dr. Shubhankar Vedanta, and I also thank my all lab members for their help and support. I thank Department of Science and Technology, Nanomission for financial support. Thank you. Hello.
Thanks, Dr. Thiruvengadam. It was really nice thing. There seems to be hand raised. So Ravi Kumar, can you go ahead and ask your question, please?
Yes, sir. So Thiru,
yeah.
So you have shown that domain images,
yes,
the video footage, yeah. That
yes.
is measured in the plane or out of plane?
It's in plane measurement. I told it's a longitudinal mode, yeah.
Okay, so the angle dependent one, it is in plane only,
yes,
not to the outer plane.
No, it's completely in plane measurement. There is nothing out of plane here.
Yes, yes. Since the CYFB thickness is more, we can't see outer plane anisotropy, right? What is the thickness of CYFB?
It's a 6 nanometer.
Yes. So if it is lesser than 1 nanometer, you can be able to see perpendicular one.
Perpendicular anisotropy due to the MOS2, it seems.
Totally MOS too. So heavy metals. You have seen in my case, platinum is attached, right? So due to the heavy metal, even for MgO, Al2O3 kind of oxides also giving rise to DMI.
Okay.
And perpendicular anisotropy.
Mm-hmm.
Yeah. Thanks.
Yeah.
I don't. There seems to be another hand up. I can't see. Is this Manikandan? Can you, Damodaran? Can you go ahead and ask your thing?
Hello, sir. Actually, how you estimated the layers, number of layers of MO, SIS2?
Usually,
from Raman.
No. For Raman, I used only for the MOS2. Like for TMD group compounds, the Raman spectroscopy is a powerful tool to measure the layer thickness by the frequency difference between these two peaks. We can estimate easily the layer thickness of TMD group compounds.
Thickness, okay. Number of layers, like you showed different layers, like 1, 2, 3, like that?
No, that is from a literature. Just I would like to tell as an example, I showed that for monolayer, while increasing the layer thickness of MOS2, the difference between the Raman peak, the two peaks, gets shifted. It means the difference increases. So
Okay.
up to 25 centimeter inverse, we can estimate it's a fine monolayer thickness. Above that, it fall under the bulk category.
Okay.
Yeah.
But Thiru, I just like to add a comment that when you are taking these bilayers of MOS2 cobalt iron boron,
yeah,
you have also done the cross-sectional TM.
Yes, yes.
So the thickness also is coming from that, isn't it?
Yes, yes, yes.
Yes, yes. Thickness XR cross-section.
Yes, sir. Actually, for monolayer or bilayer,
we'll take this
two
one last
monolayer, we didn't do the TEM. Yeah.
A reason for the cause of large value of Landau G factor that was observed. Can you explain that?
Yeah, in the case of cobalt iron boron, the pristine cobalt iron boron is amorphous, first of all. While depositing on top of the MOS2, its crystallinity might be improved, but still it's fall under the amorphous category. So because of the amorphous nature, the most of the orbital moments are not quenched properly, and it contribute to the G value. Means I'm thinking like that, and that's why it shows the large G value. Hello. Hello.
Yeah, that.
So, hello.
Okay, so thanks, Dr. Thiru, for your presentation. I think let's move on to the next presentation. And I would request, yeah, okay. So firstly, let me clap for you because you really gave a very nice presentation, a new field of direction and direction of research. So your plaque reads like this: Symposium on Magnetism and Spintronics, SMS 2021, from National Institute of Science, Education Research, NISA, Bhubaneswar, India. Takes immense pleasure in presenting the plaque to Dr. V. Thiruvenganam from NISA, Bhubaneswar, in appreciation for being a valuable speaker to give a lecture on effect of MOS2 on magnetization reversal, magnetic domain structures, and anisotropy of MOS2 on coffee B heterostructures. Thanks, Dr. Thiru. With this, once again, let me clap for you. And
thank you so
maybe
much.
we move to the next speaker. So I think our next speaker is Dr. Debojyoti De from Sukumar Sengupta Mahavidyalaya, West Bengal. And I would like to invite him to give his presentation on origin of exchange bias in nanocrystalline cobalt chromium oxide. So Dr. De, you can start sharing your screen and maybe go ahead with your presentation.
Can you hear me?
Yeah, I can hear. We can hear you. You have to start sharing your screen. Yeah, your screen is coming up now.
Is my screen visible in full screen?
Yeah, your screen is visible.
Thank you, sir. Myself, Debojyoti, and at first I would like to thank the organizers of the Symposium of Magnetism and Spintronics, especially Professor Shubhankar Vedanta, for giving me this opportunity to showcase our collaborative research work with his group in front of this audience, and giving me this prestigious platform to express our research initiatives. I work as assistant professor at Sukumar Sengupta Mahavidyalaya. Also, I am associated with Dana University. And today I'll be talking on origin of exchange bias in nanocrystalline COCR204. And exchange bias, as you all know, it is the consequence of magnetic field separation in the magnetic inhomogeneous materials, and which puts the signature in loop shift of magnetic hysteresis loop followed by increase in coercivity in any kind of magnetic inhomogeneous system. Moving on, I have worked at the Indian Association for the Cultivation of Science and 1 year for Indian Statistical Institute. I am associated now with Ghana University and Sukumar Sengupta Mahavidyalaya. And at Ghana University, we have established a small research lab. And this is our research team, myself, our PhD student Suchandra, and Dr. Magnetism. And since the inception of the lab, we are getting the cooperation and full support from Professor Vedanto and his group. He was also present during the inauguration of our lab. And we work on mainly transport and magnetic properties of nanostructured materials, thin film, graphene, graphene plus nanocomposites. and GMR, TMR, portion structure, etc. And presently, we are interested to find the reason of tuning X-inverse in nanomaterials. X-inverse, which is having the applications in magnetic lead heads, memory device, electronics, GMR, TMR, improving the coercivity of permanent magnets, cancer therapy, etc. And here I would like to present some sweet memories with Niger Bhubaneswar, also our collaborative research initiative with Professor Vedanto's group, Laboratory of Nanomagnetism and Magnetic Materials. Presently also I am associated with this lab as a INSA visiting scientist for 2 months, and we are working on perpendicular X-inverse. And I have visited Niger many a times, and we are getting immense support from Professor Vedanto's group in our research initiative. He has been so kind to us to help us in our research. And the work today we are going to present is the part of the project Dependence of X-inverse on Interparticle Interaction funded by SCRB-DST. X-inverse, as you know, it is not a new phenomenon in science. It was invented years back in 1956 when McLeod and Bain they first reported that a new type of magnetic anisotropy has been discovered, which is best described as magnetic anisotropy, exchange anisotropy. And this anisotropy is the result of an interaction between the ferromagnetic and antiferromagnetic layer in cobalt-cobalt oxide 4-cell nanostructures. And they got the signature of this anisotropy by a loop shift followed by increase in coercivity when the sample is cooled below the nil temperature of the antiferromagnetic crystallite in presence of external magnetic field. And they found that the reason behind X-inverse is the pin ferromagnetic layer generated between the ferromagnetic and antiferromagnetic interfaces when this is cooled in presence of external magnetic field. But nowadays we have learned that X-inverse is not only seen in case of four-shell structures or ferromagnetic antiferromagnetic layer, but X-inverse can be seen in any kind of magnetic inhomogeneous systems having a dual structure like dual magnetic interfaces of ferro, ferri, ferro, antiferro, ferro, glassy, superspin, glassy, and superspin, ferro, glassy, ferro, etc. So we'll be trying to find out the reason of X-inverse, reason of getting X-inverse in cobalt comet in nanocrystalline form. Before that, I will take 1 minute to describe the phenomena of X-inverse. As we know that in four-shell structure, we can get, if we elaborate the or magnify the interface layer, we can have the ferromagnetic structure like that, which are aligned along the direction of external magnetic field. And antiferromagnetic field will be oriented antiferromagnetically. If we cool it below the antiferromagnetic Nil temperature, antiferromagnetic crystallites will be aligned, spins will be aligned antiferromagnetically, antiparallelly. But the fast layer of antiferromagnetic spins will be aligned along the maintaining the direction of the ferromagnetic spins, and they will generate one coupling in between the ferromagnetic and antiferromagnetic interfaces. This is the reason of getting X-inverse in this kind of structure. During the magnetization reversal, the torque is either acting towards the favor of rotation or they opposes the rotation. And depending upon that, we get a loop shift followed by increase in coercivity. And loop shift is along the negative field axis if we put the sample in presence of positive field and vice versa. So the anisotropy is unidirectional in nature. And borrowing slides from Professor Vedanto's PPT, I can describe that in case of this spin ferromagnetic and antiferromagnetic layer, suppose this is the ferromagnetic layer which can be rotated if we change the direction of magnetic field, but the antiferromagnetic layer will have a coupling in between with the spin ferromagnetic layer. So during the magnetization reversal, because of having internal coupling, it is not easy to rotate the spin ferromagnetic layer. And if we magnify the two states of magnetization reversal, this is the first case during the third loop, and this is during the fifth loop. You can see that when the torque is acting against the rotation, you have to apply excess magnetic field in order to initiate the rotation. But when the torque is acting in favor of rotation with less amount of magnetic field, you can easily rotate the spins. If you see this simultaneously, you can easily visualize the difference, and that is why the loop is shifted towards the field axis. That is the phenomenon of X-inverse, as we know. Here we will be talking on the X-inverse in nanocrystalline COCR204 and try to understand whether it is a surface effect or not. So this what I am going to present is the research students who are involved with this project, Mr. Shukendra Goswami from TNU and Mr. Pushpanjali Gupta from Niger Bhubaneswar. And first we prepared different particle sizes of cobalt comet. And the first one with 30 nanometer particle size, 12 nanometer particle size, 7 nanometer particle size embedded in silica, and also a bulk. Now, the first we understand the difference between bulk and nano effect. First, we'll be talking for the sample of 30 nanometer. For the 30 nanometer sample, it was characterized well by XRD and 10. And while taking the thermal variation of X-direction magnetization, we got the magnetic transitions from collinear ferrimagnetic to non-collinear spiral ordering at TS. And when the spiral orderings are locking into the lattice parameter, we got the lock-in transition temperature as reported in the literature already. While we are measuring the exchange bias in this kind of sample at low temperature, we got loop shift towards the field axis while cooling the sample in positive and negative field. This is the clear signature of exchange bias. But while taking the exchange bias at different temperatures, we have noticed that the exchange bias field and coercivity both were decreasing monotonically with temperature. And they were suddenly vanishing after crossing the spin spiral transition temperature. So initially we got some idea that somehow the spin spiral transition temperature is having some connection with the origin of exchange bias in this kind of material. To understand it more in detail, we did the experiment of training effect of exchange bias, and in the training effect, fitting the result with the formula proposed by Binek et al. We found that in the surface there exists rotatable and surface fields, rotatable and frozen fields. So interaction between the rotatable and frozen fields and also interaction of them with the core fields can generate exchange bias. But we are not satisfied enough because the exchange bias we are getting was pretty high. It was about 1000 Oersted. But interaction of the surface glassiness or interaction of the distorted surface cannot give this kind of much exchange bias. We also measured the AC chi in the real and imaginary part of chi in AC magnetic field. We didn't get any loop shift and surface was not glassy. Despite that, we got a clear signature of exchange bias effect, and that paper was reported in Journal of Physics, the Applied Physics. This was our first collaborative work. And to understand it in more detail and find the actual origin of getting exchange bias in this kind of sample, we again repeated the experiment for 3 different samples. First one with 12 nanometer particle size, where the interparticle interaction is pretty high, and as the particle size is very low, surface effect may be there. Second, the particle size was more low, but it was embedded in silica matrix. Surface interparticle interaction was controlled, and surface effect was a little low because of prohibition by silica matrix. Third, we prepared a bulk sample of the same composition to understand the origin of exchange bias, and in the bulk sample we can clearly clone the effect of surface effect or surface field. And the samples were characterized by XRD and 10. And in thermal variation of X-direction magnetization, we got clear signature of this spin spiral transition temperature, as I already told about, and this is lock-in transition temperature for all the 3 samples. Clear signature of exchange bias was noticed at low temperature, and interesting result we got while taking the measuring the exchange bias in different temperatures.
9 minutes.
Exchange bias in different temperatures. We got that monotonically the exchange bias field and coercivity was decreasing with temperature for all the samples. Though the value of exchange bias field and coercivity was different in different samples, but the nature of decrease and vanishing of exchange bias soon after crossing the spin spiral transition temperature was similar in all kinds of samples. If we look all the 4 samples in a single frame, and if you concentrate at the blinking arrow, you can see that exchange bias field and coercivity where exchange bias field mainly was vanishing soon after crossing the spin spiral transition temperature. The first sample with 12 nanometer particle size, it was not glassy. There was no peak shift in AC chi. But the second sample, we got the clear signature of peak shift in real and imaginary chi prime and chi double prime, and it was fitted well with dynamical scaling formula. But we didn't get any peak splitting in AC chi measurement, so it was not a core shell structure. The whole sample was glassy. Despite that, we got exchange bias effect. And as the whole sample was glassy or super thin glass mainly, as we call in case of nano samples, we got a beautiful exhibition of memory effect in XC magnetization, ZXC magnetization, different relaxation protocols, and different protocols in isothermal dominant magnetization. Now, in the conclusion, what we understood finally that suppose I am considering this is room temperature, I am going towards the low temperature, I am crossing spin spiral transition temperature, then locking temperature, then going towards the lowest temperature. The collinear ferrimagnetic spin, they will with decrease in temperature, they will suddenly convert into conical spiral spin. This is as expectation. But in reality, this doesn't happen. In reality, we have seen the clear signature of hysteresis in thermal variation of X-ray ionization. So it is a first order transition, and in the first order transition, there is a high probability of coexistence of both kinds of spins below the spin spiral transition temperature. So the actual scenario may be like this, that below the spin spiral transition temperature, there may be existence of collinear ferromagnetic order, and also above the spin spiral transition temperature, there may be existence of conical order in short range. So competition between them, high competition between the collinear ferromagnetic spin and non-collinear or conical spiral spin can give rise to the exchange bias effect. We propose this model for the 3 samples, where we have seen why the exchange bias field was decreasing or increasing in different samples. Sorry, 1 minute more. For this sample, with 12 nanometer particle size, we have seen that internal magnetic inhomogeneity is present in all kinds of samples, all the samples, whatever be the particle size, whatever be the interparticle interaction or not. And origin of exchange bias is coming from the internal magnetic inhomogeneity. Additionally, where the surface effect is dominant, the exchange bias is increasing. Where the surface effect is negligible, in case of bulk samples, the exchange bias is low. But origin of exchange bias is coming from internal magnetic inhomogeneity, that is the competition between collinear ferromagnetic order and spiral or conical spiral order below the spin spiral transition temperature. And this work was published in the Journal of Alloys and Compounds recently. And we found that this is a potential multivariate sample, and having exchange bias and memory effect in this kind of sample is seriously eye-catching from the point of view of application of magnetic functional material. We acknowledge our work, and I thank Professor Shubhankar Vedanta and his group, especially Pushpendra, who has been very kind to help us during this work. And thank you for giving me this opportunity to present our research work in this big platform. Thank you.
So thank you, Dr. Day, for this nice presentation. So I hope you could hear my clap. Not sure. So I think we have time just for one very short, quick question. If anyone wants to make one. Doesn't seem to be the case. So let us once again thank Dr. Day. And
very nice, Devajyoti.
Thank you.
So I would like to read out a plaque for your nice presentation. It reads out like this: Symposium on Magnetism and Spintronics, SMS 2021, from National Institute of Science Education Research, NISA, Bhubaneswar, India. Takes immense pleasure in presenting the plaque to Professor Devajyoti Day from Sukumar Sengupta Mahavidyalaya, West Bengal, in appreciation for being a valuable speaker to give a lecture on origin of exchange bias in nanocrystalline cobalt chromium oxide. Thanks, Dr. Day. Okay, so let me clap for him once again, and let's move to the next speaker. So again, it's my pleasure to invite the next speaker, Shakti Das from NISA, Bhubaneswar, and she's going to make presentation on the topic device geometry dependent deterministic skyrmion generation from a skyrmionium. Okay, so I think that's it. Yeah, Adriya, if you can start your presentation.
Hello.
Your slide is there. Yeah, you're audible. Your slide is there. You have to go into presentation mode.
Yeah, okay. Okay, thank you, sir, for giving me the opportunity to present my work. Good evening to everyone, and thankful to the organizing team of SMS for all their efforts and management. And I'm grateful to Shubhankar sir for giving me the opportunity to work under his supervision. My work is titled as Device Geometry Dependent Deterministic Skyrmion Generation from a Skyrminium, and this is right now in archive. So before moving on to the discussion, I would like to give a small introduction about myself and my experience at NISA. So my name is Shakti Das, and I completed my MTech in nanotechnology from Central University of Jharkhand in Ranchi. Then I joined NISA in 2019 for my final year dissertation project work.
And I was in NISER for 1 year, 6 months as a short-term project student. And it has been a great pleasure to be a part of LNMM family. And I really like the dynamic environment and the wonderful people, their support and cooperation. Definitely my stay at NISER has been fruitful and enjoyable. Now talking about my interest and research field, it's based on implementation of Spintronics for Spintronic application, and we'll be discussing about it in the upcoming slides. Now, before we get into the details, I would like to give a brief introduction about skyrmions. The skyrmions can be classified as magnetic quasi-particle. It is a non-collinear stable spin texture with the magnetic moment forming a twist structure. The origin of skyrmion can be explained as a consequence of competitions between the exchange coupling, magnetic anisotropy, and DMI in magnetic systems lacking the inversion symmetry. In order to have DMI in the system, it is necessary to have large spin orbit coupling and inversion symmetry breaking. Now, in this image here, the DMI can be explained as the interaction between the atomic spins S1 and S2 with the neighboring atom in the heavy metal in the magnetic thin film. And they have a large spin orbit coupling, which can be seen expressed as this equation here. Now, the skyrmion can be characterized by these numbers, the Pointryagin number, which is called as the skyrmion number, and it is expressed in this expression here. It represents the number of winding from the core, and then we have the vorticity and the helicity, which is basically based on the orientation of the spins. On the basis of this, we can have derivatives of skyrmions, like the anti-skyrmions, which has skyrmion number as -1. Then we have biskyrmion, and then skyrminium with skyrmion number as 0. And then we can also have fractional skyrmion numbers, like in the case of merons. Then a biskyrmion and a skyrminium can be explained as the fusion of two skyrmions with opposite magnetization. Then there are numerous reports with experimental observation in bulk materials, then magnetic thin films and nanowires, and then other nanostructures as well. But the skyrmions are of interest because of its potential spintronic applications as information carriers, then quantum computing, logic devices, then data processing, neuromorphic computation, and so on. So the nanoscale size, the gyrodynamics, and the low driving current density makes it promising candidate. Then there are various type of devices that have been proposed in which geometry plays vital role in control generation and manipulation of skyrmions. Here you can see a device here, which is a hybrid device, and it is based on domain wall and skyrmion. So it has been shown that the transformation of stripe domain to skyrmions can be achieved by using the geometric constrictions. And then here, this is another work where they have shown that the skyrmion based logical operation by duplication and merging of skyrmions by the influence of notches and narrow channels can be achieved. They have shown the logical OR and application operation here. Then in another work here, we can see that how two different anti-notch can prevent coherent skyrmion generation. What they have done is they have introduced anti-notch with different dimensions to study this type of function in the device. And then here there is another work from nanolators. It shows device operation of reconfigurable skyrmion logic gate along with voltage controls. So my motivation of work was to generate deterministic multi-skyrmionic states from a skyrminium using different geometric designs. So here, as we can see that for the same simulations, we have used two type of systems. Like for the first one here is a single layer of magnetic thin film, which is on heavy metal substrate. And then here the second is the of synthetic antiferromagnet. We have a non-magnetic spacer layer, which is sandwiched between two magnetic layers. And then here you can see that there are three schematics that show the device dimensions. And here we can see this is for the device 1, this is for device 2, and this is for device 3. The device 1 is a simple single channel device, and the device 2 and 3 has a bifurcated narrow output lines, which is divided here, and here you can see as well. And then basically the device can be seen as the combination of three chambers here. So this is the source, this is the channel, and this is the detector. We nucleate the skerminium in the source, and then we allow it to translate through the channel, and then we get skermions in the detector. So moving on, we have used OOMP software for the micromagnetic simulations, and for nucleation we have used spin polarized current of value 2.5 mega ampere, and we have used these parameters. These are already used in previously reported works. So for translation we have used current in plane geometry, and we know that there arises a Skermion Hall effect when there is when a Skermion is driven through a nanotrack, and this happens due to the Magnus force. Now there are a few tricks to overcome this challenge, and in single layer thin film we have considered alpha equals to beta for that, where alpha is the Gilbert damping constant and beta is the non-adiabatic aesthetic coefficient. But the issue is this condition is not experimentally feasible. So we have taken the synthetic antiferromagnetic system with interlayer antiferromagnetic coupling strength of -2 picojoule per meter, which is considered as strong coupling. And here we can see that this is a schematic which shows the conversion of skerminium into skermions via domain walls. And as the skermions get injected into the narrow channel, here it gets converted into domain wall, and then after some time the former domain wall is pushed further and the later domain wall is injected into the channel. Clearly we need to have the channel width comparatively equal or smaller than the core skermion of the skerminium, and then we can see that the junctions in the device 2 and device 3 splits the domain walls, and ultimately when they pass out of the channel they are converted into skermions. Also we can see that the number of skermions we get can go up to maximum up to twice the number of output channels we have, and we can understand this from the table here. Here we can see that there are a number of skermions. The number of skermions we are getting in the system, like from 0 to 6 maximum we have got, because we have used 3 channels yet. So this is the table that represents for the 3 devices. This is for device 1, this is for device 2, and this is for device 3. And here we have for single layer, this one is for synthetic antiferromagnet. And in case of single layer, we are able to achieve all the intermediate states from lower to maximum, as you can see. But in case of synthetic antiferromagnet, either we get as many skermions as the number of channels or the twice of it. Then I have given a GIF of the translation. So this is for the single ferromagnet. Then here we can see the graph. This graph shows the increase in topological number as a function of time achieved in single layer for 3 devices here. And this second one is the graph that shows for synthetic antiferromagnet at different current density for different devices. Then we have this plot which shows the variation of skermion number and total micromagnetic energy only for the maximum number of skyrmions that we have achieved in the system as function of time for 3 different geometries. And as expected, you can see that the topological number of skyrminium initially is 0, and then it increases as we achieve the skyrmions in the system. So for device 1, we have 2 skyrmion number as 2, and then for device 2 we have 4, and device 3 we have 6. And then the same simulations we are trying to do for higher temperature, but we are facing issues in translating the skyrminium through the narrow channel. We are still working on it. And so lastly, I summarize that this type of device with efficient adjustability can pave way for advancement of skyrmion-based memory stores, spiking neuron devices, and other neuromorphic devices. Then hence, geometric-dependent generation of skyrmions enables few functionalities that may be inaccessible to conventional technologies. And thank you all for your attention. And this is my email ID. You may contact me if you need any discussion further.
Thank you, Adya, for the very nice presentation on this quant physics. Let's clap for him. I will request Subhankar to also join me because my hands are kind of stuck into many other directions. So
Thank you, sir. Thank you, sir.
Very nice talk.
Yeah,
Thank
thanks,
you,
Adya. So, are there any questions around? Not really. So, can we give a play, Subhankar?
Yeah. I think flag. Okay, I was just sharing the screen. Just a second.
Yeah, please. Okay. So here it goes. Symposium on Magnetism and Spintronics, SMS 2021 from NISA Bhubaneswar, India, takes immense pleasure in presenting the play to Mrs. In appreciation for being a valuable speaker to give a lecture on device geometry dependent deterministic skyrmion generation from skyrmionium. Thanks, Adya Shakti.
Thank you, sir. Thank you so much.
For a very nice presentation. So once again, we clap for
Very
you.
nice. Thank you,
Thank you,
Adya.
sir. Thank you, sir.
Okay, so with this, we move to our last speaker of the session, which is Mr. Aditya Kumar from University of Mainz. So I would request him to kindly start his presentation, which is about spin pumping with low spin orbit coupling material in C60 in a LSMO kind of heterostructure. So Aditya, would you please start your, we can see your slide.
Yeah. Hello. So good evening, everyone. In this talk, we will talk about spin pumping in a low spin orbit coupling material fullerene in a LSMO C60 interface. So yeah, first of all, a word of thanks to LNMM, where I did my master's thesis, and the work I'm going to present was done there. The guidance and the training I received was helped me a lot in my further career. And currently, I'm doing a research project at Johannes Gutenberg University of Mainz. And my current area of research is spin orbit talks and 2D materials. So yeah, let's get into our talk first. So here's me. When I joined the group, I was in 3rd year. So here's the photo I could find. Yeah. So first of all, before we go into the experiments and results, first let's discuss some basic fundamentals. First we'll go with magnetization dynamics, and then we'll take a look at some spin-dependent phenomena, and further we'll see what we have done. So if we place a magnetic moment in a magnetic field with slight inclination, what happens is the spin starts to precess around the magnetic field. And the frequency of precession is called Larmor frequency. So the motion of this magnetic moment in a material is governed by the Landau-Lifshitz Gilbert equation. And since the practical systems have damping, there is this damping term. And the alpha is called the Gilbert damping parameter. Higher is the alpha, higher is the damping in the magnetic system. The contribution of magnetic damping is due to various different phenomena. The first one is intrinsic, which is due to the material itself. And then there is, because of proximity, if you have some interface and a heterostructure-like device, and then the contribution from spin pumping, and throughout this talk will be mostly focusing on this contribution. And there is some contribution from impurities. Yeah, so let's take a look at the spin-dependent phenomena and Hall effects. So first of all is the basic Hall effect, where if you pass a current through a material in a presence of magnetic field, there is a transverse generation of voltage. And if you have a magnetic material and you do the same thing, you get anomalous Hall effect. In this case, the Hall voltage is much higher compared to in the previous case. Then we have spin Hall effect, which is if you pass a spin current through a material which has high spin orbit coupling, then you get a transverse potential generation. And no, you get like if you pass a current through a magnetic material, like a material with a high spin orbit coupling, this splits into a plus and minus spin, and we get a spin current in the device, in the material. So this is called spin Hall effect. And the last one here is inverse spin Hall effect. It's just the opposite of spin Hall effect. In this case, if we have a current and a high spin orbit coupling material, this charge current give rise to some spin current in the spin current, which is passing through our material, gives a charge current in the transverse direction and generates a voltage. So this converts a spin current into a charge current, which can help us a lot in detection of spin current, because and the conventional detection of inverse spin Hall effect is very difficult. Yeah. So there are, let's take a look at the various kind of spin currents that we can have. The first one is a basic simple charge current when there is no spin polarization. So the total spin current is 0. If you have some polarized current, then we can have some charge current as well as spin current. But if the spins are fully polarized, there will be charge current as well as spin current. But if there is some spin dependent phenomena and there is like no charge current, but still the spins flow in opposite direction, then you have a pure spin current. So pure spin current are like current really interesting in the sense that they can really minimize the joule hitting in any computational device. So spin pumping is a method of generating a pure spin current. In case of spin pumping, we make a heterostructure with a ferromagnetic material and a nanomagnetic material. And if you perturb the magnetic moments of ferromagnetic material using an RF field, the precession motion starts. Due to this precession motion, that creates additional angular momentum in the ferromagnetic material, which eventually dissipates into the non-magnetic material. This additional angular momentum causes some spin current in the non-magnetic material, which can be detected if there is some ISHG happening in the non-magnetic material. So yeah, first of all, for spin pumping, we need a good ferromagnet. An optimum ferromagnetic material for us, the spin pumping heterostructure should have a high saturation magnetization, low magnetic damping, high TC because we need it to be ferromagnetic room temperature, and should have a high spin polarization because that's interesting for spintronic related applications. LSMO is lanthanum strontium manganite is a popular ferromagnetic material. It's been used for like a long time. And the reason is it has doping level dependent properties, which we can really fine tune the properties depending upon the doping level of the material. It's very robust to corrosion, which comes in is robust to corrosion and a very high TC, which comes in handy if you want to do the experiments. And it also has a high spin polarization, which helps it which gives it applications in spintronics. Then there are like multiple spin pumping experiments have been done with the LSMO, and in a recent study, Gupta et al. Studied LSMO platinum interface, and they observed a very high spin pumping voltage of about 20 microvolts. And another very interesting phenomena they noticed was the anti-damping, like the magnetic damping, the Gilbert damping constant alpha was smaller for the bilayer structure compared to the monolayer structure. And if we take a look at the non-magnetic layer, for most of the experiments for spin pumping, heavy metals have been a very popular choice because of their high spin orbit coupling, due to which they are expected to give a very high inverse spin Hall effect voltage. But organic semiconductors have gained attention because as spatial layers and because of their high spin length. So in this work, we choose fullerene because it has curvature enhanced SOC, because, it has much higher SOC compared to other organic materials. And in a recent work, Gupta et al. Studied spin pumping in fullerene in a cobalt iron boron structure, and they found that it showed some ISHG voltage, some spin pumping voltage of 2 microvolts. So they showed that even the organic materials can also be used for spin to charge conversion. So eventually, with the focus of studying of damping in this damping and the ISHG, we chose our heterostructure to be LSMO and fullerene. Yeah. So our sample structure is we have LSMO of 1500 meter, and then we deposited LSMO using pulse laser deposition, and then we deposited fullerene using thermal evaporation method. So we did the experiment with the CPW based FMR device. Hello.
Yeah, please go ahead. I think there was some.
Okay. Yeah. So we did the experiment in a CVW-based FMR device, and to measure the voltage, we made silver contacts around the edges and there were connected nanovoltmeters to measure the inverse spin Hall effect voltage. So in FMR measurement, what we do is we set some RF frequency and then we vary the magnetic field. So in this case, we will get a Lorentzian-like curve, and if we fit it with a symmetric and an anti-symmetric Lorentzian, then okay. So somehow this is missing. Okay, no issues. So once we fit it with this, we get our delta H, which is FWHM of this curve. This is, and we will also call line width, and then we get the H resonance for all the frequency of RF field. Yeah. So to do the damping analysis, we did this at various different frequencies. So these are the plots that done at very different frequencies. We are the FMR plots at very different frequencies. By fitting with the symmetric and anti-symmetric, like symmetric, this Lorentzian function, we get the H resonance and delta H, which we can fit into the Skittle equation to get this gyromagnetic ratio gamma. And then once we have this gamma, we can substitute this into this equation on the right side and now we can fit our line width and frequency to get our Gilbert damping constant, which was our eventual goal to study the magnetic damping. So we did this for our both samples, one monolayer sample which only contains LSMO, and another one which has 50 nanometers of LSMO and 10 nanometers of C60. And we got the alpha for the single layer sample to be 0.006, and for bilayer sample to be this one, which is smaller than what we have for the single layer sample. And if you take a look, the value is outside of the error bars. That means if the damping is decreasing in the bilayer sample, and we are seeing some anti-damping like behavior. So the why anti-damping? Like how can the anti-damping happen? The reason can be that if the material is not good at dissipating the additional angular momentum, then what happens is the spin accumulation takes place close to the interface, and this spin accumulation causes a backflow of spin currents into the ferromagnetic layer, which can apply an anti-damping like torque and lead to the
12 minutes.
Okay, so to make sure that there is some spin pumping happening, we did the ISHE measurement, the angle dependent ISHE measurement, and we did the separated and did this fitting with this equation. And we found that the spin pumping voltage for bilayer sample was 2.26. And to ensure that this contribution is indeed coming from the non-magnetic, coming from spin pumping, we also did the ISHE for our single layer sample. So the spin pumping voltage for single layer, we found it to be 0.5 microvolt, and for the bilayer sample, it was 2.26 microvolt. So we can clearly see that indeed this ISHE voltage we saw is coming from spin pumping. This can be happen because of the curvature enhanced SOC, the sigma and pi orbitals, the intermixing of sigma and pi orbitals due to the curvature can enhance the SOC, and which can cause this ISHE in our system. Various other experiments have also been done, and they have observed that ISHE in C60 is much higher compared to other organic semiconductors. So conclusion is we observed anti-damping like behavior. We saw a decrease in Gilbert damping parameter after addition of fullerene on LSMO interface on LSMO as a ferromagnet. And then we confirmed that there is indeed ISHE happening inside our interface where fullerene is used as a non-magnetic material. And we obtained our spin Hall angle, but our spin Hall angle was much smaller for what we have already measured by Sarangi et al. And the exact mechanism behind anti-damping and the curvature enhanced SOC is not well studied, but requires a lot of theoretical work for, yeah, that's it. So thank you for your attention. And if you have any questions, I'm open to them. Hello.
Yeah, thanks Aditya for this beautiful presentation. I don't see any hands up there. Are there any questions? No, doesn't seem to be the case. I would request Shubhankar to join hands to clap for him. Shubhankar, if you can please. Yeah. So can we give his plug around? I will request Shubhankar to read it out for me to Aditya, because there's some network issue at my end.
Okay. I'm happy to present to Aditya this digital plaque. Symposium on Magnetism and Spintronics. NISA Bhubaneswar, India takes pleasure in presenting this plaque to Aditya Kumar. from Johannes Gutenberg University, Germany, in appreciation for being a very valuable speaker on his lecture. Thank you so much, Aditya. Very nice.
Thank you so much, sir, inviting all your guidance throughout my work.
Yeah, it's a pleasure. Thank you. So, Pushpendra, please share the digital plaque for Professor Indranil Sarkar. So, it is really my privilege and happiness to present the next digital plaque for our session chair, Professor Indranil Sarkar. I still see Aditya's, but mine does not change. Okay, so SMS 2021, Nisar Bhuvneshwar takes immense pleasure in presenting the plaque to Professor Indranil.
Okay.
Am I audible? So, yeah, am I audible now? Really? Okay. I'm sorry for this technical glitch. Okay, it's my really pleasure to present this digital plaque to Professor Indranil Sarkar. So I just read it. SMS 2021, Nisar Bhuvneshwar takes pleasure in presenting this plaque to Professor Indranil Sarkar from INST Mohali in appreciation for chairing the session. And it's really, Indranil, you have done a wonderful job. So we have about 15 minutes. So thank you, Indranil, for your excellent session chairing. So it was really nice set of talks. We will break now for 15 minutes, but on the same Zoom window, we will again continue after 15 minutes, so exactly 8 p.m. Indian time. And we have very exciting set of talks. So please stay tuned. Let's take a short break. Thank you so much.
Sir?
See you again.
Sir, this is Sogato. Hello?
Hello? Sogato?
Sorry, sir. Actually, I just wanted to confirm if I am audible or not because I'm using the mask. So it seems like it's fine.
No, it's fine. It's fine.
Okay.
So we will meet in 11 to 12 minutes. Okay.
Okay.
Okay. So please stay tuned all. Thank you.
Hello, Swagato. How are you?
Hello, sir. I'm fine. How are you?
I'm fine. Where are you now?
Sir, in the lab. So I am doing now my second postdoc, and now I am in Unitemix, the physics, this CNRS Thales lab, where Professor Albert Fert is also working. So I am working under him, kind of, so to say. He is not really a regular nowadays, but he comes like once or twice a week. And yes, it's very nice. The only problem is I have to be with the mask because I am in the shared office, so I cannot really open the mask.
Let's see. And how is your work going?
Sir, it's going good. In the previous work, so you will see the talk I will present today is mostly like the work I did in my previous postdoc. And we are now like writing the papers. I lost some time due to COVID because for like there was like almost 3 or 4 months where we could not go to the lab at all. And then there was like 4 or 5 months where we had like partial going to the lab like 2 or 3 days per week. So the publication got a bit delayed, but we have some really nice results, and now we are kind of writing. And so yes, and everything else is going fine. Sir, actually, I am also applying to different places. I will tell you about those later because everyone else is here. So
Sure. No problem. I see. Then in this session, we have Srijani.
yes, she is in home because she was preparing the slide this morning, so she wanted to stay back at home and present from there.
Okay, Srijani is there. I see. Then we have Swapna Sindhu.
Yes.
Where is he? Let us see. Yeah, he's there. Then we have Arup. Arup from Kansas. Let's see. He's there. Arup has I see. Then we have Biswajit. Biswajit is there. He has written Biswajit Sahu, scribe.
Good morning, Professor.
He's Professor. I see. Professor Sahu.
I'm not oh my God, I'm just a grad student, sir.
Really? You
Yes.
have managed to jump over the sun.
Oh, that's yeah.
Okay. We have one more, then we'll start. Okay, is Shavankar there? Should we start or? Shavankar, you are there? Purvasa is raising hand. No. So we should wait. Abhishek, Puspendra, Shakti.
Sir is here, sir. He will be just joining, sir.
Hello. Okay.
Hello, Vedang.
Okay. Shavankar, we start.
Yes, we start. Sorry, my iPad has some issue, so I'm joining from Pushpendra. Yeah, you please start.
Okay.
Yeah.
Okay, welcome everyone to this session 3 of this very nice symposium. The session has all ex-NICER students, PhD and masters. We'll start with Dr. Swagato Malik. So I request Swagato to start his talk.
I cannot share my screen. I need the permission from the host.
Abhishek, Pushpendra, Sakti. Yeah, no, now you can. They made you co-host.
Yes, so I don't know. Do you see
yes
in presentation mode? Okay.
Yes.
So thank you, Vedant sir, for the introduction, and thank you, Subhankar sir, for giving me this chance to talk about the work which I have been doing for last 2.5 years in my postdoc. So the work I will be presenting today was mostly done in my previous postdoc with Stanislas Rohart in Laboratory Physics des Solids in University Paris-Saclay. And then I will briefly mention about the work which I am doing right now in my present affiliation in Unité Mixte de Physique CNRS Thales, also under University Paris-Saclay. But before I go to the scientific part of my talk, let me briefly share some memories with you during LNMM days. So as you can see in all the pictures, I am smiling. So you can see that I was very happy during my PhD days. And I really saw the department as well as the group grow from a group of 20 people to 200 people. And it was a pleasure. We also saw the lab in the old Sainik School IOP campus to the new campus, and it was also a very pleasant memory. And I also have very fond memories with my supervisor, Professor Vedanta, and I am always thankful for his guidance during my PhD work. And you can see here, where is my pointer? Sorry. In the left hand side, this is during my PhD defense. And also I got the Outstanding Student Award from HBNI for my PhD dissertation. So without any further ado, let me go back to the topic today. I'm not going into the details of skyrmions anymore because in the previous section, people have already introduced what is skyrmion and what is the use of them. Briefly, I will tell you when you write the micromagnetic energy of a system, you have the exchange term, then you have the anisotropy term, and then you have something called DMI, which lowers the overall energy of your system. And if you solely concentrate on the DMI term, so basically when you expand them, you can see for depending on the sign of D, you have either clockwise or counterclockwise rotation of spin. And this kind of introduces a spin orientation with a fixed chirality in your system, which stabilizes this skyrmion. And you can define skyrmion by this equation, which is either plus or minus 1, depending on the polarization. Now, before going to my work, briefly to tell how to stabilize skyrmion in magnetic thin films. So when you write the domain wall energy only with the presence of DMI, you can write them like this, where you have A as the exchange term, K effective as the effective anisotropy, and then you have minus pi D from the DMI energy. So basically you compete between two extreme cases. When your domain wall energy is very large, then you have the skyrmion collapse and you cannot stabilize them. And when this is very negative or large negative, then you need significantly high magnetic field to assess or access the isolated skyrmions. So the common tricks is to reduce the anisotropy energy as much as possible. So this you can do by working near the spin reorientation transition thickness, and then you can stabilize skyrmion. And this is a typical representation of a skyrmionic loop and the domain structure. So you have a hysteresis loop where you have the nucleation in the negative side, and in this slope you can stabilize skyrmion. So basically this is in the demagnetized state, you see the 1D stripe phase, and the more and more applied field you apply, you delete the stripes and stabilize skyrmion at high field. But you know, to to really implement this cosmionic device in real device applications, you need to eliminate the necessity to apply some external magnetic field to stabilize them. So this is going to be my first part of this talk, how to stabilize fermions in zero field. Then also I will show you how you can use low pinning materials for lower power consumption to move the fermions, because that is also a crucial aspect of racetrack memory applications. And then I will briefly talk about my present work where we are trying to improve the fermion dynamics using compensated magnetization systems, so namely the synthetic antiferromagnets and ferrimagnets. Now, in the sample structure I took, it was a bilayer cobalt thin film, which is separated by a gold special layer. And here you can see all the energy, all the interactions. So basically you have domain to domain wall interaction, which is known as the dipolar coupling. You have a flux closure mechanism. And because these are the nil wall, so you have charges stored in the opposite side of the wall. And so you have a positive contribution of dn, which is given by this red arrow. And then also you have interaction between domain wall to domain wall. And this is this. And when you have the special layer thickness smaller than the domain wall width, these two terms cancels each other. And then you have an extra term due to the dipolar coupling, which is coming from the domain interaction with the domain walls. So basically this helps you further to reduce the domain wall energy of your system. Now, in order to stabilize fermions in zero field, the trick is, here you can see you need to take d value less than 1. This is known as the critical DMI parameter to stabilize isolated fermions. So this you can do by increasing the anisotropy energy, but you need to take care that you cannot increase the anisotropy energy significantly that you collapse the fermions. So there is a really fine tuning, and because you have two additional negative energy terms, so you gain some freedom in the bilayers to increase the anisotropy energy and still be in the fermionic phase. Now, here you see it, this is the sample structure. So I have two cobalt layers, and which is separated by a gold special layer of 3 nanometer. And when the cobalt thickness is near the spin reorientation transition, so the anisotropy in my system is very low, and we can stabilize fermions in some applied magnetic field. But as soon as we release the magnetic field, because in remanence, I lose magnetization of my system, so it goes from the fermionic phase back to the 1D stripe phase. So this is not something what we want. Now I will try to increase the anisotropy energy of my system by reducing the thickness of the cobalt layer. So here you can see when I go from 1.55 nanometer to 1.4 nanometer, I stabilize fermions in some applied magnetic field. But when I go back to zero field in the remanence, I still have some textures. Obviously, the size has elevated a bit because you do not have any curling energy to confine the fermions. And I will show you in the next slide that even with this 1.4 nanometer film, which shows in the static measurement that you can really stabilize fermion at zero field, is not enough for the dynamic part. So this is my device structure, how they look like. So there I have titanium gold contact with point-like contact, and one end I have the flat electrode. So this design I used to have more spin accumulation and heating effect near the point contact of the track. And here in the blue, I have the track of my cobalt bilayers. So when the cobalt thickness is 1.45 nanometers, so here in the static mode, we see that we can stabilize fermion at zero field. But you see, when I apply some current to it, I have nucleation everywhere, and the fermions kind of merge with each other. So it's not good. So I cannot have motion or nucleation of individual fermions. When I reduce the thickness even further, I have a little bit better result. I have most of the fermion accumulation near the point contact, but still they kind of merge with each other and go back to the stripe phase. Then we reduce the thickness of the film even further, and now you see really we are blowing some real fermionic bubbles, and which is coming from the vicinity of the point contact, and they are going in the upside, which is popularly also known as the fermion Hall effect. And you can see with the opposite pulse sign, I have opposite polarity of the fermion, and also the fermion Hall effect in the opposite direction. So this is also an indirect proof that these are fermions and real topological entities. Sorry. And these are some dynamic measurement, and you can see we can achieve skyrmion velocity up to 80 meter per second at some current density of 1.2 into 10 to the power 12 ampere per meter square, which is in the acceptable range of the literature so far. So here I show you that we can really nucleate and move skyrmions even in the existence of magnetic field, just by the trick of reducing the thickness of the ferromagnetic layer to increase the anisotropy of the system. In the next, so these are the samples we received from Niger, Bhubaneswar, and this is a collaborative work with Bindamon and Subhankar sir. So here you can see we have single layer of cobalt iron boron, and the loop is skyrmionic. But immediately what you see, the immediate difference from the previous slide, is that the contrast of the texture is reduced significantly. This is because the magnetic tip which I use for the MFM measurement is the lowest possible magnetization. So this means if I reduce the magnetization of the tip anymore, I cannot see any contrast. But still, you see, when I zoom into the features, I have some perturbation in the scan axis. So basically, I scan with my MFM tip in the x-axis, and you can see some perturbation. So this kind of signifies that the texture are very loosely bound with the background, which is an indication that the sample may have low pinning, and so it should be helpful for the dynamic measurement. And indeed, when we move these skyrmions in the track, we can see that our in this work, you see from this table, we can move the skyrmions really at 8 into 10 to the power 10 ampere per meter square, which is significantly low than the existing literature, and we can move them like up to 50 meter per second. So this has been a significant improvement in this field, because now this cobalt iron boron can be the new material for the building block for future works regarding skyrmions, and this work is under review now. And now I go to the topic which I am working right now in my present lab. So I am here working on ferromagnet. So this is a very boring slide. I will just give you a short gist what is important about the ferromagnet. So you see the switching time is ratio of total angular momentum with applied spin current. So either you decrease the applied spin current, or either you increase the applied spin current or you decrease the angular momentum to increase your switching time. But then there is a certain limit up to which you can decrease the applied spin current, but you can reduce the total angular momentum if you have antiferromagnetic coupling, and two lattices exactly opposite to each other. So the antiferromagnets are best for this purpose. However, there is some problem with antiferromagnets, is that they are mostly insulating in nature and they are not very good for dynamics. And also you cannot use conventional techniques which you use for ferromagnets. But in case of ferromagnets, you have both this freedom. So you have two oppositely coupled lattices, ferromagnetically coupled, but they have reduced magnetization in their system. So you can really achieve angular compensation, and you can move them in very high speed. So these two are basically the main papers, which is the kind of the motivation of my work in this postdoc. And for this work, we take rare earth transition metal based ferromagnets, which is like terbium cobalt or gadolinium iron cobalt used for my work. I will briefly show you some initial results. So here I have a multi-layer of platinum, cobalt, terbium. You forget about everything else. So this is the most important part. So cobalt and terbium, because of their intrinsic electronic structure, they should have opposite spin alignment, and that is why they should cancel the magnetic moment of each other and lower the magnetization. So here you can see I have prepared some samples by varying both the cobalt and terbium thickness from 0.2 nanometer up to 1.5 nanometer. And you see from this curve that irrespective of the cobalt thickness, when my terbium thickness is more than 0.4 or 0.5 nanometer, I have a significant drop in magnetization. And also in the left hand side, you can see the same information. However, these dotted lines, what you see are the samples where I could stabilize skyrmions. I would really like to stabilize the skyrmions in these samples where the magnetization is very low for the dynamics, but unfortunately I still don't have them, and I have to increase the DMI by some means. However, right now we will be working in this region where the magnetization is low. And you can see a typical skyrmion stabilization here with applied field. We can stabilize really low diameter magnetic skyrmions like 80 nanometer. And of course, the next step is moving the skyrmions with the current pulses. We already have the designs. It's just a matter of time. And this is another topic where we are using the ferrimagnetic gadolinium iron cobalt. So this is basically a ferromagnet heterostructure. So there is a paper which has been published in 2021. They say that the spin current coming from the in-plane magnetized gadolinium iron cobalt is 80% more efficient than the conventional platinum cobalt based heterostructure. So we want to use this ferrimagnet as a spin source and to move the skyrmion in the ferromagnetic heterostructure. And in this one also, you can see that we have stabilized skyrmion from the demagnetized state by applying some field. And this loop, you can see we have the skyrmionic loop, which kind of saturates near 100 millitesla. And then you have some tail, which is giving you the in-plane magnetized, coming from the in-plane magnetized gadolinium iron cobalt. So we know that our gadolinium iron cobalt is in-plane magnetized, and we have the skyrmionic heterostructure because we can stabilize skyrmions. Now again, the next step is moving the skyrmions with some current pulses. So this basically summarizes all the results. We have successfully stabilized the skyrmions in absence of external field. This is very important for the specifically the antiferromagnetically coupled systems like synthetic antiferromagnets, where we will be using where we can stabilize the skyrmion even without a bias layer. We also observe very low threshold current density to move the skyrmions in cobalt iron boron based heterostructure, and we have stabilized the skyrmions in rare earth transition metal based ferrimagnets. We will move the skyrmions hopefully soon. I want to thank the team. So this is the team in LPS, so Sujit, Stanislas, and Andre. And this is my current team in UMP, where Nicola, Karim, Vincent, and Albert, we are working together. And we also have some collaboration in Institut Jean Lemore in Nancy, France, where Eloise, Michel, and Juan Carlos is helping us. And also we want to thank Brindavan and Subhankar sir for providing us with the cobalt iron boron samples. So thank you everyone for your attention.
Thank you, Swagata. Very nice talk, nice work. Now it's open for some questions, comments. You can raise your hand and then any questions to Swagata.
Swagata, very quick question. This gadolinium ferrite,
yes,
you say it is like having in-plane magnetized, in-plane magnetization, so to say.
Yes.
So I didn't understand when you talk about spin current. So are
Yes.
you
Sir,
like
actually,
applying some kind of like charge current to make spin Hall effect, or?
So this is basically the self torque of gadolinium iron cobalt. So basically what we do is we use the gadolinium iron cobalt as the platinum layer. So basically, depending on the magnetization of gadolinium iron cobalt, you have something very similar what you see in platinum. So the spin current will come from the gadolinium iron cobalt, and then we'll have the SOT effect on the ferromagnet. Now why we use this? Because they say that the self torque from gadolinium iron cobalt based system is 80% more efficient than the platinum or platinum based structures. So basically the gadolinium iron cobalt here is just a replacement of platinum.
Okay. Thank you.
Okay. I don't see any other hand raised. So Swagata, thank you very much for this nice talk.
Thank you.
Okay. So Mohanty, there is a small memento for him.
Okay.
So you kindly read it.
Okay, here is the memento for Swagata. It is from the Symposium on Magnetism and Spintronics at NICER. Let me see if I can read the text. Can you make it big? I'm getting old. So, okay, it takes immense pleasure in presenting this play to Dr. Swagata Malik. And in appreciation of being a valuable speaker to give a lecture on deterministic nucleation and efficient motion of skyrmions. So Swagata, this is your...
Thank you. Thank you very much, sir. Thank you.
Thank you. Now let's move to the second talk. It is by Dr. Srijani Malik. Srijani, can you hear me?
Yes, and am I audible too?
Yes, you can start sharing. Nice to see you after a long time.
Yes, nice to see you also. it actually feels very nice to be with the LNMM family after a long time. So should I begin?
Yeah.
So thank you very much for your introduction, and thank you to Shubhankar sir also for giving the opportunity to present my work in the conference. So it's really nice to be back with the LNMM family, and where I did my PhD on spin interface with fullerene, as you can see from these. And these are some photos of my PhD defense. But and I really want to thank Shubhankar sir for all his support and guidance which I got during my PhD. So but this is not the only thing the only memory I had from LNMM, because we had a lots of fun during work as well as during numerous dinners and lab outings, which made my stay at LNMM really beautiful. So now I am a postdoctoral research fellow at CNRS Thales and working in the group of Dr. Manuel Vives. And today I will show you some of my recent results on spin to charge conversion in different oxide heterostructures. So of course, the works I am going to present is not done by me alone. So these are the group members from our lab who helped substantially in my work, and also the collaboration from SpinTech. And I also work with the Intel company. So this is the Intel team with which I am working. And now I want to start my presentation by showing you this graph of the power consumption of information and communication technology. So currently we are here, and the prediction tells that in about 9 years, the ICT will consume almost 20% of the whole world's electricity. So of course, this is impossible and non-sustainable. So all the ICT companies, they are looking for a possible solution to mitigate this issue. And a couple of years back, Intel proposed a solution called magneto-electric spin orbit logic device, in short MISO device. And I will briefly show you how the MISO device works. So the core of this device is a ferromagnetic material, and if you, let's say, pass a charge current through a interconnect, and if the ferromagnet is coupled with a magnetoelectric element, then through the magnetoelectric coupling, you can switch the magnetization of the ferromagnet. This is the writing part of the device, and for the reading part, we rely on the spin orbit effect. So if a current is passed through the ferromagnet, then in the spin orbit material, we have a spin current. And due to the advantage of spin to charge conversion in the high spin orbit material, we can have a charge current as output. And now, depending on the direction of the magnetization of the ferromagnet, we can either have positive or negative output current. So I am working with Intel in the readout of this device, where we are trying to find the most suitable candidate with oxide heterostructure to have the highest spin to charge conversion in the readout section. So we will be mostly relying on the Rashba spin orbit coupling, which enables the opportunity to achieve spin to charge interconversion. And the Rashba effect is the manifestation of spin orbit interaction where the spin degeneracy is lifted due to a symmetry breaking electric field. So this is the Rashba Hamiltonian, and if we introduce this Hamiltonian in the main Hamiltonian of the system, then we have the lifting of the degeneracy of the bands. So basically, we have two Fermi contours with opposite chirality. And in such kind of system, if we pass a charge current, then the Fermi contours will shift in the K space, and this is why there will be some spin accumulation generated, and the accumulation in the inner contour and the outer contour are not same in the quantity, so they cannot compensate each other, and finally we will end up with a finite spin accumulation, which can also pass through the adjacent layer. So basically we have a charge current to spin current conversion, which is a direct Edelstein effect. And inversely, we can also have indirect Edelstein effect, where let's say in the same system, by spin pumping, we directly inject a spin density. And if we inject a spin density, then the Fermi contours will shift in opposite direction. And the shift for the inner contour and the outer contour are not same. So therefore, we will end up with a finite delta K, which will generate a charge current. And we will be mostly relying on this inverse Edelstein effect for our samples to measure the spin to charge conversion. And the most important factor is the figure of merit, that is the lambda. And this is very important to remember that the lambda depends both on the Rashba coefficient as well as the momentum relaxation time. This will be very useful for the rest of my talk. Now to form a 2D electron gas. So the conventional idea, like since a long time, was we could achieve 2D electron gas at the interface of two insulating perovskites, let's say strontium titanate and lanthanum aluminate, but this involves high temperature PLD growths. But then a few years back, the group of Andre Santandar, they showed that just by depositing a few angstrom of aluminium at room temperature on the STO, actually it is possible to achieve 2D electron gas at the interface. So if it is possible by aluminium, then probably, of course, by other metals also. So basically, it's nothing that the metal is taking out the oxygens from the STO and creating oxygen vacancies and thus forming the 2D electron gas. So the criteria to achieve this reduced STO is that the work function of the metal has to be lower than the STO, and the enthalpy of formation of metal oxide has to also be lower than STO. So when we deposit such kind of metals on top of STO, then basically it pulls out oxygens from the interface of STO. The metal becomes metal oxide, and at the interface of metal oxide and STO, we end up with the 2D electron gas. So this is the experimental facility I have used to prepare my sample. This is the sputtering, and this is in situ connected with the X-ray photoelectron spectroscopy, which I have used to measure the valence state of different materials. So mostly I have used two types of sample structure. So just the metal on top of STO for the characterization of XPS and transport. And when I did the spin to charge conversion study, then to do a spin pumping, I must need a ferromagnet. So for that, I have used the nickel iron. So let's begin with the results. So the in situ of this graph is showing the XPS spectra for the bare STO substrate. So we have nothing, just the STO substrate, and from here we see only the titanium 4+ valence state of the substrate. This means no oxygen vacancies. Now when we deposit just 4 angstrom of aluminium, we already see evolution of another peak corresponding to titanium 3+. So this means oxygen vacancies are created in the sample, and as we increase the thickness of aluminium, we see more and more oxygen vacancies are created. And this we also see similar kind of effect with depositing tantalum and yttrium. For all the cases, we have titanium 3+, this means oxygen vacancies. And then we take out the samples, oxidized outside in the air, and then repeated the XPS measurement. So for the thinner samples, you can see the intensity of the peak is getting reduced. This means the TUDEG is getting oxidized by exposing to the air. But let's say for the thicker samples, for this case, the intensity is not changed. So this means we could preserve the TUDEG even after exposing the air. So with very less thickness of the metal, we can already achieve the TUDEG, but to preserve the TUDEG, we need a finite amount of the metal. And this is what is summarized here in this plot. So for different materials, basically how much thickness we need to protect. And in case of yttrium, we saw that still like beyond 1.5 nanometer, still we are having this oxygen vacancy creation. This means the highest reduction of STO is observed for the yttrium in compared to aluminium and tantalum. And this is this analysis is in well agreement that the oxygen formation enthalpy of yttrium is lowest. So this likes to get oxidized a lot, and this is why it continuously pulls out oxygen from the STO substrate. And then we have measured the samples, the transport properties for all the samples. All the samples are very nicely metallic down to 2 Kelvin. So this means we have formation of nice 2D electron gas in all the samples. And we did Hall measurements to calculate the carrier densities. And in this case, we saw the highest carrier density in aluminium and lowest in yttrium. So this trend is not matching with what we got from the XPS, because I just said that with yttrium we are having the most reduction in STO. So this means that the higher reduction does not always lead to higher concentration of carriers, because it also depends on the diffusion coefficient of the native oxide. So yttrium likes to get oxidized, but the yttrium oxide is also not very well protective layer to protect the 2D. This is why we have very less carrier density in compared to aluminium. And now we deposited nickel iron layer on top of the sample and did spin pumping measurement. So basically at the ferromagnetic resonance, when a spin current is injected in the 2D due to the inverse Edelstein effect, we have a charge current in the transverse direction, and we are measuring this voltage in the transverse direction. And these are the spin pumping data. So these are the ferromagnetic resonance data with respect to different backgate voltages. So basically we are tuning the Fermi level of the STO band structure by changing different backgate voltages. And from here we can see very nice symmetric signal of voltage exactly at the ferromagnetic resonance. So we have quite efficient spin to charge conversion in our system, and the amplitude as well as the sign of the spin to charge conversion is changing with respect to the backgate voltage. So this is quite nice, because we can control the sign of the conversion as well as the amplitude just by changing the Fermi level position in the STO band structure. And this is because like there are positions in the band structure where the Rashba splitting is much higher, so we expect very large amplitude of spin to charge conversion here. And then there are some bands where due to different orbital character we have negative Rashba coefficient. So this is why we can also have the negative sign of the conversion. And then when we measured for all our samples like aluminium, tantalum and yttrium, the same spin to charge conversion, they are similar in nature, I would say. And then we like to have a better comparison, we plotted them together. But here we have to remember that we have to shift the backgate voltage axis to have the carrier density of all the samples corresponding to each backgate voltage at the same point. Then only we can compare the samples. And from here we can see the highest spin to charge conversion is observed in case of aluminium and the lowest in case of yttrium. So here you have to think about what I said in the beginning, that the efficiency depends on both the Rashba coefficient as well as the momentum relaxation time. So here the Rashba coefficient is the same for all of them because they are all STO2 days, but the tau is not the same. The tau effective is the tau of the 2D electron gas as well as the tau escape, which is the possibility for the electron to leak out of the 2D. And I already showed you that yttrium oxide is not a good barrier to protect it. So this is why the electrons are escaping, and this is why finally we are ending up with less spin to charge conversion efficiency. And now this is about STO2 and very quickly I would like to introduce to another oxide system with 2D electron gas, that is the potassium tantalate. In principle, KTO and STO, they have many similarities, like it can become metallic upon minute electron doping, and also we can have the 2D electron gas exactly in similar way like STO by depositing lanthanum aluminate or lanthanum titanate. So we did exactly the same thing in this case. One thing I must say, that KTO has tantalum, which is a 5D element. So we think that the Rashba spin orbit coupling in KTO should be much higher than the STO2 days. So in these samples also we did exactly the same thing. We deposit aluminium on K2, and by the redox reaction, we have formation of 2d electron gas at the interface of aluminium and K2. And this is the room temperature RPS data, where we see very nice band structure of K2, quite like multiple bands forming. And also from the transport, all the samples are metallic, and we calculate the carrier density and the mobility from the Hall measurements, where the carrier densities are similar to the aluminium STO samples, but the mobilities are little bit higher, but more or less comparable. And then we also perform spin to charge conversion in these samples. Here we still have not done the gate dependent study. This is yet to be done. But here also we see quite efficient spin to charge conversion, and also by changing the magnetization direction, we can have either positive or like positive or negative spin to charge conversion. This is what actually we wanted for the meso device, like by changing the magnetization direction, changing the output current. So this is quite nice and promising. But the estimated Edelstein length is comparable to LAO STO, but less than the aluminium STO 2 So we need to work a bit more and increase the tau to have higher mobility sample. The good thing is the Rashba coefficient is much higher, but the tau is still less. So, but we are very hopeful that we can achieve very high spin to charge conversion with the KTO 2 With this, I think I am already out of time, so I will just display the summary slide, and just I will tell that our findings are very important to tune the correct material and the correct condition to have higher spin to charge conversion for the meso device with Intel. And thank you very much for your kind attention.
Thank you for this very nice talk, Srijani, and so many very interesting measurements. Now it is open for 1 or 2 questions or comments. Anyone? You can raise hand.
I have one small question.
Yeah, go ahead.
Isn't it this, I think 2-3 slides back when you saw the ISHE data. So I think if you go back.
This one.
I think here. So in the y-axis is which unit millivolt dot G to the power -2.
Yeah, this is basically the voltage.
And what is G?
This is the magnetic field Gauss.
Oh, this is Gauss. Okay. Okay.
Yeah.
Okay. So if you plot it, so it is basically the voltage is millivolts, the amplitude.
Yeah, the voltage is millivolt. Yes.
Oh, okay. That's really significant voltage because we observe in microvolts.
Yeah.
And most of the people.
Yes. This is very significant. Actually, okay, I must say all these measurements are at 15 Kelvin. And when we do all these measurements at room temperature, because the 2D electron gas can work very nicely in the low temperature, but at room temperature, the spin to charge conversion efficiency is much lower. But still, because finally we are like finally we want the voltage, not only the current, but the resistance of the 2D electron gas is much higher at the room temperature. So finally, even if we have less current through the spin to charge conversion, the product of the resistance and the current gives very high voltage. So at room temperature, so far we have got for aluminium STO 10 millivolt of output. This is so far we have got.
Wow.
But to work with the meso device, the challenge is we have to reach 100 millivolt. So we are still working with this. I don't know how much will be possible, but it's
that's very interesting.
in good direction.
Yeah, good. Thank you.
Yes. Thank you, sir.
Okay. So let's thank Srijani again for this very nice talk, and all the best, Srijani.
Thank you.
Okay. So there is a flag for you all there. Yeah. So can you make it bigger? Okay. Symposium on Magnetism and Spintronics at NICER takes immense pleasure in presenting this plaque to Dr. Srijani Malik. in appreciation of being a valuable speaker to give a lecture on two-dimensional electron gas for spin to charge conversion. So thank you, Srijani, for
Thank
giving
you.
this
Thank
talk.
you, sir.
Yeah, very nice words, Srijani. Thank you.
Okay, so let's then move ahead. I think next is Arup Behra. Arup, you are there?
Hello. Hello, Vedanta sir.
Arup, today is your birthday.
Yeah.
So happy birthday from all of us.
Thank you.
How is your guitar?
Yeah, I'm still playing. I find time to work with my music also. Yeah.
Okay, let's get started
Thank
with your presentation.
Let me share my screen. Can you see my screen?
Yes.
In the presentation view?
Yes.
Not in the like double presentation view, right?
No, we can
Okay.
see. Yeah.
Okay. Thank you, Vedanta sir, for the fun introduction, and thank you, Subhankar sir, for inviting to give a small talk on what on my recent work. So I would like to give a breath of fresh air to the community here, because lately I've been working on electrical systems, not technically not magnetic systems. So I would like to present my recent work titled Two-Dimensional Heterostructure Field Effect Transistors with One-Dimensional Contacts, leading to enhanced electrical performance in and ultra-low noise. And this is a collaborative work between Kansas State University, SINTEF in Norway, and Center for Integrated Nanotechnologies in Albuquerque, New Mexico, which is a branch of Sandia National Laboratories. Before moving on to the talk, I would like to give a brief background. I was actually having a tough time finding a good picture, and today Subhankar sir posted this photo on Facebook, wishing me happy birthday. So I was like, okay, this is a good photo to put on the slide. So I did my master, like integrated MSc at NISER in School of Physical Sciences from 2013 to 2018. And during the time of 2017 to 18, I worked with in LNMM under the guidance of Subhankar sir, and I performed simulations there on magnetic materials. And right now I am a PhD student at Kansas State University. And after I've completed all my coursework, I'm actually a visiting student researcher at SINT in Sandia National Laboratories in Albuquerque, New Mexico. Here I perform low frequency electrical noise characterization on different two-dimensional materials. So a brief background on what I perform, what the studies that I did at LNMM are like. The first one is one second. The first one was to study the Skyrmion statics and the stability at different DMI and anisotropy values, starting from a bubble state, which got published in Jeopardy Applied Physics. And the second one was actually inspired from a talk presented by Dr. Saugata Malik when he was a PhD student under Subhankar sir, and he was studying domain nucleation in triangular antidot arrays, and that gave me an idea of can we create skyrmions from triangular antidot in a racetrack geometry with DMI, and it was a collaborative work with Dr. Chandrasekhar Murapaka from IIT Hyderabad. So moving on to my talk, recently there have been a lot of developments in two-dimensional van der Waals materials. That like the OG was the graphene, which is two-dimensional semi-metal. And recently there have been discoveries in two-dimensional semiconductors like MOS2, molybdenum disulfide. There are two-dimensional magnets like CRI3 and FGT, two-dimensional superconductors, two-dimensional metals, and two-dimensional insulators. We can actually use a combination of all these materials to work around to make fancy devices and to make fancy working devices, basically. So the paper that we published was mainly focused on graphene. So graphene, which is like a very flat, two-dimensional, atomically thin material is a fun material to work with, because you can actually use like a basic cello tape or scotch tape, and you can actually mechanically exfoliate single layer graphene flakes. And graphene has very high electrical mobility and very high thermal conductivity. And the way we electrically characterize such material is by fabricating field effect transistor structure, which has like metal source and drain, and then there is a gate which source and drain provides field for carriers, charge carriers in the channel to conduct, and the gate provides actually modulates the amount of the number of charge carriers in the channel, basically making it a switch. And this high electrical mobility in graphene is attributed to its Dirac conical type for the band structure. And when you actually modulate the gate voltage, you actually play around with the Fermi level around the Dirac point, leading to ambipolar transport. But interestingly, if you encapsulate graphene with the two-dimensional insulator, which is hexagonal boron nitride, if you encapsulate that and encapsulate the graphene channel in that, people have actually seen mobility values of around 100,000 centimeters square per volt per second, which is around 20 times higher than what graphene shows on bare silicon dioxide. So moving on, for the low frequency noise, I mean, noise is noise. Like, people perceive noise as noise. It's like something unwanted, but noise is a thing which we can use to characterize. If we study low frequency noise in a particular way, we can actually use it to characterize how noise is originating in the channel, and that leads to understanding what are the different scattering mechanisms that carriers undergo while moving around in the channel. So noise has been historically explained through two models. One is mobility fluctuation model, where there is the mobility in the channel is fluctuating, which is leading to the noise. And then there is number fluctuation model, where the actual number of carriers in the channel are fluctuating, which leads to noise. And noise is characterized by this noise amplitude, which is given by alpha h over n. Alpha h is actually huge parameter. And SI over here is noise spectral density, I is current, and F is characteristic frequency. So recently, noise studies on graphene have shown that the noise coming from the noise that we measure in a graphene channel actually comes from the contact region underneath the metal contact, and not from the channel. And that has been attributed to current crowding underneath the contact region. But it has been shown that if you can reduce the contact length in such a way that if the contact length is less than the transfer length, then that leads to uniform injection and not crowding, and that will lead to the noise studies. That will lead to possible noise studies in the channel. And then there was a study where they showed the noise coming in encapsulated graphene is much lower than the noise coming on graphene fabricated on SiO2. So here in our work, what we have done is we have used a viscoelastic stamping method to stack boron nitride graphene and boron nitride. Here is the complete heterostructure. And then we used E-beam lithography and metal evaporation and reactive ion etching techniques to fabricate a Hall bar structure. And then here you can see the scanning TEM images and the Raman spectra. And here, then we moved on to measuring the electrical conductance of the device, starting from room temperature all the way down to 80 Kelvin, like liquid nitrogen temperature. And you can, and here is the corresponding resistivity plot. Here you can see that there are actually two regions where the resistivity behaves as like a metal away from the zero gate voltage, which is we call as charge neutrality point. And at charge neutrality point, it behaves the opposite way. And if we extract the mobility of this device, you actually confirm that this thing is actually true, and there is a region between the mobility peaks where the conductance is explained in a different physics than the diffusive transport away from that region. We actually focus on the region away from the neutrality point, as we are still trying to figure out what is happening in our noise measurements in this region. So here is a noise spectral density measurement as a function of frequency at different temperature. You can see that noise spectral density behaves linearly with frequency with a slope of -1. Like this solid line has a slope of -1, and here is the extracted slopes of these noise spectral density. And you can see that away from that region, we have the slope lying well between -1.2 and -0.8, which is in agreement with what people study in noise. So to understand what is happening in the channel, we actually model the resistivity in the graphene channel as a 4-scatterer problem. The first rho 0 is actually coming from short range and short range scatterers, which are like basically defects and electron-electron scattering. And then there is long range Coulombic scatterers, which are like trapped charge in substrate and stuff. And then rho A is actually longitudinal and acoustic phonon scattering, which is actually the scattering happening between electrons and phonons in the graphene channel. And the rho RIP is remote interfacial phonon scattering, which is like the electron phonon scattering interaction happening from between the electrons in the graphene channel and the phonons, the polar photon modes from the HPN substrate and the encapsulating layer. And these are the corresponding formula. So what we actually found by doing that model is the remote interfacial phonon scattering is a dominant. These are the corresponding fits at different gate voltages for our device. And what we found is the remote interfacial phonon scattering is dominant above 200 Kelvin. And you can see that in this figure, the black curve is corresponding rho contribution to the remote interfacial phonon scattering, and the red plot is the contribution to from the acoustic phonon scattering. So you can see that below 200 Kelvin, the acoustic phonon scattering is dominant, but above 200 Kelvin, the remote interfacial phonon scattering just shoots up. And rho 0 is anyways temperature independent. So from obtaining all these, all the resistivity contributions, we actually used a 2-scatterer noise model to explain our obtained noise amplitude, which we show here from room temperature all the way to 80 Kelvin. We actually use this 2-scatterer noise problem, I mean the model, to explain why the noise behavior switches from a V shape or an M shape to a delta shape from room temperature to low temperature, which has been an outstanding question for like last 5-6 years. The Hooch parameter, which I mentioned earlier, alpha H, is a very important parameter for noise studies in field effect transistors. Whose parameters have been shown to lie between 0.01 to 0.001, like 10 to the minus 2 to 10 to the minus 3. In our studies, we have got extremely low Hooch parameter, which lie between 10 to the minus 4 and 10 to the minus 5, which is like a pioneering thing in the field. But interestingly, we can use this Hooch parameter to actually find the trap states underneath the graphene channel. So we fitted the Hooch parameter in the occupation of trap states model to actually find the trap states in which charge carriers get trapped from the channel, and we found that they lie between 0 to 20 milli-electron volt. And recently theoretically it has been shown that actually encapsulating graphene with boron nitride actually opens up a band gap of 180 milli-electron volt. So our results are in complete accordance with what they have predicted. And actually the trap states get depending on the type of carrier and the gate voltage, the trap states below the conduction band or the valence band get occupied as the devices function, as we work with the device. So in summary, we have we have fabricated field effect transistors with two-dimensional van der Waals material heterostructures with HBN, graphene HBN, and one-dimensional edge contacts. I think I forgot to mention that, but yeah, they have one-dimensional edge contact, because having one-dimensional edge contact will give us transfer length higher than contact length. That would lead to uniform charge injection. And then we characterize the temperature dependent transport, and using that characterization, we actually figured out what are the different scattering mechanisms in the happening in the channel. And using those scattering mechanisms, we actually were able to explain the transition of the noise amplitude from an M shape to a delta shape behavior from high temperature to low temperature, which was an outstanding question for the last 5-6 years. So with that, I would like to conclude my talk. Thank you for listening. And
thank you, Arup, for this nice talk. Now, if there are any questions, comments, suggestions, you can raise hand, or you can also directly ask. Okay, looks like it was a clear talk. So there are no other questions, comments. So thank you, Arup. Here is a memento from Symposium on Magnetism and Spintronics. It at NICER takes immense pleasure in presenting the plaque to Arup Kumar Behra in appreciation for being a valuable speaker to give a lecture on two-dimensional heterostructure field effect transistors with one-dimensional electrical contacts leading to enhanced electrical performance and ultra-low noise. Thank you. And please convey our...
Thank you, Arup. Very nice talk.
Thank you, sir.
Please convey our hello to Supreme also. Okay.
Yes, thank you.
Okay. Okay, then let's move to the next speaker. I think it is Swapna Sindhu. Are you there?
Yes, I'm here. Can you hear me?
Yes. Oh, so you are talking on this topic which has recently come up in the applied physics letters?
Yes. Yeah, this is the one we published recently. Yes.
This is very interesting work. So welcome to this symposium, and I can see your slides. You can get started.
Okay, thank you for the introduction. So my talk will be on Josephson junctions containing nickel, ruthenium, nickel synthetic antiferromagnets. And this work was done at Michigan State University under the supervision of my advisor, Norman Burge. And this research was supported by Northrop Grumman Corporations, where we have really close collaborations with. So before I start my talk, I would like to say something about my time at LNMM, NICER. So I joined NICER as an integrated MSc student from 2012 to 2017. And I was working in LNMM from my second year onwards till I graduated. And while there, I worked on multiple topics. One of them was thin film simulations. Also did some work on relaxation dynamics in PMA cobalt platinum antidotes, mostly the simulations part, which was published in scientific reports. Then I also worked on simulating some of the early work of simulating skyrmions with variable DMI, and which was again added on a lot by Arup and published in JPD. I was also working towards the end of my MSc on a post-magnetic setup, but I had to leave it incomplete to go start my PhD. The time there was really nice. It was fun learning physics from all of my professors, and also learning a lot of lab work from my advisor, Subhankar Vedanta. So now I'll move on to my talk. So this is the brief content of my talk. I'll give you a little introduction about the superconductivity and ferromagnetism. Then I'll say what the superconductor ferromagnetic proximity effect is, and then how to achieve something called phase control in an SFS Josephson junction, and its application in Josephson magnetic random access memory, or JMRAM. And then I'll talk on my specific project, which is the nickel ruthenium nickel synthetic antiferromagnets. and then give some summary on my work and some future plans. So what's superconductivity and magnetism? So in conventional superconductors like niobium, conduction doesn't happen by single electrons, but it happens by a pair of electrons called Cooper pairs, and they're bound by something like a phonon. But in ferromagnets, electrons always tend to prefer to be aligned parallel to the external field. So as you can see, this gives us a problem because superconductors have antiparallel spins and ferromagnets want it to be parallel. So for a lot of time, we used to think that superconductor and ferromagnets are antagonistic orders of materials, but they are not really so, because superconductivity can actually leak into thin ferromagnets. And similarly, magnetic fields can also penetrate into superconductors. And this interaction at the interface of a superconductor and ferromagnet has a really rich physics and has a lot of applications, one of which is a cryogenic memory in an energy efficient superconductor. So what is SF proximity effect? What happens when you put a ferromagnet next to a superconductor and try to push a supercurrent through it? Is what will happen is the Cooper pair or the supercurrent will decay into the ferromagnet. That's true for all materials, but ferromagnets are special in that it not only decays, but there's also this oscillation in ferromagnets. And that is because of these band structures in ferromagnets, where one of the spins sits higher energy than the other spin. And this creates a problem for the Cooper pair because now it has this net center of mass momentum that gets accumulated in the ferromagnet. And this center of mass momentum will show up as a cos function or as an oscillatory function. So this is why this oscillation takes place. So what happens if we put another superconductor next to this SF that was already there and create a Josephson junction? So what will happen is, so the supercurrent will oscillate and also decay, and that will oscillate between 0 and pi phases. This is because the way the supercurrent oscillates in direction and also how it shows up in the energy of the Josephson junction. So the question one might ask is, can we actually use this somehow? And the answer is yes. So what we do is, let's, instead of using one ferromagnet, to use two ferromagnets and make one of them harder to switch and call it a fixed layer like nickel. And the other one is something called a permalloy, which is a really easy to switch magnet, and it's the free layer in this design. So it's similar to the MRAM design that magnetic people work on. What happens now is we'll design it in such a way that in its parallel state, it will stay in one of these pi states here that I showed before. And now when we switch one of the easy magnets, the permalloy layer, it will switch back to the antiparallel because the magnets are now canceling each other. So this is how you can achieve phase control between these pi and 0. So now you have two states and you can toggle back and forth. So now that's a memory device. And that's that has been shown in theory around 2002 and also shown experimentally by our group in 2016. And this application of this phase control was done by our collaborators at Northrop Grumman. And they have this entire architecture with lots of read lines and write lines that are present in a memory structure. But I want you to focus on only this part, which is the magnetic Josephson junction. That's where the information actually resides. So that's what we work on most of the time. And but there are some problems with this design, especially with the materials that we use. The free layer permalloy has really low supercurrent transmission compared to nickel. But the bigger problem is that the fixed layer, which is nickel, has really bad magnetics at low temperatures. It has multi-domain magnetic structure and can interfere with how the free layer switches. And that's a really bad thing for you to have in a memory device. So one of the idea was to, why not replace this really thin nickel layer with a really thicker nickel layer? Because as the magnet gets thicker and thicker, the magnetic properties tend to improve. But the problem is if you keep making it thicker, it'll shift where the 0 pi location was, and that'll make your memory device really poor. So we came up with an idea that why not replace this really thick, thin nickel with a really thick nickel, but a synthetic antiferromagnet nickel. So what we'll have is we'll have a really 2 layers of nickel, one of them thick and one of them thin, and we'll be coupling with a coupling layer like ruthenium. And so the effective magnetic field that the system will see is the difference between the thickness of these 2 nickel layers. So before, and there has been some theory work on this, and it predicts that the pair decay oscillation should only depend on the difference in thickness and not the total thickness. But before we study any of that, we need to study this system nickel ruthenium nickel SAFs first, because this system is completely new. We didn't find any magnetics or transport properties in the literature. So we went about actually making this system. So we made thin films of nickel 2 on both sides, and then varied the ruthenium thickness, which was the coupling layer. And what we did was we measured the M versus H curves, and we get this really different curves depending on the thickness of the ruthenium. So what happens, it varies from a really ferromagnetic layer to a really antiferromagnetic layer. And what you can do is extract the saturation field values where these curves saturate and plot them, and that will plot the saturation fields with respect to the thickness, and that will give you a really nice oscillating function, which is called the RKKY interaction. And what happens is at some thicknesses it will have ferromagnetic coupling, and some thicknesses it will have antiferromagnetic coupling. So the first antiferromagnetic peak was at 0.9 nanometers, and the second one was 2.3. So the next thing we did was, once we found, okay, this is where our antiferromagnetic peak is, we fixed the ruthenium layer and we varied the nickel layer, because that's what we are going to vary in our actual junctions. So we did that and then extracted the saturation field, moment values, and plotted them just to characterize them. So with thickness, the saturation field really goes down, which is pretty good. And also with thickness, the moment goes up and stabilizes around the literature value of nickel. So that's also pretty good. So what it tells that in really thin nickel, there's some dead layers, but that's okay. As far when you go to thicknesses where you actually make devices, they're really good. So that works for us now. So the next thing is to make junctions. So what we do is we actually put down our bottom leads and then form our pillars. And our Josephson junctions are these micrometer thin ellipses. And they have this nickel ruthenium nickel and then copper for good growth. And we have niobium on top and bottom as our superconducting leads. And this pillar is protected for oxidation and also from any short by a layer of silicon oxide. And that's how it looks like the picture of an actual device. So once we are done fabricating our devices, we do a 4-probe measurement inside liquid helium. And we also have a magnet that goes around it's enveloping the silicon chip, so we can apply magnetic fields. So the first thing we can do is check the Josephson junctions by applying a bias current and checking how the voltage develops. And as you know, the Josephson junctions are really weird in the sense that there's no voltage across them until a critical current, and then all hell breaks loose and we have this voltage. So the maximum amount of current that we can push through is this critical current around here where the voltage starts shooting up. And we can extract these from our IV curves. And then we change the magnetic field and plot these IC values with respect to the field, and we get something called a Fraunhofer pattern. It's called Fraunhofer because it's similar to the optics Fraunhofer in the sense that we have this bright bands and dark bands, but it's just high current versus low current at different fields. And for a normal ferromagnet, it looks like this. The blue curve is the downsweep and the red curve is the upsweep. And there's this shift because the magnet switches, and it also has some internal magnetization. So that's how it looks. But come to our actual junctions of nickel ruthenium nickel SAFs. When we do the ICRN versus field, what happens is we get this symmetric Fraunhofer. This is because the two layers of nickel are compensating each other. So there's not really any magnetic shift or switch taking place in our junctions. So they are really stable even at really low temperatures. So then next thing we did was take these IC values of these Fraunhofers and for each thickness of nickel, and then multiply with the resistance just to normalize, so that because there can be variations in the shape of the ellipse or the size of the ellipse, quality of the junction. So multiplying with Rn normalizes it, and then we plot it with respect to the total nickel thickness. And what we see is this beautiful exponential decay, which matches up with theory. So there's nothing new until this, but the only good thing that we found in this work was that the decay constant is really, really high. So it's like 7.5, which is much longer, almost twice as high as plain nickel, which is like 4 nanometers. So this is because these nickels are canceling the phase. So the supercurrent is not seeing a thick magnet, but it's seeing a really thin magnet that have been compensated by the two layers. So it decays really slow with thickness. So what it means that we can vary our thicknesses in our devices and still get it to function. So that's our next work. So in summarizing my talk, the superconductor ferromagnet interface has really rich physics and applications in cryogenic memory. Phase control in these Josephson junctions have been demonstrated and have been applied in a JMRAM device, but the magnetic layers need a lot of improvement. And that's where we come in, and we're working on improving the free layer and the fixed layer. And the talk that I gave was on the fixed layer. And the potential is that we have this nickel, ruthenium, nickel SAFs that can replace these fixed nickel layers by creating an unbalanced SAF layer. And the really interesting thing that we found was this really slow decay constant in these SAFs versus the plain nickel. So future work is to be done. I have some magnetic data that I can't really show right now, but we have to study the Josephson junctions and see how these unbalanced nickel, ruthenium, nickel layers actually function. And we can then put a permalloy flea layer and see whether it actually interferes with its switching or not. So that's still to be seen. So thank you. That was my talk. And if there are any questions, let me know.
Yeah, thank you very much for this very nice, interesting work. I already see a hand raised by Ansuman. Go ahead.
Thank you, sir. It was a very interesting talk. So my question was, you used a ruthenium layer, right? So
yes.
What, my first question is how exactly it couples? Like what exactly it couples? Like there are whether it's the moment of the two layers of different thicknesses. And the second question was, what was the role of copper? You used some 2 nanometer thick copper. Was it to avoid some adhesion issues or what?
Yeah, well, I'll answer the second one first because it's simple. Yes, copper is just there because ferromagnets don't grow well on niobium. So in our group, we always use copper as just for a really good growth layer for the ferromagnets. Because copper grows well on niobium and then everything else grows well on copper. So that's why. So RKKY, so I had this small footnote. It's actually an indirect exchange coupling between the spins of these two layers. And this happens by localized inner DF electrons. So it's actually a second order effect that shows up if you do the perturbation theory. So actually the spins of these two layers are getting coupled by the ruthenium atoms, also the nuclear spins of the ruthenium atoms.
Okay, Swapna, that was your junior from NICER, Ansuman. Next question is Swagata.
Hi, Swapna.
Hello,
Very nice talk. I have a couple of technical questions. One is the inset loop. I think it is normalized. It's not real scale, right, in this one, because they kind of have the same magnetization, and I don't believe that is correct.
No, it's actually not normalized. So these are actually raw values from a MPMS-3 measurement, which is a squid magnetometer. And since all of them have the same nickel thickness, we would expect them to have almost similar movements. There are some samples which will have slightly lower or higher, but all of them should have pretty much close to 450, which is the, I think, or 430, which is the moment value of nickel at low temperatures at 10 Kelvin.
The second question is, these nickel layers are in-plane magnetized or out of plane? Because I think I see that you vary the nickel thickness over a wide range. So I believe that the magnetization changes from out of plane to in-plane, or it is in-plane in the whole regime.
It's in-plane in the whole region because we're starting at 1.2 nanometers on each side. Maybe if we go really thin, like sub-nanometers, it might become a PMA. I don't know. But all our junctions have ellipses, and the easy axis is pointed along the ellipse in plane. So all of our magnets are in plane. We actually checked. So when we had low moments in these samples at really low thicknesses, we actually went back and checked out of plane just to make sure that these are not out of plane samples. These are actually indeed in plane and have dead magnetization.
Okay, and the third question, sorry, can you please go back to the previous slide?
Okay.
You see, like in RKQI, what we will expect that the periodicity increases with the increasing thickness of the spatial layer. But you see, if you see the first peak, it's starting from something like 0.6 nanometer going up to 1.3. So the periodicity is like 0.7. However, the next period is only 0.4 nanometer, where you should see the ferromagnetic in the other side if you plot the exchange interaction, but it's the saturation field. Why do you think for the antiferromagnetic regime, it's following the trend and not for the ferromagnetic regime? Is there a reason behind this?
I do not have any idea about this. We also didn't go like more thicker, and also we didn't look at the third peak. Maybe that would have given us some clue, but right now I have no answer to that question.
Okay, fine. Thank you.
Thank you, Swagata. Thank you, Swapna Sindhu, for this very nice talk. And please convey our regards to Professor S.D. Mohanty.
I will definitely do that.
And we have a plaque for you in appreciation of being a valuable speaker in giving this nice talk on Josephson junctions, which has wide applications into quantum computers, as I understand reading your paper and comments on it. Thank you very much.
Thank you so much.
Okay, next speaker, Biswajit Sahu. I don't know whether he will speak on music, photography, or a painting. Let's see what he is going to speak today.
Good morning, everyone. Can you hear me properly?
Yes.
Okay. So I'll just turn off my video so that there is less bandwidth consumption. Good morning, everyone. It's morning over here. Good evening, everyone. Today, my talk will be on efficient charge to spin conversion in 5T transition metal oxide. This is the work that I'm doing for one of my projects of PhD under Eric Fullerton. I'm working at University of California, San Diego at the Center for Memory and Recording Research. This work is funded by a collaboration of a group called as Quantum Materials for Energy Efficient Neuromorphic Computing. So this work is actually an extension of what I did for my master's thesis under Professor Vedanta from 2014 to 2019. I believe he's proud of me because in the pictures he seems very proud. I don't know. I mean, I've gotten a lot of scoldings and advice from him. And thanks to his recommendations, I could get a nice PhD offer from UCSD. So I'm very thankful for him and all the experiences that he gave me. Coming to the topic. So why do we need efficient charge to spin conversion? So the thing is, charge-based electronics are reaching their limitations due to Joule heating, which will limit the number of bit flips that we can do in a processor. So what the way out of this dilemma is basically we use spin instead of charge to represent binary states. And the spin states can be manipulated by spin torque effect or local magnetic fields. The picture over here shows all spin switch, which is developed by Supriyo Datta's group. So they use pure spin currents to switch from 0 and 1 state. The advantages of using spin is basically there will be no Joule heating, and the only power dissipation will be due to the bit flip, which is of the order of a few kVt. Now, there are a number of ways that we can generate spin current. One of them is the optical methods, where we use polarized light to excite different spin states. The other one is the electrical injection, where we pump in a normal charge current through a magnetized ferromagnet. When it gets out, the charge current that comes out of the ferromagnet is preferentially aligned. The spins of the electrons are preferentially aligned in the direction of the ferromagnet. There's another popularly used method called as spin pumping, where we excite a precision in the ferromagnetic layer, which pumps in the spin angular momentum into a non-magnetic layer. And finally, the most used, commonly used effect, as in the platinum ferromagnetic heterostructures, which is the spin Hall effect, which converts directly charge current to a spin current due to spin orbit coupling. So in brief, spin Hall effect converts charge to spin current. It depends on the spin orbit coupling strength of a material. And since SOC is proportional to Z to the power 4, Z being the atomic number, platinum, palladium, tantalum, like heavy metals are generally preferred. However, iridium oxide also exhibits high SOC, not only because its atomic number is very high, I believe it's 76, but also because in iridium oxide, we have IR plus 4. The 5d electrons in IR plus 4 actually increase the SOC strength with respect to pure iridium by 2 times approximately. There are other theories as to why there is high spin Hall conductivity in iridium oxide. So basically, iridium oxide contains networks of Dirac nodal lines inside its blowing zone. So a DNL is basically a one-dimensional version of a Dirac point. So due to high SOC in iridium oxide, the high symmetry points, that is the hexatriple and octuplet points, they actually split, leading to formation of more DNL lines, as we can see in this GGA in ab initio calculation. And this leads to high spin Hall conductivity in iridium oxide. Further, these nodal lines can also contribute to large magnetoresistance, which are robust against chemical perturbations. Coming to the basics, iridium oxide has a rutile crystal structure with these parameters over here. They have the IR06 octahedra. They share the edges along the C-axis, while there is corner sharing among the counter-rotated neighboring chains in the 001 plane. So because of this mixture of both edge and corner sharing in the IR06 octahedra, there is a relatively direct coordination between the iridium atoms that provide additional hopping channels for the electrons and results in an increased p-d orbital hybridization. So this leads to iridium oxide acting as a band metal in the weak interaction regime. I shall discuss like why this is important for my experiment in the later slides. So till date, the first experiment was done using iridium oxide by Fujiwara et al., which was published in Nature Communications. And they used very nice non-local spin valve measurement structures to find that the spin Hall angle, which is the charge to spin conversion efficiency for iridium oxide, to be 0.065. Since then, iridium oxide has picked up interest recently, considering this is a 2020 paper using harmonic Hall signal, which showed again a SHA of 0.093 in amorphous iridium oxide. A very detailed work using epitaxial 001 iridium oxide by Bose et al. From Cornell University. They did this a very nice work where they showed that the iridium oxide SHA can be theoretically up to 75%. In this experiment, actually, they showed that the actual value they showed was 35%, but since they put an iridium interlayer in between the permalloy and iridium oxide, they claimed that the interlayer like took away around 50% of the spin that was being pumped into the permalloy, causing the SHA to be less, like 50% less. And finally, this is the work that I did for my master's thesis, where I showed that the polycrystalline iridium oxide, by spin pumping, the spin Hall angle is around 25%. So following that, I decided to grow iridium oxide over here. I have used reactive magnetron sputtering. What I need is basically extremely smooth layer of iridium oxide, and they should be highly conductive as well. So I used a variety of deposition processes to optimize the growth of the iridium oxide, and finally I could achieve that. So at room temperature, when I deposit, I see that from the fitting, the roughness is around 0.6 nanometers. But when I anneal it in the vacuum chamber at 700 C, the roughness decreases to 0.341 nanometers. However, upon depositing iridium oxide at 700 C heated substrate, the growth is extremely polycrystalline and it's very rough. So to confirm my findings, I use AFM to find the roughness of the iridium oxide. As you can see, when I anneal it at 700 C, the surface is extremely smooth with slight bits, localized bits, and this has a roughness of 0.2 to 8 nanometers, which is like very good for spin torque ferromagnetic resonance experiments. To find that, to confirm that the thing that I'm growing is indeed iridium oxide, I did XRD measurements, and we see that when I anneal the iridium oxide, which is the green curve over here, there is 3 peaks, which corresponds to iridium oxide 110, 101, and 200 structure, confirming that this is indeed a polycrystalline thin film. Further, via 4 probe measurements, I find that the resistivity of iridium oxide is 142 microohm centimeter for a 30 nanometer thick film, which is comparable to that of a 10 nanometer of covert iron boron room temperature grown film, which is about 120 microohm centimeter, putting iridium oxide's conductivity in the metallic regime. So all these properties basically help me to like convince me that yes, I can do STFMR and get proper signal out of the system. So what is spin torque ferromagnetic resonance? So in any standard paper or publication or books, this is the first figure that you'll find: a normal GSG waveguide system with a bias T attached to the signal and ground connections. And the sample resides in this blue area. The sample resides in this blue area over here, and we apply an external magnetic field, which is slightly non-collinear to the alignment of the sample. So the dimension is around 10 micrometers to 20 micrometers. It is quite localized. So what happens is basically we inject IRF current, which excites the magnetization dynamics of the ferromagnet. Now, when this RF current goes into the transition metal oxide, in this case iridium oxide, it generates an oscillating transverse spin current due to the spin Hall effect in the iridium oxide. This spin current gets injected into the ferromagnet and exerts an oscillating spin torque, which affects the excitation magnetic moments of the ferromagnet. The magnetization precision leads to an oscillating bilayer resistance due to an anisotropy magnetic resistance effect. The mixing of the IRF and the oscillating resistance gives rise to a DC voltage signal over here. And the magnitude of the voltage signal is maximum at resonance, because in the resonating case, the maximum number of moments is simultaneously leading to a big signal over here. So ideally, from a particular profile pattern, the more symmetric, so this signal is generally a mixture of symmetric and antisymmetric Lorentzian. The more symmetric a signal is, greater is the spin torque in the system. So finally, the voltage, the oscillating voltage is detected after being filtered out. After the RF component is filtered out, we only get the DC component from the voltage after passing it through a bias T. So to find the spin Hall angle in this system, we use this equation over here, which was developed by Liu et al. In 2011. This is valid for line shape analysis for systems whose dimensions range in the micrometer scale. For smaller scales, it is better to do line width analysis. So this is a standard STFMR curve that I got for iridium oxide 20 nanometers, cobalt iron boron 7 nanometers, capped by a silicon oxide 5 nanometer protective capping. So we see that there is a symmetric and an antisymmetric component, and we fit these for various thicknesses of iridium oxide And we find that the SHA tends to saturate at around 30% for 20 nanometers of iridium oxide, which is close to what was shown in the advanced quantum materials paper of around 25%. But I want to basically use this iridium oxide for other purposes, such as spin Hall nano oscillator. So I was thinking of how to increase the amount of spin torque that is being injected onto the ferromagnet. So what I do is I cap it with a platinum 5 very thin, which is 5 nanometers of platinum layer, and check how the SH's STFMR signal looks like. We see on the right hand side that the S by A ratio is 1.3. That is the symmetric part of the component dominates as opposed to the antisymmetric part in just pure iridium oxide, showing that a platinum layer actually has a has the opposite sign of the spin Hall angle as iridium oxide and can be used to achieve greater charge to spin conversion. But then again, if I use platinum, like is platinum the one that's dominating, or is it iridium oxide? So I fabricate again a range of samples where I increase the thickness of iridium oxide ranging from 1 nanometers to 20 nanometers. And we see a very nice variation of the amount of the symmetric component that is being added. Now, as we can see, when the iridium oxide layer is very thick, the S by is approximately 0.33, which is like the same as that of just iridium oxide 20 nanometers without any platinum cap. But as I continue to increase the thickness of iridium oxide, the symmetric components dominate more and more and reaches a value of 1.32. This means that iridium oxide has a definite effect on the system, and a platinum iridium oxide bilayer sample can actually increase greater spin torques on the system. So since I could find high spin Hall angle and high conductivity in this samples, I believe my future that this can be used for spin Hall nano oscillator, and that's my future plan. So in a conventional magnetic moment, what we do is when the magnet movements are excited, there is a damping action which aligns the precessing magnetic moments in the direction of the external applied field. This is due to the dissipation of angular momentum of the magnetic moment. So this is how a simulation looks like. But what will happen if somehow we put a charge current due to SHE, it gets converted into a spin current, which is basically spin angular momentum, and compensates the dissipation of the angular momentum. So what we'll have is a oscillating, continuously oscillating magnetic moment, which is also called as the auto oscillations. So the damping becomes zero at the critical current, and that's where the auto oscillations set in. So basically, what I do is what I plan to do is make a tapered device with the nanometer size confinement at the middle, which can provide high current densities for providing auto oscillations in these frequencies. Of course, a lot of parameters have to be tuned, such as the constriction width and the amount of current that can be sent into the system. Till now, I have been able to go as high as 18 milliamperes without breaking the system. So further work is in progress in this particular material, and we'll be publishing a paper on this very soon. Conclusion, highly smooth polycrystalline and conductive iridium oxide thin films could be grown. The spin Hall angle in 20 nanometers of iridium oxide was found to be approximately 29%, give or take 1% of error. And these properties prove that iridium oxide is a good candidate for spin Hall nano oscillators and spin torque applications. Thank you.
Thank you, Biswajit, for this nice talk. Let's see if there are any questions, comments. Swagato.
Hi, Biswajit. Very nice talk.
Thank you.
I wanted to know how this figure compares with platinum. I want to know this because, like iridium oxide will be quite resistive. So even if you have a high spin Hall angle or something, when you really want to apply some charge current, you have to apply very large voltage, so to say. So I would like, because most of the people use platinum, that's why I want to know how the comparison figure is with platinum. Do you have any idea about that?
Yes, yes, of course. So I am doing currently DC current analysis, and it is actually quite similar to that of platinum. Like if I have, let's say, 20 nanometers of platinum, of course, it's quite what do you call this? Quite conductive. But then again, what we are like concerned is about just the spin diffusion length, which is like around, which is similar for iridium oxide and platinum. So I can basically use a 20 nanometer of iridium oxide, and I find that I can push up to 20 milliamperes of DC current before blowing the system, as compared to platinum, which is around 21 to 22 milliamperes in my devices.
Okay,
So
and what is kind of the sheet resistance when you just have a iridium oxide layer, let's say in 4 probe?
yes, so it's just 142 micro ohm centimeters, which is comparable to cobalt iron boron, which is 120 micro ohm centimeters.
Okay.
Yes, which is like quite metallic.
Okay. Okay. Thanks.
Okay. Thank you, Swagato. Any other questions, comments? Okay, if not, then Biswajit, I have one question. What are
Yes,
the
sir.
Dirac nodal lines? Is it some point where some bands meet?
Yes,
Or
exactly.
is it some
So
topological structure with symmetry? I don't know. So what are those?
yeah, so basically so for our Dirac points, what we have as in graphene, we have basically a conduction band and a valence band. They come and meet at one point. But in this case, in iridium oxide, for example, it is slightly bit more complicated, and those bands, instead of being like focusing on one point, they're extended in 2 dimensions. So where they meet is basically still a 1-dimensional extension. So it's like, so over here, if you see in this figure, this blue figure over here.
Yeah.
So it is like an extension. This over here, the meeting point, that's Dirac nodal line, and it does have topological protections. Yes.
Okay, great work. Very nice talk. Thank you very much.
Thank you.
I think with this, okay, you have a plaque. This is in appreciation for being a valuable speaker and giving lecture at this symposium on magnetism and spintronics on efficient charge to spin conversion in 5D transition metal oxides. Wish you all the best.
Thank you so much.
Sajid. And it
Thanks
was
so much.
great seeing all the nice ex-Nicerites giving such nice talks. Things have changed. I mean, yeah, beautiful work. So thank you all for this nice session.
Thank you.
Okay, over. Oh, there is something for me also. Okay. Okay.
Oh,
Thank you so
okay.
much.
Yes,
over to you.
actually, I want to say that Biswajit, I'm very happy to hear this nice lecture. You are basically all continuing the same work what you were doing here, and I'm seeing that instead of 25, now you have got 29%, and probably the annealing was a bit increasing the efficiency. It's going the right direction. So,
yes, sir.
for you, and okay, we are not working on spin talk nano oscillators, and I think it would be nice if you do that. Good. So
Yes, thank you,
thank you so much, guys. I'm very happy and privileged to present this small memento also for our session chair. I read it for you. So Symposium on Magnetism and Spintronics, SMS 2021. Takes immense pleasure in presenting this plaque to Professor Bedang Das Mohanty in appreciation for chairing the session 3 very, very efficiently and very nicely. Thank you so much.
Thank you for the second plaque for today. Okay.
Okay. So see you tomorrow, all participants. We'll start exactly at 2 o'clock. And tomorrow we have very vibrant poster sessions. So see you tomorrow. Have a good night, or the people from US have a nice day. See you. Bye-bye. So we end the session for today. Thank you. Thank you all.
Bye. Good night.
Bye. Bye-bye.